of retired ISRO scientists, SAC especially, those who work in the field of remote sensing, उनको भी कहा है और they will all join on YouTube.
In Department of Space, I had Dr. K. Radhakrishnan with me.
जी.
And Shailesh Naik was with us.
Correct. तो शैलेश नायक तो बेंगलोर में ही हैं आजकल.
Was PS Goel भी join करा था. Muthu Nagam. So we have a history of a lot of space people.
Correct.
माथुर साहब ये पीसी जैन साहब थे हेडक्वार्टर.
कौन से? हाँ, जैन साहब वो अहमदाबाद आ रहे हैं अभी.
हाँ, वो इन स्पेस वगैरह के लिए कुछ.
हाँ, वो अपनी बिल्डिंग में ही थे ना, 21 नंबर बिल्डिंग में ऊपर बैठते थे वालदिया जी के साथ.
वालदिया जी के साथ बैठते थे.
हाँ, सेम.
हेडक्वार्टर काफी टाइम मिला हूँ उसको.
हाँ, वो काफी मतलब जगह मूव कर चुका है. पहले एनआरएस से हैदराबाद में था. वहां से सैक आया, ट्रांसफर होके सैक से बेंगलोर गया, फिर वापस सैक आया, अगेन ही वेंट टू हेडक्वार्टर. नाउ आई थिंक
अभी इन सर्विस है.
सर्विस है अभी, मेरे ख्याल ये लास्ट पोस्टिंग होगी, इसके बाद हो जाएगा रिटायर.
अच्छा अच्छा.
यहीं पर ही.
इसका मतलब पहले से ही वेल इन एडवांस उसको. अच्छा. कल ये इनॉग्रेशन फंक्शन था साइंस सिटी में.
हाँ, वो ह्यूमन स्पेस मिशन के ऊपर
गगनयान.
गगनयान का.
हाँ, तो डायरेक्टर साहब भी थे अपने.
गए थे आप देखने के लिए वहाँ? गए थे?
नहीं, मैं गया
ऑनलाइन.
मैंने ऑनलाइन देखा था.
Veena, you can see it is right now 10 o'clock. If all the people from your college side have joined, I think we can start the program. Welcome, Sitaram ji.
Morning, sir. One and all.
Yeah, very good.
Chintamani, sir.
Yeah. Am I audible?
Yes.
Yes, sir. You are audible.
Okay. So, very good morning to everyone. I am Chintamani Pai, co-founder of Space Geeks, and it's great to be here as a part of the awareness webinar series on opportunities and challenges for science students in space sciences. And a very warm welcome to our today's chief guest, Padma Shri Professor H.K. Gupta sir, who has agreed to be a part of this event and will be inaugurating the event and giving the online talk. He is a renowned geophysicist. He is also the president of Geological Society of India, and it's great pleasure to have you, sir, and to inaugurate this awareness webinar series and to give the inaugural talk. Also, a very warm welcome to all dear scientists from ISRO, PRL, and all the associated research organizations and institutions, and also to all the students and teachers who all are part of this event. And I'm sure you will all find this event very inspiring and which will help students to take up opportunities in the field of space sciences and space technology. I'm also grateful to all the other speakers who have agreed to be a part of this event, especially from ISRO and PRL. And I must say that they have been the pillar to develop space science and space technology of our country. And I also welcome Professor A.C. Mathur, who is the founder of Indian Space Industries Exhibitors, principal of the college, Dr. Horakiri, and head of the physics Dr. P.R. Jhiagal, and Coordinator Professor Veena. I know that space science and space technology has been very exciting to all of us, and uh, I'm really thankful that all of us, especially from the college, they took interest to organize this event. And to my dear students, teachers, and all the participants who are attending this event from all over the nation and in the hybrid mode, I'm sure that you all are very excited to attend this talk. And as I was talking to Professor Mathur just half an hour ago, we have received around 290 entries all over India, and which is very encouraging for all of us. And I'm sure with the motivation we have been continuing these activities, it is a real fuel for all of us to continue these activities to encourage students to take up careers in the field of space science and space technology. And with that, I invite principal of the college to give a warm welcome to our chief guest and all the other dignitaries.
Thank you, sir. Thank you very much. Am I audible?
Yes, sir. You are audible, sir.
Yes, yes. Good morning. A very warm good morning to one and all present over here on this splendid board of 2-day national level seminar on challenges and opportunities for science students in space sciences, organized by KLE Society's prestigious PC Jabin Science College, Hubballi. So Karnataka Lingayat Education Society is one of the rarest educational institution in northern Karnataka now, which has spread over across the country and across the globe also. So the PC Jabin Science College has contributed and excelled in imparting quality science education in northern part of Karnataka since its inception in the year 1957. It's the first college to voluntarily undergo NAC assessment and accredited with 4 stars in the year 1999. Subsequently, A grade in the 4th cycle with CGPA 3.43 during the year 2007. Recognizing the quality of education rendered by the college, the UGC has granted autonomous status in the year 2007 and extended in the year 2012 and 2018. Based on the excellent performance in the academics, research, and concern for community, the UGC has recognized our college as a college with potential for excellence in the year 2007 and continued second and third phases with a grant of 100 lakhs in each phase. So such a prestigious pure science college is organizing this seminar. So on this important occasion, we are very much having with us now Padma Shri Dr. H.K. Gupta sir. So on behalf of our college staff and students, I extend a warm and sincere welcome to Dr. H.K. Gupta ji. Welcome you, sir.
Thank you.
I extend a warm welcome to Dr. Hari Om Vats, Dr. D.R.M. Samudraya sir, Dr. Alok Mathur, Dr. K.G. Srijay Lakshmi, Dr. M.R. Shivaraman, Dr. Himanshu Shukla, Dr. Arjit Roy, Dr. Raj Kumar, Dr. Shashi Ganesh, and Dr. Sumanta Sarkel, Dr. Raj Kumar, and Sri Anant and Sri V.K. Jain. So such a galaxy of space scientists we are having today now. So once again, I extend a warm and sincere welcome to all the galaxies of space scientists who are going to enlighten our staff members and students during these 2 days. And I extend all the faculty members who have joined this blended mode, and I extend a warm welcome to all the delegates and students who have joined this webinar series for the 2 days, which is going to be held on 4th and 5th today, that is, and tomorrow. So with this, once again, I welcome you all to this grand event. Welcome one and all. Thank you. Thanks a lot.
With that, I invite Professor Bharat Mehta sir who is also ex-scientist from SAC ISRO, to present few activities on the behalf of Indian Space Industries Exhibitors.
Thank you, Chintamani ji. Is it okay? I can hear audible?
Yes, sir, you are audible.
You can see my screen?
Yes, sir.
Good morning, everybody, and welcome on this national webinar on challenges and opportunity for the science students in space sciences, which is organized by ISI Ahmedabad in association with KLE Society's PC Jabin Science College, Hubballi. Here I am Bharat Mehta. I am specifically giving you the highlights of the Indian Space Industry Exhibitors, the activity and the detail about this MSME. About ISI, if I say it's a micro venture under the MSME New Delhi, it was registered as an educational company in June 2018. It is an initiative by Sri A.C. Mathur, an IIT Roorkee alumni and retired group director of SAC ISRO. It's a registered office at Ahmedabad and a working office at Ghaziabad. If I give a brief introduction to Sri A.C. Mathurji, he is a MD of ISI. He did BE and ME Mechanical Engineering in 1977 from IIT Roorkee. And he joined SAC ISRO Ahmedabad in 1978. Retired on superannuation in the year 2017. Hence onward, he has already started this ISI activity. Addition to that, he is a life member of many society like ASI and SSME, ISRS and IU, and founder secretary and ex-president of SSME. He's current president of IIT Roorkee Alumni Association Ahmedabad, and is active in delivering invited talks in schools, colleges, and conferences about space applications for the common man and the challenges for the young engineers. The vision of ISI, if I brief you, to spread the awareness about the tremendous applications of space science and technology among the young school and college students. Like this webinar we are conducting on this motto, which is along with the common man of India to popular lectures, awareness seminars and exhibitions, etc. The advisory board of ISI, if I can give you the name of the advisory board member. First is Sri Vilas Palsuleji, he is the ex-director DECO ISRO. This Sri Vikram Desai, ex-director DECO ISRO. Sri A.M. Jha, ex-deputy director SAC ISRO. Sri Arun Saxena, he is ex-EDM general manager Indian Railway. And Sri S. Velachami is ex-head HRD ONGC. The highlighting the activities of the ISI, which gives the awareness seminars for the students and youngsters, the national seminar and conferences for researchers, professionals and academicians, short-term courses for engineering student, researchers, professionals and academicians, space science galleries for the common man in the cities and villages, the skill development program for technicians working in Indian space industry. And the other activity, like we have already initiated, the Space News magazine, which is badly needed in our Indian area, because here we don't have such magazine. So we have started the Antariksh Udyog, which is started in August 2020, which is a platform for sharing information by the academic, R&D and the industry. If you give the breakup the activities in year-wise during 2018 to 2020, the various seminar and webinars organized during this period on a different topics like satellite communication for common man, different types, materials and structures and application on satellite remote sensing, 3D printing, and its application in engineering, and many more. During 2021, online awareness lecture series on satellite navigation, NAVIC, and application for the common man, which is 5 popular talks already given in National Science Day on February 20, 2021. The speakers is also very prominent, like it has been mentioned here, Dr. Arvind Ranade, Professor Kale, Bandariji, Ashok, NM Ashok, and Dr. Hariom Bose. The various collaborative programs also being conducted, which is in academic wise, there is IIT Roorkee, Sri Nadar University. For R&D, it's in Natira, Ahmedabad. NGOs like Space, Mumbai, and then professional association like SSME, IEI, ISRS, IMSA, and ISG, etc. The short-term courses in future we are planning, like short-term courses on small satellites, a short-term course on mechanical design and fabrication of satellite earth station antennas, a short-term course on composite material technology, short-term course on SATCOM earth stations, and plan for the mobile space science exhibition also. The plan to create a team for organizing exhibition in school societies of various towns and villages of NCR, particularly National Capital Region and other parts of the country too. The awareness seminar, the seminar on space thermal system with Nirma University, then seminar on habitats and mining on moon, team of civil engineer and architect already working, seminar on space education for school teachers and students, and the seminar on application of space science and technology for the common man. The broad topic and topics for this activity like remote sensing, satellite communication, space material, composite, lightweight, stiff and smart material, advanced manufacturing and design technique, additive manufacturing like 3D printing, development of Indian industry for the space software and hardware, etc. We have already association with a few of the academic institutions and academic and professional institutions that can help by providing their auditorium and other logistic support to ISI for organizing such activity. They can also become a joint organizer to have activities in the various parts of India. The Space Science Gallery Ghaziabad that we have already started, it's a permanent space exhibition. It is given a name as Sri Lal Bahadur Shastri Space Science Gallery. Started on the Gaur Homes, Govindpuram, Ghaziabad on 4th October 2019. Poster related with the space basics and applications already there in display. Students and local residents, they already started visiting on Saturday and Sundays. The future activity or the work in the gallery, the models of satellites and rockets to be added, posters and flex banners to be printed, books on space topics in Hindi to be added, scientific workshop or the Antriksh Udyog magazine, as I told you. I'll just give a brief highlight on the magazine detail. It's a publication of a magazine highlighting the work carried out mainly on the research activity by the academic institution, product developed by the Indian government, private industry of space. The first issue, till now, we have already published 6 issues. It is a quarterly magazine published on the digital platform. So we can also circulating through our members who is registered. And there is a first issue we have already started on 30th October 2020 by Sri Padma Shri Pramod Kaleji, his Egg Director SAC, Ahmedabad. And the last 7th issue we are just going to introduce soon on 19th April. These are the editorial board. B.D. Mehta, myself as a chief editor, retired from SAC ISRO as an head of the department. Sri B. Subramaniam ji, retired deputy director SAC. Dr. S.M. Bhandari, retired scientist, Sec ISRO. Shri A.C. Mathur, retired director, Sec ISRO. Shri K.P. Balso is a retired scientist, Sec ISRO. Shri Sanjeev Kandaji is a consultant for this, and Shri M. Srinivasam, retired scientist, Sec ISRO. Shri Vinod Kumar Srivastavji, retired range officer, SDSC. These are the first page of the previous space magazines which we have already released. It is every time we cover have a cover story of a different topics, as it the small satellites, then on orbit satellite servicing and refueling, then IRNSS, NAVIC, ISRO, then telemedicine. Last was the space tourism, and the next issue is going to be on a space materials used for the satellite communication and other activities. Now, contact detail for ISI, you can contact Mr. A.C. Mathurji. Number and the email number is already given. Thank you very much. Thank you all.
Thank you very much, Bharat Mehta, sir. With that, I invite the head of the Department of Physics, Dr. Jiragal, sir, to talk briefly about our webinar series.
Good morning to each and everyone who have taken the part in this important webinar series. Once again, I extend a warm welcome to all the renowned resource persons. I, Dr. P.R. Jirigal, the head of the Department of P.C. Jabin Science College, head of the Department of Physics, P.C. Jabin Science College, would like to highlight about the importance of today's and tomorrow's the webinar series. There is no need to tell much about the importance of this webinar series. Everyone is well known about the importance of this series. Anyway, as a formality, I'm going to tell few things about the importance of this webinar series. The Indian Space Industry Exhibitors have taken initiative in association with the P.C. Jabin Science College, the Hubballi, in organizing an awareness program of its kind on the various topics associated with the opportunities and challenges in various subjects of a space science virtual platform for the benefit of young science students and a common man of the country. The aim of the webinar series is to create awareness among the science students and educate them about challenges and opportunities available for them in the field of space science. Many students may have interest in joining space research organizations, universities, etc. in India or abroad, or may think of having a startup with the support of a state or central government. During the webinar, a number of invited talks would be delivered by experienced scientific professionals and experts from ISRO, IITs, R&D institutes, and industries. They would be covering the number of topics we will come across in the sessions. Mainly to create awareness among the young students and educated, unemployed in the country. It will create a lot of opportunities for the college students of a science stream, from physics, chemistry, mathematics, and biology researchers and young faculty members, etc. And anyway, this is a very important webinar series during which renowned speakers are going to deliver important topics. And I'm going to request once again on behalf of the Department of Physics, P.C. Jabin Science College, to make use of this webinar series. Thank you one and all.
Thank you very much, sir, for your encouraging words. And with that, I invite Professor V.K. Jain, the ex-head of the Department of Space Application Center, ISRO, and he's also the chairman of Broadcast Engineering Society, Ahmedabad. Over to you, V.K. Jain, sir, to officially introduce our today's speaker. Over to you, sir. Sir, your voice is not audible. No, sir. Jain, sir, are you there?
Sir, Jain sir left.
I think there is some connectivity issue with him. Has he joined, Professor Jain?
No, sir. Now sir has joined.
Okay. So I invite Professor B.K. Jain, ex-head of the Department Space Applications and ISRO, Ahmedabad, and he is also the chairman of Broadcast Engineering Society, Ahmedabad, to officially introduce our today's chief guest, and then we'll proceed with the inaugural talk of the event.
Jain sir.
Bharat sir, if you could confirm if he is audible at your end. Is Jain sir audible?
Dr. Jain, you are muted. So unmute yourself. No, your speech is not audible at all.
Okay, he's saying he's able to listen, but Jain sir, we are not able to hear you.
Chintamani, he has already he has joined. He is there in the chat box. Also, he has put up a message.
Yeah, actually, but his voice is not audible, sir.
चिंतामणि इनका माइक तो अनम्यूट है
Right.
इन सबका, मगर पता नहीं आवाज नहीं आ रही है.
Correct.
He is trying. माथुर साहब.
Jain Saab, maybe you can use some other device like smartphone.
या तो आप फिर से ट्वीट करके फिर इमीडिएटली लॉग इन कर दीजिए फिर से.
Yeah, that also is okay.
He is trying to join with another device, trying to use his smartphone.
enter तो हो गया.
I think there is still issue.
Sir has joined. VK sir has joined.
Yeah. But, are you able to hear? Is he audible?
No, no sir.
माथुर साहब, आपके पास डिटेल है क्या?
Yeah, I think now Jain sir can unmute himself. I think now he'll be audible.
Hello, now I am
sir is
audible.
audible.
Yes.
Yes. Okay.
Jain sir, you may start.
Yeah, can I proceed?
Yes, sir.
Okay. Very warm good morning. Sorry for the inconvenience at our end. Maybe some problem that I will resolve afterwards. Okay. So, most respected chief guest of today's function, Padam Shri Dr. Harsh K. Gupta and other dignitaries, Professor of Principal Science PC Science College, Dr. L.D. Horankari and Dr. P.R. Jeragal, my colleague is from ISRO, from Dr. V.D. Mehta and Shri A.C. Mathur and program convener Mr. Chintamani Pai. I, on behalf of our Broadcast Engineering Society Ahmedabad chapter and my own team, I welcome you all. And it's my pleasure that I have been introduced to the renowned speaker of today's webinar, Padam Shri Professor Harish Chandra Gupta. He is most appropriate person for today's this webinar because he has a vast experience in Geophysical Research Institute and he's connected with ocean development. He's connected with Earth Science Studies. He's doing huge biodata. I will be just introducing about him with a few things. He's a member of National Disaster Management Authority, Secretary of Government of India, Department of Social Development, Director, National Geophysical Research Institute, and Vice Chancellor, Cochin University. These are his former designations. Presently, he's a NASI Platinum Jubilee Fellow, member of Atomic Energy Regulatory Board, AERB, President, Geophysical Society of India, Editor-in-Chief, Encyclopedia of Solid Earth Geophysics Springer, and co-editor-in-chief, Natural Hazard Springer. He has been past president of International Union, Geodesy and Geophysics, IUGG. He has an important contribution, being a member of National Disaster Management Authority in Ocean Development Authority, Secretary of Government of India, Department of Ocean Development, Director of National Geophysical Research Institute, Hyderabad, Advisor of Department of Science and Technology, Government of India, Vice Chancellor, Cochin University, Science and Technology, Director, Center of Earth Science Studies, Trivandrum, Adjunct Professor of University of Texas at Dallas, Research Sciences, University of Texas at Dallas, and he has a major contribution. Apart from that, he has been associated a key focal person for Antarctic mission, Gangotri, conveying. His major significant contributions are development of discriminatory artificial water reservoir triggered earthquake for normal earthquake, which are globally applied, and finding the safe sites for construction of reservoirs, making a medium-term forecast of an M8 level earthquake in northeast of India region in 1986, chairing the many committees like Steering Committee of Global Science Seismic Hazard Assessment, where 500 scientists worked under him to produce the global seismic hazard map, pioneer in the gas hydrogen program and delimiting the zones for stability of gas hydrates within the exclusive economy zone of India, taking up detailed studies of the genesis of triggered earthquakes in the Koyna region and making successful short-term earthquake forecast. Indian tsunami warning system. After occurrence of the devastating this in 2004 of magnitude 9.38 at Sumatra earthquake, he contributed significantly by providing the scientific in which the 250,000 humans' lives were dead. So he prepared a tsunami warning system, which has just completed in just 30 months. This is now assessed to be among the best tsunami warning system globally. So apart from scientific work, his work is for many, this is social and need-based like tsunami, earthquake, etc. He has published several papers, like he's published over more than 200 scientific papers in international reputed journals. He has authored 5 books and published by those. These books have been published by the reputed publisher like Spencer and edited about 21 volumes. One of his paper was adopted as a chapter. This is a great contribution in Open University UK textbook on the geophysics. His first book, Dams and Earthquake, published in 1976. So what a lot of experience. From 1976 onwards, he has a significant contribution till today. Professor Gupta completed the edited Encyclopedia of Solid Earth Geophysics. This has a monument, 1,500 pages of 2 volumes, testicle published by Springer is globally landmark. So he has having international, globally contributed in several fields in the key position with a very vast lead role. He has significant contribution in IU, GG, IC, SU, AGU, AU, GS, etc. Long time involvement in IU, GG as a president.
I think we should be enough.
No, sir, just it will be injustice to me if I do not clearly tell, because you have I have not seen such a speaker so far which having some vast experience since long. Okay, sir. It will be injustice to I will feel, sir. So he's a vice president. He has been a vice president and many executive committee members, chairing steering committee and chair hazard groups of ICSU, founder president of Asian Seismological Commissions, vice president and president, scientific and technical committees, member of AUG, publication, etc. Actually, he has been exposed to the many prime minister, past prime minister. I have seen his photograph with Indira Gandhi, Rajiv Gandhi, and also has been contributed in this thing to, with this thing Atal Bihari Vajpayee. So he's a very renowned person. So that's why I want to. It's my एक्चुअली मेरा जो मैं उनको इंट्रोड्यूस कर रहा हूँ, मैं सूरज के सामने दीपक दिखाने जैसी बात कर रहा हूँ, सर. He's having about awards, many awards. Like I am will just tell a few awards, sir. He is a key prestigious awards: Shanti Sarup Bhatnagar Awards, US Academy of Science for 100 years of International Geoscience Award, National Mineral Award from Government of India, CSI Technology Prize from Business Development Technology Marketing, second Outstanding Performance Award by in 11th this thing Festival of Indian Research Organization, several awards like Physical Science Award, Jawaharlal Nehru Visiting Fellowship in 2003, Professor B.C. Karukaran Fellow Award. He got Padam Shri in 2006, and Bruin Memorial, etc. Professor Navai Duma Memorial Award, Waldo E. Smith Medal Award. This is one of the prestigious awards in 2008. Professor Gupta is the first so far, one scientist from the developing world awarded a Waldo E. Smith Medal by American Geophysical Union. So he's a great personality. It's our pleasure that that I am introducing to him, and all the I feel that all the scientists who have joined it under MSc, BSc, and all different level will definitely be benefited by his speech. So I request him to inaugurate this event. And now over to Chintamani, please.
Thank
Please
you,
go ahead.
Mr. Jain, sir. It's now time to have the official virtual inauguration of the event. And we are very fortunate to have with us Padma Shri Professor Harsh Gupta sir. We are really fortunate, and I'm sure all students, faculties, and all the participants, they will really enjoy his talk, and there will be a lot for inspiration to take up the motivation of taking space sciences ahead in our country. With that, I invite Professor Harsh Gupta sir to officially inaugurate this event and to proceed with the inaugural talk.
A very good morning to all of you. I'm indeed very grateful for this opportunity, and thanks to Shri Jan for a very detailed introduction. I really appreciate the effort of PC Jabin Science College and Indian Space Industries Exhibitors in organizing this webinar series on challenges of opportunities for science studies in space sciences. So I think this is an extremely important step, because we need some guidance to be provided to youngsters. And one area where we are lacking is to get students interested in science and technology at a very early stage. Most students you will talk to, they would never say that you want to be a scientist or take up science as a career. So these kind of webinars provide an opportunity to share how science is fulfilling the need of everyone, and how exciting it is when you get a paper published in a good journal. And the biggest advantage of science is that when you write a paper, you are the first person to get the credit of it, and then your institution gets the credit, etc., etc. So literally, you are working for yourself, whatever research you are doing. So this kind of opportunity should be made aware. So I'm very happy that this webinar has been jointly organized by PC Jabin Science College and Indian Space Industries Exhibitors, and it's a pleasure to inaugurate the same. And once again, I thank you for this opportunity.
Thank you. Thank you very much, sir. Sir, you may, sir, now proceed with the inaugural talk.
Thank you very much. Thanks a lot. And I've chosen to talk about setting of the India's permanent station, Dakshin Gangotri in Antarctica. I must tell you that in my life, I have come across several challenges and several opportunities. But the kind of challenge and opportunity that was provided in 1983-84 in setting up the permanent base for India in Antarctica is unparalleled. Can I get my PPT, please? Can we go to the first slide?
Yeah,
Okay, we can go to the next one. So before I talk about this expedition, it is very important to get to know some fundamentals about Antarctica. With almost 14 million square kilometers, it is the 5th largest continent in the world. And it has a very thick ice sheet. The average thickness of the ice sheet is almost 1.8 kilometers. And we still don't know that how deep the ice goes. But the deepest estimated thickness is almost 5 kilometers. And this enormous ice sheet has depressed the continent by about 600 meters. This is also the highest continent in the world, with an average elevation of 2.5 kilometers. Now, it is a very big surprise that it is the driest continent also, with annual rainfall of only 10 centimeters. And there are places in the interior of Antarctica which haven't experienced rain for thousands of years. Next slide, please. You may also know that of all the fresh water on the Earth, 80% stored in the Antarctica. If this ice melts, the sea level will go up by 60 meters. And actually, very, very scary scenes are already being seen when we see that huge chunk of continental ice sheets are breaking down and coming. Only 2% of Antarctica has exposed rocks. Also, the world's lowest temperature ever of minus 88 degrees Celsius was recorded at Vostok in 1960. It also has a magnetic and geographic North Poles. There is 24-hour summer time daylight and 24-hour darkness in the winters. Next one. The name Antarctica was coined much before it was found. Because Antarctica is opposite of Arctic. Arctic is an ocean surrounded by continents. Antarctica is a continent surrounded by oceans. We have penguins in Antarctica and we have polar bears in Arctic. And existence of Antarctica was hypothesized almost 1800 years ago, just thinking that there should be a continent south, just opposite of Arctic. Next one. So people started going around Antarctica. Captain James Cook and circumnavigated in 1770s. James Ferrell discovered the Antarctic Peninsula, and early expeditions were basically for sealing and whaling. People will go with huge ships and catch hold of shipload of sails and wheels. Next one. Global attention was drawn to Antarctica with the International Geophysical Year during 1957-58. And it was also realized that Antarctica is not to be exploited. So all the Antarctic territorial claims were put to shelf, and Antarctic Treaty was signed on 1st of December in 1959 by 12 countries. Next one. Then also, there is a lot of commercial interest in Antarctica. The minerals are there, the oil and gas reserves are there. The largest coal deposit around the 2,500 kilometer long trans-Antarctic mountains is there. Antarctica, fortunately, is not populated. The summer population is about 6,000. In winters, it's come down to 4,500. And there are about 70 wintering stations which are populated during the winters. Next. Now, India got interested for several reasons. You see, India was a part of a huge continent known as Gondwanaland, which broke away some 200 million years ago. And various constituents of it, Antarctica, India, Africa, Australia, Arabian Peninsula, all of them moved in different directions. India collided with Eurasia some 40 to 50 million years ago. And that is what created the mighty Himalaya. Also, it is very interesting to know that the east coast of Antarctica was juxtaposed with India. Indian Ocean separates India and Antarctica. So the Antarctic weather controls the Indian Ocean weather, and Indian Ocean weather controls the Indian weather. So for a long-term forecast, it is very important to understand what happens in Antarctica, what is the effect of that on Indian Ocean, and what is the effect of Indian Ocean on Indian continent. So these are some very important issues. Then comparative studies of genesis of mineral deposits is again very important. Next one. Next.
Yeah, sir, I am trying. Yes.
So India was to be a part of major decisions being made about Antarctica. And this need was felt in 1970s. And that resulted in the first expedition in 1981 led by Dr. Zahur Qasim. who was then the secretary of Department of Forests. And the second expedition went in 1982. Next one. And this is just a map which shows breaking up the Gondwana land, and you can see Eurasia, you can see Africa, South America, Antarctica, India, and Australia. So after the second expedition, next one, in 1983, there was a call for people to go to Antarctica, and the call was for submitting some science programs which you want to conduct there. So that was the time I was at Trivandrum at the Center for Science Studies. Until then, not much was known about the seismic structure and seismicity of Antarctica. So I made a proposal to set up a 5-station network in Antarctica. In the early 80s, everything had to be manual. There were no digital transmission, etc., etc. So this proposal was made to Department of Ocean Development. And after a month, I was called for a presentation. So I went for the presentation. There were another 15 scientists, other scientists who had also made similar proposals. And we made our presentation one by one. Dr. Qasim chaired the session. And they said that they like my presentation a lot. But the aim this time is to set up a permanent base. And it will not be possible to accommodate 5 individuals that I needed to man all these stations. Then they paused for a minute and said that, can you wait for some time for us? We'll call you and talk to you later. So when all the presentations were over, I was called again. And I went in, and they said that although we are not able to support your proposal to operate seismic station in Antarctica, we'll be very happy if you consider to be the leader of the 3rd expedition to Antarctica. So this was something which came as a surprise to me. And then I said, why me? So Dr. Qasim said that you are just 40 years of age and you are already director of a full-fledged laboratory. So that means you have established yourself scientifically. You are physically very robust, look in good health, and we know that you have been working in Himalaya and all that. So I said, please give me some time because I have to consult my own setup. So I called Mr. V. Ramchandran, who was the chief secretary and was looking up the Center for Science Studies in Trivandrum, because at that time Trivandrum was under the state government of Kerala. Of course, it was like a CSR laboratory. And Mr. V. Ramchandran was very happy. He said that you must consult your family. And he talked to Sri Karnataka, who was the chief minister at that time, and they were both happy. I talked to my wife and 2 daughters, and it took them some time to understand. But finally, I conveyed my concurrence to Dr. Qasim the same evening. He asked me to come to the office next day. That time, DOD was located in the South Block, a small office where about 15, 20 people worked. When I entered, everyone stood up. So I realized that they have already known that I'm going to lead the expedition. And those days, Prime Minister was not not too busy. And the then Prime Minister had taken a direct interest in Antarctica. So Dr. Qasim said that I need to introduce you to the Prime Minister. An appointment was sought in the afternoon, was available. So I went with Dr. Qasim, met the Prime Minister, and she spent almost 1 hour with us, asking some very fundamental questions, many of which I had no idea. So it was decided that I get back to her in about a week's time. That week I spent in DOD, and I tried to learn as much about Antarctica as possible. And I learned quite a bit from the Soviet Union and the British Antarctic Survey. And many questions were asked. And again, second time I went, and she again asked me many questions. And finally, she said, yes, done, please go ahead. So that's how I got involved into Antarctic program. And after that, a very hectic studies started. First thing was a medical checkup. Fortunately, I was quite strong and I got the medical clearance. Next important step was training of all the 80 odd members who were selected on different reasons. at Machoy Glacier to familiarize ourselves with what ice is, what snow is, because many of the participants had never been to a snow or ice-laden country or place. Since I was educated in Missouri, I was quite familiar with ice and snow. Anyway, that Machoy Glacier training was very important. It was spread into three groups, first, second, third, 30, about 25 in each. And I was in the central group so that I could talk to the people who were leaving after the first group and also talk to the third group people. So all that preparations went underway. Many important things were learned about Antarctica. Next one. And finally, we had hired a ship Finn Polaris from Finland. It was chartered to go to Antarctica. And on way from Finland to Goa, it had collected all the material for building the permanent base. It was to be a prefab base. You can see loading of a Mi-8 helicopter into the hold of the ship. You must have heard that on 8th of December, we had a Mi helicopter crash in which we lost General Rawat and many other senior colleagues. Now, one thing which I had learned, that when you load the whole of a ship, it should be loaded in a way that the things that you need first are on the top. So Major Nair was in charge of construction. He was from Corps of Engineers. I talked to him and I wanted to have the sequence of loading of the ship, which he had a faint idea, but not the exact idea. Now what happened, the Finn Polaris ship had arrived and Dr. Qasim took me to the ship, introduced me to the captain and said that from now onwards, whatever Dr. Gupta says has to be done, and that's the last word. So a lot of other participants had arrived and we were discussing the ways and means. And it was decided that the ship would sail on 1st of December 1983. And some very high dignitaries, including the governor of Goa, was invited to send us off. When I learned from Mr. Nair that we don't know the exact sequence of loading, next day I went to the ship with Mr. Nair and got the whole hold unloaded. And Dr. Qasim came and he was aghast to see that everything was out. He asked the captain, what has happened? He said, sir, you said Dr. Gupta is in charge, so he asked it to be unloaded. Imagine unloading of a 80 feet deep hold, which was carrying about 1,000 tons of building material. But then I explained it to Dr. Qasim and he saw the point. So in the process, our departure
It's 11 o'clock.
was delayed by 3 days. Instead of first, we started on 3rd of December 1983. Next slide. This is a picture of the ship. You can also see the oil barrels. We were also carrying 1,000 barrels of oil. This oil was carried that in case we succeed in setting up of our permanent base, we need something to energize, and the oil was to be used for it. I was also told very clearly by the Soviet and British friends that no one has set up a permanent base in Antarctica in one Antarctic summer. You see, Antarctic summer is from December to February. And if you succeed in doing it, you'll be the first to do it. But the chances of success are not more than 10 to 15%. So in case you do not succeed, don't get upset. So this was on the top of our mind. Another thing the Soviets had done is shown me a movie of a piston bully. A piston bully is a tracked vehicle which we use for moving on snow. So they showed me a movie that a tracked vehicle was kept on the fast ice. You see, Antarctica has shelf ice, which could be 400 to 500 meters thick. And in addition to that, the sea around Antarctica freezes during winters, and you get 1 to 1.5 meter thick layer of ice, which is called fast ice. And this fast ice is quite good. You can move, walk, and do anything over it, but it can have crevices, it can have breaks. So one has to be careful. So I was shown a movie where they placed a piston bully on fast ice, and it just sank, and they could not save the people who were sitting there. So those are all the things at the back of mind that all this care has to be taken. Next slide. So finally, we sailed off on 3rd of December 1983. It was a wonderful send-off. Next one. And we had a stop at Mauritius, a short stop, where we had by that time checked whether we have everything that we needed, and whatever was required was ordered and obtained. And another very important thing happened, that during this voyage, we kept on calculating the time given for each task to be accomplished. Now, we had a time window of 60 days because we realized that we reach Antarctica somewhere in the last week of December, and somewhere in the first week of March, we have to leave, depending upon the ice condition in the sea. So 60 clear days are available to us. Out of 60 clear days also, several days are lost due to whiteouts. What is whiteout? Whiteout is a situation when the wind blows, the ice particles get airborne, and the sunlight falls on them, and it is so glittering that even with thick sunglasses, you can't see anything. So those days you cannot walk. And then you have got the famous blizzards of Antarctica. When the blizzards are there, the speed reaches up to 150, 160 kilometers an hour. You can't even stand in that blizzard. So our aim was to cut down construction time of this station to 30 flat days. In the process, we cut down the reconnaissance from 1 week originally to 1 day or 1 afternoon, because we had aerial photographs, and I had selected a spot. And I said that I'll go with a piston bully and 4 or 5 people, look at it and then decide, because we cannot afford to spend a week's time in deciding where to build it. At around 60 degrees south, we located the first iceberg. This was a huge iceberg. And iceberg, this is approximately 4 or 5 meters in height. So this is only 10% what you see above the ice. So there will be another 90 meters below. Next one. And this is the fast ice, which we can see the ship has reached into fast ice area. And next one. And finally, we anchored here. And these are the fast ice. And we have to work on this fast ice, move on this fast ice to reach the station. So we had taken the Chetak helicopter. We had 2 Chetak helicopters, which are Edwards, and 2 Mi-8 huge helicopters. And we surveyed the area aerially. And then we took the piston bully and decided if the station will be built. Next one. Beautiful penguins. I must tell all my colleagues that no matter how much you read about Antarctica, when you reach there and see, it is unimaginable what we find there. The vast spread of ice, no horizon, no trees, nothing, no idea of distances. So it is really breathtaking. And you know, no one catches cold in Antarctica because there are no bacteria. So the injuries are there, but no one gets cold, cough, etc. in Antarctica, unless until you import it. Next slide. So these are the 2 main tents we had fixed on the fast ice. These tents can accommodate 2 persons. And this is the piston bully. So these tents were set up on, we reached there on 26th of March. These tents were fixed up, and we started operations. Next slide. And this is a Mi-8 helicopter in operation. And the modus operandus was that this helicopter will come and hover on the deck of the ship, and we will underslung the load, and then we'll start moving. Now, as you can see, that if this underslung load generates an oscillation, it could be hazardous for the aviation. And the pilot cannot see what is happening down below. So the fuselage of helicopter was cut open and a plexiglass window was fixed there. So through that plexiglass window, you can see what exactly is happening. And the flight engineer can keep on telling what is happening. So just on the third day, on 29th December, next slide, we had the helicopter crash. What happened? The helicopter did not gain adequate height. It started moving and the underslung load caught hold of the railing of the ship. It pulled the helicopter and the rotor blades of helicopter hit the crane of the ship and the helicopter crashed. Fortunately, I was on the deck at the time, so I launched an Eluard, a smaller helicopter, to pick these people. And they had broken open the plexiglass window and they came out of it. Now imagine if the plexiglass window was not there, they couldn't have come down, they would have just sunk with the helicopter. Also, I forgot to tell you that on way to Antarctica, the doctors told me that there are not adequate facilities, medical facilities on the ship. And they wanted a space to set up a good hospital on the ship because they were carrying everything that was to be put in the station. The same room was required by the scientists to deploy some of their equipment. And I decided to give that room to the doctors. And the scientists were very angry with me that you yourself being a scientist, you are not favoring us. I said, science is there, but more important is its mission. So you can see that these people are coming out. Next slide. And this is the Chetak helicopter which was sent to bring them up. It lowered the lift or the ladder they would catch hold of and come. In the meantime, the helicopter had drifted somehow 200 meters away from the ship. So one person caught hold of it, and as soon he was being lifted, the other person caught hold of his legs, and they both started moving to the ship. Halfway through the ship, first this person down below fell, and the second person also fell. We were again fortunate that the helicopter did not crash on the ship. Had it crashed on the ship, the whole ship would have been written off. Had it crashed on the fast ice, helicopter would have been written off. It crashed in the water, that's very lucky. And then it turned turtle. So when these people dropped, we had in the meantime also launched a rescue boat. Next one. So that rescue boat went and brought those people back to the ship, and the doctors had been alerted. There were 5 of them, and they were taken to the medical room. Now, this was such an important incident on 29th of December. I had to inform Dr. Qasim, so I came to the bridge of the ship. All the communications were from the bridge. We did not have the luxury of the communications that we have today. So on the bridge of the ship, when I was on the ship, half of our people were very upset. Many of them were crying because we did not know what would happen to these 5 people. So I came to the bridge of the ship and I called Dr. Qasim and I very briefly told him what had happened. He said, you have to inform the Prime Minister because she has personally taken an interest in all these expedition things. And I didn't have to wait for too long. Within 10 minutes, there was a call and the Prime Minister was on the line. She said, Harsh, is everyone safe? I said, ma'am, 5 of them have been exposed to water. Hypothermia may have been set up, but we are very hopeful of saving them. Our next question was, can you still do it? I was not prepared for this question, but we were so charged up. My instantaneous reply was that if I do not do it, I do not come back. This was heard loud and clear by everyone on the bridge. There was a long pause. And then she said, go ahead and do it. And the phone was off. Then Captain Chandna who used to fly Elwood, he said that I must go to the base camp and inform them, because otherwise different versions of what has happened will reach the people. So I went to the base camp where we had these tents and people were there, and there was a small hut in which we collected all the people, and I explained everything to them. And there was a loud cry, "We shall do it!" And that was a war cry, taken up by the officers and men of police, of army, all the scientists, everyone. Next one. And from that onwards, the work started on a very fast mode. Next slide. Here I'm showing you laying the foundation of the building. You see, since we are building on ice, you have to provide a raft foundation, a common raft foundation, so there is no differential settling of the different units. So the building area was 620 square meter. So you dug open 1.5 meter of the ice to put this raft foundation in place. Next one. And the building is being built on the foundation. This is a double-story structure, and there are 2 wings. These 2 wings are separated by a very small corridor, because fires are very common in Antarctica. And you don't want the whole thing to be blown up. So the idea is this, that if something mishap takes place, at least one wing will survive. And you can see people working on it. That was a time when I had to switch off generators at 10 p.m. in the evening, because it's daylight and people will not stop working. And there were many cold injuries reported. What happens that when you are in such an area, in such a cold place, you tend to dress up yourself. And when you are working, you can sweat because the heat generated due to your work. And after that, if you sit down, that sweat freezes, and then you can have the frost bites and things like that. So there were small little reports of frost bites, and anyone who reported a frost bite, I sent a gentleman to the ship to get a replacement. After a week, the frost bites were not reported anymore. Next slide. This is an aerial view of our station. As I told you, there are 2 blocks connected by a flimsy corridor. And you can see all the construction activity continuing all that. I must tell you, while all this was doing, the scientists were doing their job, and anyone who was free would help, give a helping hand. But all the scientific work was also continued simultaneously when this was happening. Next slide. There is a Russian station close to our station we were building, and one could go by helicopter. We visited them, and you can see me myself with the leader of that expedition. And you can see I have not worn thermals on my legs, which or everyone else, they are the 4 Indians they are wearing. And I purposely did not wear them to tell that it's not cold. Although at times I shivered, and then I'll just do spot running. Before going to Antarctica, I was running almost 10 kilometers every day to be able to take all the hard work necessary required. So when I told the captain or the leader of this expedition that this was, so he just laughed. He said, "Harsh, are you dreaming? Which has never happened." Next one. So by the end of January, the fast ice had all gone. And you can see this is the shelf ice. And the ship touched the shelf ice, and then transportation became easy, because earlier we were carrying everything by helicopter. Now the piston buoys could carry all that stuff. Next slide. There have been many occasions for me to hoist our national flag, but 26 January 1984 was my proudest moment when I was able to hoist our national flag in Antarctica. There were people from the ship, and people from the nearby German camp came. We had sent a helicopter to get them. From the Russian camp came. And they were astonished to see how much we had progressed on our station. And the Russian leader said, Harsh, this is unbelievable. Next slide. So he's a Russian leader, and exchange our meetings, etc., etc. Next slide. Another view, the station is getting closer to being completed, and it is dressing up a building 3 times. You construct it. Inside there is an asbestos lining put. Asbestos lining is put to make sure that it is heat and fire resistant. And outside we put a cladding of iron sheets to protect it against wind and other things. The station is also anchored so that it doesn't get airborne. Next slide. Views of the inside the station. This is our medical room. Next. One of the laboratory for measurements of all the properties of rocks, etc. Next. Another laboratory, chemical laboratory. Next. The communication room. Next. The toilets. I'm saying these are special toilets which mix up your waste, and then you have to collect it and destroy it. Next. And in between, we went to the Volthard Mountains, which are very high, and the wind is very strong. And the helicopter engine was not turned off, because for some reason, if it doesn't start again, you get stranded there and it will be difficult to get back. And you can see the wind speed, the flag is almost horizontal. So there were such exciting things happening during those months we were there. Next one. So finally, the station is ready. And we had lost many days in blizzards and everything, but by 24th of February, the station was ready. And the captain of the ship had told me that we must depart by 1st of March. Otherwise, there's a chance of getting ice locked. And then you stay for 9-10 months in that situation. The question was to make a decision to leave those people behind. And again, I asked Dr. Wasim that what should I do? And honestly, he said, Harsh, there's nothing I can tell you about it. It has to be your decision. If you feel those people can survive, leave them. If you have any doubt that something may happen, then you bring them back, because we cannot afford to lose anyone because of this kind of error. So I was in a dilemma. But to our good luck, on 25th of February, a huge blizzard hit us. And that time, almost 40 of us were on the station. And that blizzard touched the speeds of the maximum speeds that were ever recorded in that part of Antarctica. And we were there it lasted for 3 days. And the whole station, which was meant to house 12 only, we were 40 of us, we were sleeping here, there, and everywhere. In the night, it looked like a big dormitory. Next slide. So finally, I made a decision that I could leave the people behind, because the station survived that blizzard, and the engineers who were to be left behind were able to fix small little things. They were very competent people. We also did some philately work, stamping of the stamps, and this is the final meeting. Here is Colonel Sharma, who was the leader of the wintering, and these are all the people in that station. We were all holed up for 3 days. Next slide. So finally, we got them in, and Dakshin Gangotri was created, and we told them bye-bye on 1st of March. Parting them was, of course, very difficult, because we had grown very close to one another. And also, there was a big question mark that they are going to be by themselves for next 10 months. Because the 4th expedition will reach their end of December. So we are living in March. So March, April, May, June, July, August, 10 months, they have to be on their own. But they were very brave people, and they assured me that things are going to be fine. Next. On way back, we stopped again at Mauritius, and it was very warm welcome. The Prime Minister of the Mauritius, Jagannath, welcomed me. Next. And there was coverage all over Mauritian, the Antarctica continent with Gupta there. It was a very festive thing in Mauritius. And next one. This is my cabin where I used to write. Now, I must tell you that on way back, I found that several of my colleagues had cold injuries, which they did not report. And I said, sir, why didn't you report about it? He said, if we reported, you will send us back to the ship. We didn't want to do that. We wanted to be on the front line to do the work. So that kind of a commitment. Also, what had happened, that after that helicopter crash, within 1 hour, there was an inquiry set up by Air Force to find out the reasons of crash, etc., etc. I sent a fax to Prime Minister's office that if I get busy with the inquiry, no work would be carried out. And that inquiry was lifted. Next slide, please. So this is the total route we took. We went from Goa, went across. Here we did a lot of experimentation and then came back. We stopped at Mauritius on both ways. Next slide. There was a very wide coverage all over in all the magazines, as you can believe at that time. Next slide. And on 6th of June, 1984, as was conventional, we had a meeting in the Vigyan Bhavan. Everyone got there. We all exchanged our information, etc., etc. The Prime Minister was to come for half an hour's time. And the modus operandi was that for 10 minutes, she will see a video, which I'll show her about Antarctica. 10 minutes, she will have question answers, etc., with people mingle and leave in 30 minutes time. So we all go together. I showed the video that I had prepared. There was some little bit of auditing of it. It was done by Dr. Qasim. And she came at sharp time. And she mingled with everyone. I showed the video. And she continued with us for almost 2 hours, talking to all the people. We were all surprised that instead of half an hour, she spent 2 hours. And then we realized that 6 June 1984, Operation Blue Star was on. And probably she wanted to be away from her office at that time. So that's my influence. Next one. Then later, I must tell you that the next 10 months were very, very difficult for me, because I will keep on getting news from the station, something has gone wrong. Dr. Arunachalam was a scientific advisor to the government, to the defense minister at that time. Arunachalam I had known from Hyderabad, and he will call me almost every week because he was worried. He will think about some complaints coming, something happened, this happened, that happened, that Gangoti. So for full those 10 months, I was on tenterhook that if something happens, I wouldn't be able to pardon myself. Finally, the 4th expedition reached there, end of December 1984, and I got a message that everyone is hale and hearty. Only caution was that they did not mix up with the 12 people in Antarctica immediately, because they are carrying a lot of viruses with them on the ship. And those people are totally free of virus. So there is some 10, 12 days you remain separate so that your own virus die down, then they met. I made a presentation to the then next Prime Minister, because Indira Gandhi was assassinated, of the wintering station. And while leaving, he took me by my arm and said, "What happened? Why did the helicopter crash?" So I said, "Sir, it's the circumstances or maybe a pilot's error, because it should have reached adequate height. And he smiled, he said, I nailed. Next one. Now, when I look back, what made this happen? You see, excellent preparatory interactions, unloading and reloading of the whole of the ship. That's the most important thing. Then plexiglass window in the fuselage of Mi-8. If it was not there, what would happen? Allotment of 2 rooms to ship for medical facilities. If we didn't have that medical hospital, we couldn't have saved them. Optical crash, helicopter crash and commitment, if I do not complete, I do not come back, became a war cry and glued us all to have completed the job. It was difficult to take a person out, to take rest. They were all working so strongly. Then that lifting of the inquiry of the helicopter crash. A very strong blizzard in the last week of February at Dakshin Monthly, which stood. Colleagues have cold injuries and not reporting. And basically hard completed work of 81 members, support from Finn Polar's crew, and total government of India support. And look at this station, built over 620 square meter raft foundation with living space for 12 people. Generators, laboratories, melt tank, heating, medical room, gymnasium, library, etc., done in 30 working days. Can you do it in Ahmedabad in 30 days? Not possible. So these are the kind of circumstances which happen. And next one. And of course, there was a scam brought out on Dakshin Gangotri. This is how the Dakshin Gangotri looked after 4 months. 4 years, 1988, half covered by ice. Next one. Then in 2001, I came to Delhi as Secretary Department of Ocean Development, and I realized that we did not have a cabinet clearance for our Antarctica program. So I made a proposal, and it came to the cabinet committee. I was called for it, and Jaswant Sinha asked me that you have just joined as secretary. Why are you bothered about this clearance? So then I told him that I may have joined as secretary duty just now, but I am involved with Antarctica from 1983. So they all listened to the story that I had to tell them. And then they cleared setting up of all the stations. And they also charged DOD to set up a new modern station. Next one. This is a view of Dakshin Gangotri. It is completely buried now. And a new station has been built, which was Mathri in 1988. Next one. In 2005, it was realized that no minister had ever visited Antarctica, although we are working there from 1981 onwards. So Sri Kapil Sibal came, and we went to South Africa, and from Cape Town we took a flight in a Russian plane, which has no windows, etc. Landed in Antarctica. Next. And Kapil Sibal spent time in Maitri. Was very happy to see what was happening. Next slide. And then we visited where the Dakshin Gangotri was once upon a time. So I got very emotional. I'm lying down on Dakshin Gangotri in 2005 because it's totally buried in the ice. Next one. This is Ravichandran, our current secretary MOES. He was also very deeply involved with the Antarctic program and visited Antarctica several times. Next one. These are the auroras which you see, and it's really amazing what you can. Also so beautiful. Next one. Total solar eclipse observed in Antarctica. Next one. Now this is the latest station which has been built in Antarctica. This is our 3rd station, and we are at the top of the world as far as Antarctic sciences are concerned. Next one. A book was written on Dakshin Gangotri, Building Dakshin, a Miracle. And this was sort of released at the India International Center on 15th of December. Next one. And I made some presentation. This is Mr. Vora, ex-governor of Jammu and Kashmir. Next. And I really enjoyed because after a long time, I made a physical presentation. The hall was full. Next one. Now, I got a feedback from K. Jiva, Krishna Swami Jiva, Technical Officer for Indian Institute of Geomagnetism, Mumbai, member of 11th, 19th. And so he was there for 6 years. And then he wrote that in 1992, when we lost almost all the new generators in a fire accident and were surviving with 2 old generators on the return of the comfortable season, we could get one alternator from DG and some edible oil to complete our remaining part. So he called me and he told me that under these situations, they walked over where Dakshin Gangotri was there. And they were able to dig open, dig 4 or 5 meters and go into Dakshin Gangotri and collect some edible oil and a generator, which helped them in surviving. He further adds, very heartening to imagine your state of mind when you left 12 members team behind for a whole winter. Even now we bid tearful farewell to the members left behind. Now we have every facility and wealth of experience. I'm sure that it was a very difficult decision, etc., etc. Next one. This book is now available at Amazon also. Next. I would like to thank Dr. Mathur for inviting me to give this talk, and many people, all the members of Flood Expedition, Department of Ocean Development, Ministry of Sciences, Twin Polaris crew, which made the miracle happen. And also, I would like to thank some of the people who have been helping me in all possible ways, especially Anjali Krishna, Professor Subbarao, Stephen Ford, M. Ravichandran, Rajan, and B.R. Krishna, who helped me in putting this all stuff together. Next slide. Thank you very much. Thanks a lot.
Thank you very much, sir, for such an enlightening talk. And I'm really sure the journey which started from 1983 through the regimes of 3 prime ministers, it clearly shows how the India's interests are in developing the science in this country. And I'm sure this talk must have enlightened a lot of youngsters and students who are attending right now your talk. Sir, we are really fortunate to have your talk. So with this, the forum is open for question and answer sessions. So if there are any questions, participants can put them in the chat box and we'll take them. We'll take them few selected questions.
Can I ask a question?
Yes, sir. Please go ahead.
Dr. Harsh Gupta, this was a very exciting and interesting story that you have told about how the Gangotri, Dakshin Gangotri was established. I would be very interested if you have that first movie available, which you showed to Prime Minister Indira Gandhi at that time. If you can share that with the audience here, will be great.
Okay, that was done way back in 1984, and I'll have to dig for it. And that time, the Doordarshan did everything. Anyway, I'll try to look for it. Sure.
Thank you.
Any other questions? So as other questions may come, sir, I would like to ask a question.
Yes.
So since 1983 till now, if you could just throw some light on the kind of scientific work has been carried out through our scientific base in Antarctica.
Okay. there is a lot of scientific work which has been conducted. And basically, it is a lot to do with the long-term weather forecast. So observations in Antarctica are constantly being put into the total network of observations. Then other areas are, we have learned a lot in Antarctica that what happens in extreme cold conditions. Because it's much easier to experiment things in Antarctica than to go to similar environment in Himalaya or somewhere else. Then we have also done quite a bit of work on mapping of the entire Dakshin Gangotri area, Shimachara glaciers, and juxtaposed with India, and learned a lot about avalanches, how they happen, what happens to them. And among all the microbes discovered in Antarctica, 60% have been discovered by Indian biologists, more than 120 microbes. And a lot of research is in progress at how these microbes can be used. So there are a variety of studies. I did not focus in my talk on the scientific aspect because the main aim was construction of the Dakshin Gangotri. But there is a 300-page scientific report which gives work done by the 16 scientists who had gone on various aspects, which is on a continuous basis. This has also made it possible later on that now Ministry of Earth Sciences looks after Antarctica and Arctic also, North and South Pole. And then the third place is the Himalaya. So they are doing a comparative study of all the ice and avalanche and other related issues. So it has all been very, very useful. And above all, it has provided us a base in the international scientific community on Antarctica. We are member of Antarctic Treaty. So these are all very significant achievements because of Dakshin Gangotri and the work that has been carried out.
Thank you, sir. I have one question from YouTube viewer, Mr. Srinivas Lakshman. He's a journalist for Times of India. His question is, what are India's future plans in Antarctica?
Well, I'm not exactly aware of exact plans because the plans keep on developing. I'm not in touch with them. But Bharti, the new station that we have set up, it is an all-weather, wonderful station. And there are a lot of new experiments which are being conducted at Bharti.
Okay, thank you. Are there any other questions by the audience? Any questions from students of Basic Jabin College?
Can I ask a question, please?
Yes, please go ahead.
Very nice lecture, sir. Harsha Gupta ji. Very nice and more motivating lecture. Sir, my question is, we had very rich experience in constructing the stations there. How these experiences of building stations in the extreme weather are useful either for Himalayas region or for moon mission type of things, where in future some stations can be built there?
Thank you very much for a very important question. You see, building of a station totally depends upon the surface on your building. And here this station was built on ice shelf where there is no rock below it. Whereas when we go to Himalaya or we go to moon, the surfaces are different. So this experience of building Dakshin Gangotri per se only is an experience that how you plan your work, so that whether you are building on moon or you're building in Himalaya, if there's a time limit, time constraint, then how you plan it and think of kind of emergencies, the kind of controversies, the kind of difficulties you'll get. So basically is a lesson in planning and forward looking. So for example, originally the plan that I had was for 60 days, which was cut down to 30 days, which was further, we cut down that reconnaissance cannot take 7 days. And that's why we were able to complete this station in by 24th or 25th of February. And then luck plays an important part. I say luck, one after other. If I did not have that helicopter, plexiglass window, those people could not have come back. If I did not have that hospital which was created where there were people placed, they would have died. If the blizzard did not hit us on 25th of February, I would not have dared to leave those people behind. So I think it is a mixture of, or I think there's also saying that harder you work, the luckier you become. So probably all of us worked very hard and the luck favored us. So it is a mixture of, and then cooperation, the kind of committed work of all the people, the Fin Polaris people, the building squad and Major Nair and everyone else. That's marvelous. I think I've been around for quite some time, but those 4 months were really precious.
Thank you, sir. Thank you very much.
Are there any other questions? Sir, may I request, so what will be your message to youngsters? A lot of students are attending the talk, especially from JC Jabin College and there are participants. What will be your message to youngsters and science students of this country? How to take ahead the science?
Well, I can only tell and encourage people to take science or technology as a career. And the challenges that you come in science and technology and the combined challenges are immense, and it makes your life worth living. Otherwise, we all live and then go away. So science and technology provides a basis of leaving a mark behind. So I very strongly urge, you see, one of the problems we have that geology per se is not taught as a subject. You learn about physics, chemistry, mathematics, everything as a high school student, but not geology. So the people who stay over to geology, like me, are just by chance. And the reason I went to geophysics was my elder brother, who had joined Oil and Natural Gas Commission. He had graduated from IIT Kharagpur. He was a mechanical engineer. He joined ONGC. And he thought there was a dearth of geophysicists in India. So he asked me, Harsh, why don't you take up geophysics? And I took it up. But that kind of a guidance, and I'm so happy that he told me to become a geophysicist, because I would not change a day of my life what it has been. And it has been very exciting. Even today, I'm excited with so many things. I'm totally busy even now. So what I'm trying to tell, that the best part with being a scientist that you never retire. You continue to work. You continue to research, you continue to write and enjoy it. Because unless until you enjoy your work, and anyone who joins for science for the sake of a service should not join. It has to be it has to be your hobby. Doing science, doing work becomes your hobby, it becomes your second nature. And as a musician, you don't ask a musician, sir, you are 60 years old, when are you retiring? You didn't ask this to any singer, sir, you are 60 years old, when are you retiring? So similarly, if science becomes your hobby, you don't retire. You are always alive, you are always young. And same is true with technology also. New technologies, what is happening? I saw a wonderful video just gave you yesterday, 2030. No petrol vehicles, no vehicles running on diesel, all electrical vehicles. What happens to all the stores which dispense oil and this and that? All that. It's totally unimaginable. And that is imagined now by scientists, that what the solution could be in 2030. And I would not be surprised if it really happens. I was, did you think 20 years ago, the way we are talking on this would be possible? All the gifts of science and technology.
Thank you. Thank you very much, sir, for such an inspiring talk. With that, I would request Mathur sir to add. Mathur sir, are you there?
Yes. Yeah. Thank you, Gupta ji, for a very nice and informative talk. I think the students, those who are attending this particular webinar, must have been benefited with your talk, and I also could get a chance to learn a lot of things from this presentation. I know when I was in job, that time our Mr. S.S. Waldia and team, they went and established a SATCOM station, Earth station there, where ECIL Hyderabad, they installed one antenna, and it was all total ice. On that ice they made a special foundation. It was very difficult task which ECIL did in establishing that satellite communication earth station. And um, uh, really I am thankful that you spared your time and to address these students, and hopefully we will have more interaction in future. I would also like to thank Mr. Sitaram also, who in fact in touch with me in last many years, and he basically got me introduced with Dr. Gupta.
Is
Thank
he
you, sir.
around, Sitaram?
He is there, sir. He was there. Yes, Sitaram, are you there? He was attending his morning also. I talked to him. Yes, Chintamani, if there is no question, we'll have to have a photograph on the screen with our chief guest.
Yes.
Don't forget that.
So if I could request the technical staff to have the gallery view for all the participants, so that we can go for the screenshot.
All participants should switch on their video.
I request all the participants to switch on their video for a group photo.
Sir,
Still,
please switch on the camera.
Still, I can see that many have not started their video camera.
It is over. Jain Sahab, I think you are also taking.
अभी मैं ऑडिबल हूँ क्या? Now I am audible.
Yes, very clear voice.
पुराना टेक्निक restart the laptop, then I utilized it. Okay. Sorry for that morning problem.
Thank you very much. And proceed with the vote of thanks, Mathur sir.
Yes.
Again, I thank our today's chief guest, Padma Shri Professor Harsh Gupta sir, for such an inspiring talk. And I'm sure all the participants, especially students, and even I had goosebumps while listening to his talk. The way Indian science has taken a journey, setting up the scientific base in Antarctica, starting from 1983, and I'm sure even in the future we'll be having more such endeavors. And it was we were really fortunate to listen to a legend who has contributed to this project of India's setting up India's scientific base in Antarctica. And with that, I thank the main organizer, Professor A.C. Mathur. He is a founder of Indian Space Industries Exhibitors, and who has been, as our speaker rightly said today, that there is no retirement for a scientist, and he is really taking the lead to organize such events to inspire students, youngsters, researchers all over the nation to come forward and contribute to the science and technology of this country. And I also thank his very energetic colleagues, Professor V.K. Jain, Professor Bharat Mehta, and all the other colleagues from Space Application Center ISRO and other retired scientists and existing scientists from ISRO. It's a great encouragement to all youngsters and students to be a part of this event. And with that, I also thank JC, the college, and the principal who have taken interest in organizing this event, especially Professor Veena, who actually had contacted Professor A.C. Mathur, and that is how we started planning this event, I think, since a month ago. And though we had very short time, but very good efforts have been taken on the behalf of the college to conduct this event. And I'm sure all the students of the college, they are enjoying this event, and they will also enjoy all the lectures by all the experts associated with ISRO and other organizations. With that, I'll conclude my vote of thanks. Thank you very much, sir.
Thank you.
Namaskar, sir. Chintamani, you can have a break now before going for the next session.
Okay.
Yeah, Prabhudas, I could see you now. How are you? Welcome.
Now I am getting well day by day.
Okay. Where are you now? Pune or Ahmedabad?
Ahmedabad.
Ahmedabad.
Improving day by day.
Yeah. Good to see you.
Scientist never retires.
या ठक्कर साहब का भी एक लेक्चर पेंडिंग है, अभी करेंगे किसी दिन शुभ मुहूर्त में. चलिए, तो अभी थोड़ा ब्रेक है जैन साहब, शायद 10 मिनट का,
Sure.
बिफोर द नेक्स्ट सेशन स्टार्ट्स.
Okay.
वो ज्यादा ट्राई कर देते थे उसको। तो कहा की तरह उनको जगा दो।
हाँ हाँ
क्लास में सो जाता है, जगा दो।
हाँ ठीक है। ओके त्रिवेदी जी, हाँ सेशन शुरू हो रहा है। हाँ जी, यू आर वेलकम। नमस्कार।
Sir, shall we start?
It's up to you.
Okay, fine. Welcome for the next session of today's event. And we have Professor Hariom Watts, who will be talking about opportunities for space sciences for science students. And before he proceeds with his talk, I invite Head of the Department of Physics, PC Jabin Science College, to officially introduce the session speaker.
Good afternoon to all the delegates and resource persons. I, Dr. P.R. Jirga, Head of the Department of Physics, would like to give the brief introduction about today's session. There is Dr. Hariom Watts, who is going to deliver a talk on the applications, challenges, and opportunities in space science. He is an ex-senior scientist, Physical Research Laboratory, Ahmedabad. He is a founder director of the Space Education and Research Foundation, Ahmedabad. He was born in a village named Kalina, that is of Meerut of India. That is, he has completed his MSc Physics from Meerut University. And he has joined the Physical Research Laboratory, that is the PRL, that is for his research work in the year 1970. And he has earned his PhD degree from Gujarat University for his work on upper atmosphere. And to his credit, he has published 120 research publications in the reputed journals. And again, to his credit, he has guided 6 scholars for PhD. And there is worked on research programs in several centers. That is namely, there is the USA, Diego, USA, KSRC, Japan, and INPE, Brazil. And he has given there is 265 talks. And again, another feather for him, there is another credit for him. He has translated 8 space science, there is the comic books in Hindi. There is and he has awarded INSA, there is the Indira Gandhi Prize for popularization of science in 2014. And he has visited several countries of Asia and Pacific region. For example, Bhutan, Nepal, Mongolia, Uzbekistan, there is Malaysia, Indonesia, Serbia, and Vietnam, that is etc. And with this brief introduction, I'm going to present before you, there is a great personality, a great scientist, there is for today's talk, there is Hariom Watts, sir. There is welcome, sir.
Thank you very much for a very nice introduction. And I, at the outset, would like to thank the organizers, especially Dr. Anil Mathur and all his colleagues, to have given me this opportunity to share with all of you some of the applications, opportunities, and challenges of space science today. So maybe I will share my PPT with you, and then we can start from there on. Okay, here is my PPT. Okay, so this is, I think my PPT is visible to all of you. And I recently, as in my introduction was said, that I work for this Space Education and Research Foundation at Ahmedabad. This is a foundation which is basically a virtual foundation. Most of the work is being done online, and there is a website for this whose address is given below here. And we have conducted several webinars, I think 22 webinars consisting of 108 lectures by senior scientists from PRL, universities, ISRO, and many organizations in the country. Some, I think 34 scientists have contributed to those talks. And all those talks are given, are available for everyone to use, to look at, learn, and use them on this website. I also have 2 email addresses listed here. And if there are any questions by anybody now or later, you are most welcome to contact me. And if I know the answer, I will certainly give that, or else I will try to get answer from many of my colleagues, especially related to astronomy and space science, about which I probably know some. So we'll get back to you. So with this, what I plan to share with you is, first, before I start talking about the space science, I will share with you some of the information which may be useful to several of you or most of you, including even children at the age of maybe 12, 15 or 13 onwards. And they are also useful even for researchers. And these are the 8 comic books which were originally created and published from Japan, and then later translated by scientists of Japan and NASA in English. And then they said that they can be translated in other international languages. And I opted to translate those books in Hindi, and they are all available on the website, on their website. And today these books are available in, I think, 12, 13 international languages, including several European language. So you can click on these. In fact, my PPT, I have sent my PPT to Dr. Anil Mathur, AC Mathur. So if you wish, you can get this PPT. And on each of these, if you click, you get to the books which you can read in Hindi or English, as the case may be. And they are very interesting books. While translating these books in Hindi, I myself learned several new things which I had not known before. Similarly, on 11th August 2020, I gave a talk in Science City of Ahmedabad, and that was about Vikram, father of India's space program. And the recording was not very good at that time, but this video is also available on this click on their website. I also wrote a interesting, simple book called Shooting Stars, which is based on the questions and answers, the type of questions that were asked, what shooting stars are and why and when they come and all that. So in a very simple manner, from the point of view of children, these answers are given in that book, and that also is available on the website. By clicking here, you can see those. Now, we start with the application of space science. And I'm sure all of you will agree with me that space science today is used by almost each and every one of us. We use this for information, we use this for communication, we use this for education, we use this for predictions of weather, wherever in world over you want to learn what is the temperature, what is the kind of temperature it's likely to be in next 10 days, 20 days, 30 days, or even a year or year after that. So all that information today is available through internet and through in a very, very simple manner to almost everyone. Even the smartphone gives all these information. And the example of education, as Dr. Harsh Gupta in his talk mentioned, that today you are able to hear him or me or all these speakers that will follow in this conference, that you are at a very far distance from me, and I'm sitting in my home and able to talk. This is all the application of space science and technology that we have today. So the space science has a tremendous application in our day-to-day life now. Traditionally, if I would say that the space science program that we have in India today, which is very, very proud program and very accomplished program of India, began from this institute called Physical Research Laboratory, which was established by Vikram Sarabhai, and has been, so this is called the kernel of space science in India. And of course, today the program is so large that this institute is a very small component of the Department of Space. And this institute or the laboratory has 3 more campuses, one at Mount Abu in Rajasthan, where there is a 1.2 meter optical and infrared telescope, which is used for the study of celestial objects. And in fact, there is a plan for establishing there in a much larger, I think, 2.5 meter optical and infrared telescope very soon. Another interesting center of this laboratory is at Udaipur in Rajasthan, where there is a lake called Fateh Sagar Lake. And in this lake, there are some islands. One of the island was taken, and on that, there are 3 telescopes existing, and they study the sun. Some part of solar research I will explain in the later part of my talk, because I also have done some solar research work. And there is a third center, which is in Ahmedabad itself, in the periphery of Ahmedabad, called Thaltej Campus of Physical Research Laboratory, where there is this has mainly the astronomy group and also the planetary exploration program, a very large program where they build payloads and develop programs for Chandrayaan and Mars mission, etc. And also many other space programs, including AstroSat. The tremendous work has been done there, and it's going on. So this was one of the very early space research lab. Today, the space research, as you all know, is done in many ISRO centers, Indian Institute of Science, Indian Institute of Astrophysics at Bangalore. These three, Indian Institute of Sciences, Indian Institute of Astrophysics, and Raman Research Institute are in Bangalore. And a lot of astronomy and space science work is being carried out there. There is an institute in Bombay called Indian Institute of Geomagnetism at Mumbai. And there is a National Physical Laboratory at New Delhi. Many of the CSR labs also not directly work on the space programs, but related programs or related technologies which are used in a space program are also being done. Many universities in India are now doing very good work. Many space research programs are conducted by the funds from UGC, DST, and ISRO there. One of the best way to learn or sort of get introduced to the space program in these centers or several other centers is a summer training program. This summer training program is especially for MSc first year students that after giving the exam of MSc first year, you apply to any of these centers and go there. They select, they also give some sort of honorarium and expenses to travel to that. And you can go there. And due to Corona, I think in past 2 years it was stopped, but I think now or soon it will start. So I'm sure some of you or all of you should make use of that. So the summer training program, you are assigned with a scientist or engineer and you work with him or her and learn and also interact with other scientists, interact with the exciting students that come from various universities and institutes. So it's a very good program, especially for MSc first year students. And second year, those who are in MSc final year, for them, there is some 10 of these centers have a common test program called JEST, and you appear there, and based on your performance in that, you get selected and go to research programs in any of these centers. Each of these centers also conduct their own tests, and they also advertise in the newspaper to say that those who have qualified NET can come directly for the interview, and on the basis of interview and the NET qualification, they can also be selected as research scholars. So that's how you enter into these institutes for doing space science and astronomy. And some of the there is also a possibility for even BSc students to join, some very, very interesting or those who have sort of very keen to learn about space science. Even BSc students also are sometimes taken for the summer training program. And all these centers also have what is called Science Day celebration in the month of February every year. And there they select few the toppers, the most brilliant students, and they give them a scholarship. They also tell them to come there during their vacation time and interact with the scientists during the vacation and learn and get into the programs. So, and today there are also many sort of startups have started working for space science programs, but most of them are not really for space science, but they are mostly for developing payloads, developing rockets, developing satellites, and or the parts of the satellite called payloads, etc. And space science programs are still in the institutes and universities. So this is in nutshell the opportunities that you have in India about space programs and astronomy. Now let me give you a very simple sort of introduction to what about the vastness of space. See, you all know that our Earth has a diameter of about 13,000 kilometers. It's very large. If we don't see the entire Earth from anywhere. We have to go to great distances, like from the satellites, you can see Earth like this. But our solar system, which consists of sun and all the 8 planets and several dwarf planets and comets and asteroid belt and all that, is our solar system, which is many orders of magnitude bigger than the Earth. The diameter is mentioned here, which is very large. But this is not very large when you compare it with our own galaxy, the Milky Way galaxy or the Akash Ganga. This is the type of Akash Ganga, Milky Way that we have. This is artist's view, and our solar system is like a point in one of its arms. The galaxy itself is as wide as 100,000 light years, which means if the light starts traveling from here, it will take 100,000 years to reach this point. That is the dimension of Milky Way, which is extremely large. And 1 light year is about 10 trillion kilometers. It's very, very huge distance. But in terms of the Brahmand or the universe, our galaxy also is also a point. There are several galaxies put together. They make what is called galactic, a cluster of galaxies, and there are large number of such clusters in the space. So the space as such is very, 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 very large. And today, many scientists in India and world over have studied several celestial objects in very, very great details. So now let me bring you to the study of our own sun, where I also have learned something and done some work. This is called the astrophysical laboratory, because this is the most studied object in the entire universe, because it's close to us and it's so bright. It gives emission in the entire electromagnetic spectrum, starting from very low radio emission to as high as X-rays, gamma rays, and ultraviolet, and even particles. So all that come from the sun. And the sun has a core which produces, where there is a fusion reaction and produces a vast amount of energy, which then gets transmitted outward through this radiative zone, and then the energy is transferred to convective zone. The convective zone has cells there. In this part, the radiation comes by going from one particle to the other particle and so on. So it's by the radiative process. And this is where the convection takes place. The energy, the heat is taken from here and come out in the photosphere, and the surface becomes hot. And we see that is what we see, the photosphere of the sun, which is the major energy source for our entire solar system. We get any energy that we have here, you can relate it to the solar energy. It is all in some sense or the other produced by the sun that we have. And not only us, all the planets, all the objects that are there in the solar system. And photosphere is at a temperature of about 5,000–6,000 degree Kelvin. And this is the coldest region of the sun, because the temperature inside also increases to very large amount. And then the outer layers like chromosphere, transition region, and corona, these are also hotter than the photosphere. The outer corona is very vast, and has a temperature almost as much as the temperature in the core, very high temperature, but the density is very small. And on the photosphere, there are spots which we call sunspots. And these sunspots have very interesting features, and people have studied these in very great detail. So this is in nutshell the sun as we have today. And a lot of studies related to this have been carried out. One of the things that I must mention is that the sunspots or the amount of energy that you get from the sun is, though to us it appears sort of constant, that sun is uniform every day. Please mute yourself. But this energy is variable. It varies. Like here, several pictures are shown of X-ray image of the sun. As I mentioned, the sun emits from radio to all in the entire electromagnetic spectrum. So this is the X-ray image of the time, say 1991, when it was solar maximum year. The number of sunspots were very large. That is called solar maximum. And gradually, every year by year, every 6-month images are shown here, and you can clearly see that the intensity from these images as a function of time gets reduced. And when you come to 1995, which is solar minimum, the X-ray emission is sufficiently smaller, weaker than what it was during solar maximum. So this is the half solar cycle. After this, again, the intensity of X-ray emission will gradually increase and reach as much as this. So this is called one solar. This is descending phase of solar cycle 22. The cycles are also numbered. They were started at one point of time, and from there on, these are given number. Right now, we are in solar cycle 25. So, so these are about 11-year cycles that we observe. And you can see these even more clearly in these two images here. This is on day 1. I forgot the date of this, but you see that it has spots here, it has spots here, there are spots here, and some spots here. Let me see if I can get the cursor. Pointer. Yeah, pointer is here. Yeah, so this is one spot, and this is another group of spots. There is a spot here, and after 4 days image, you have the sun's image, and you see that this spot has moved inward. This spot, which was this, also has moved to eastward, and this spot, which was almost at the limb, is no more there. It has gone behind the sun. So this indicates that the sun is not stationary. It moves around its own axis, like our Earth moves around its axis, and that's how we have day and night. So similarly, sun also does the same thing. But the motion of sun around its axis is rather slow. It takes about 25 days or around that to take one rotation around its own axis. This is an example of 1st December 2020, an extreme ultraviolet image of the sun, where you can there are several features, but I have put here A, B, C on these 3 features. And after 3 days, on 4th day, you can see that they all have drifted towards east. So this clearly indicates that the sun is not a stationary object as we see in the sky. And you can see it even more clearly in this small movie that I tried to create. Okay. So these are basically daily images of extreme ultraviolet on the wavelength of 304 nanometer of, I think we can see it once more. Oh, sorry. Oops. Oops. I think I should be. Oh, this is not showing it again. But anyway, so you know that the features are rotating. Let me go to one side before and see whether now I think it will come. Yeah. So these are daily images, and you can see all features are moving. So using such images and emission from the sun, we tried to study the rotation of the sun at several wavelengths, including radio wavelength. One observation of radio wavelength here, these are the wavelength in megahertz, starting from around 1000 megahertz to as much as more than the 8,000 megahertz, very high radio frequency. And two type of analysis we have done. One is called the fractal analysis, which sort of gives you at the emission at which you can see the rotational property very clearly. And if the fractal dimension is, say, around 1, that means it is a regular series. So you see that the intensity at that wavelength will have a periodic variation. And if the fractal dimension is close to 2, then it is totally random. So at high frequencies, you see that mostly it is in these colors. This color code indicate the fractal dimension. So the blue is 1.1. It's very close to 1. So blue color is mostly seen here, blue and green. So these wavelengths are good to calculate the rotational property of the sun, whereas these wavelengths are not very good. Sometimes they, like in these years, you can calculate, but these years it is difficult. And similar analysis also was done for UV, extreme ultraviolet images, X-ray images. And please mute yourself. Please, participants, please mute yourself. Okay. So they also give the fractal dimension around this value, like in the green and blue region, which means that you can calculate the rotation period of the sun at that wavelength. And because these wavelength, the emission from the sun in radio comes from corona, extreme ultraviolet comes from transition region and part of corona, a different part of corona. Optical signal comes from sun, the photosphere, which we see, and there are emission from chromosphere. So different wavelength X-rays also come from inner corona of the sun. So by analyzing different type of images, you can calculate the solar emission or rotational property of the sun at different heights from the sun. And here is one example where X-ray images of the sun for the period of 1992 to 1995 were analyzed, and the rotation period was obtained. And here in this graph, the solar latitude is mentioned here. This is solar equator, and this is towards the north pole of the sun. This is toward the south pole of the sun. And these are the years 1992 to 1996. And the period is given by these color codes. The blue, dark blue is 24, light blue is 25 day rotation period, green is 26 day, yellow is 27 day, and red is 28 day. So the sun, which indicates that we have all the colors in this. So which indicates that sun is not rotating like a solid body around itself. Different part and different years, sun rotates differentially. So that is called the differential rotation of the sun. And if we take the average of all the rotation period, that is shown by this line here, in this curve here, and the scale for the curve is given here, that the rotation period near the equator average is about 25 days. In the northern pole side, it is 25.6 days. On the southern side, it is about more than 26 days. So this indicates that not only that there is a differential rotation, there is also an asymmetry of rotation, that the northern hemisphere takes less time, which means that rotates faster than the southern hemisphere. Southern hemisphere takes long time. So that is the asymmetry of the rotation of the sun. Like our Earth rotates symmetrically, and it takes same amount of time almost all the time, and has been doing so for many, many years. But in case of sun, there is a variability as a function of year. Year to year, there is a variation. There is a variation from region of the sun to different region of the sun. And there is also a difference between the north side and the sun side. So these are the kind of examples of detailed study of the sun that has been carried out. And similarly, many such studies are being carried out world over. So this was the declining phase of solar cycle 22, the image that I showed you, the X-ray images where the intensity was falling. So in that period, this is the kind of variation that you see. Now, if we go to the next cycle, which is cycle 23, the rising phase, the first part where the sunspot number increases gradually and becomes large. So that these are the years 1996 to 2001, it increased. And here also, this is the equator of the sun, this is the southern side, this is the northern side. And you see the color codes indicate the rotation period. And again, you see that the rotation period around equator is mostly in these two colors, 24, 25, which means it is it takes less time in rotating at the equator. And on the pole side, there is an increase on both sides. More yellow and red color is seen in the polar region on both sides. But now, interestingly, in this phase, it is almost symmetric. There is no asymmetry in the north and south. They more or less look alike on the northern side as well as the southern side. And very interestingly, if we go to the next phase, which is again the declining phase of solar cycle 23, you see the situation has reversed. That here, this is the scale, the color scale, and the rotation in the equatorial region of the sun is still lowest, but there is an increase in rotation period on both sides. But this time, the northern hemisphere is taking more time. That means northern hemisphere rotates slower than the southern hemisphere. So that means there is a asymmetry, and this asymmetry also has a time variability. So these are the very interesting kind. These have implication in the solar dynamics and the generation of sunspots. I probably will not go to those details, and because want of the time. And this is also a similar study carried out using another satellite data where it is shown that there is a differential rotation of the sun. Here the latitude is this is the northern latitude, the southern latitude, and the color code is again here. This is the lowest rotation period, and rotation period increases on both sides. And here they tried to show it with the temperature of the sun or the solar corona. And with that, if you take the average, it decreases as the temperature increases. So that also has been sort of verified here. So these are some of the examples of the kind of studies that are now going on and have become very important. And similarly, many objects in the sun. And of course, these studies, the study that you do on the sun, you apply to the other stars. And particularly this rotational property of the sun is also applied to search for extraterrestrial or exoplanets, the planets which are similar to. So they group the stars by their rotation, and those who have rotation period close to the sun are like likely to may have Earth-like planet and may have life. So that this is also useful in those studies as well. How much time do I have? Or should I stop at this point and give time to questions? Hello? Organizers?
Hello, sir.
Is it that I take some more time or stop here?
1 second, sir. Chintamani, sir. Chintamani, sir.
Chintamani? Should I take few more minutes or stop here? I think my time is complete as such on the clock, but okay, maybe since he is not answering, I continue.
Sir, another 5 minutes.
Okay. So during this corona time, I did not have opportunity to go out to school. I have a hobby of going to schools and colleges to give popular lectures and also demonstrate some experiments. And a few examples of those experiments, I tried to make some, not video, some photographs, and I'll show you that. See, here is an example of a very simple experiment in which you need to have only three things. One, that you take a glass plate, plain glass plate. Like here, this is my wife, and she has a plain glass plate here and a white sheet of paper of the same size. And now she has put this paper under the glass sheet and trying to see her face. And in this, here she says, I don't see my face. But now this white sheet is replaced by a black sheet, black paper. And if you put the black paper under the same glass plate and then see your face, you see your face. So any one of you can do this experiment. And in fact, we tried to show this to several schools and colleges, and everyone is able to make this observation that when white paper is under the glass plate, you almost don't see your face. But when the black paper is under the glass plate and you look at the plate, you see almost like a mirror. So the question is why that happens. And that is explained here, that if this is the glass plate, when the light falls on the glass plate and gets split into two parts, some part, about 10% gets reflected and 90% passes through, which we call the refracted light. Now, if you put a white paper under here, then this 90% light, which is coming from this incident light, will get reflected by the white paper. But because the surface accuracy of white paper is very poor, it's not as smooth as the glass, so the reflection is scattered reflection. So it reflects, but it scatters light in different direction. So this 10% light, which was good reflection, specular reflection, also gets sort of noised that you don't see your face. But if you remove white paper and put black paper here, then this 90% light gets absorbed. and you see this 90% specular light clearly. And that's how when you put the black paper under a plain glass plate, it becomes like a mirror for you, a 10% mirror, not the 100% mirror which we have here. There's a silver plating in the bottom of the glass plate, which has the reflectivity almost 99% or very close to that. So there you see more light, but this becomes like by putting a plain simple black paper under any glass plate, you can make a temporary mirror. So that's a very simple experiment, but very interesting, and it also teaches us the reflection, the refraction, the absorption of light, and also the scattered reflection. The another experiment doesn't require any device. You can do this right now. That you like here. She is brought her hand near the ear, and you hear a sound. You can do that on with the other hand, and or with the both hands. So you hear a sound. Similarly, if you bring a cup close to it or a glass close to your ear, that also gives you a sound. So this sound is because of the resonance, that with our hand and the ear, there is a resonance. There is a column gets formed which has a resonance frequency, and our environment has all the kind of audio signals present almost all the time. The wavelength that gets resonated with the column that you have here gives the sound in our ear. And similarly, any vessel that you bring, a cup or a glass, they also have natural resonating frequency. You hear that. And let me also show you the third experiment, which is even more simpler and observable by all of you, and many of you must have seen that if we sit in a train and go from one, say, station A to B, and we are in the compartment, and if you look through the window outside, we find that the object close by object 1, 2, and 3, these 3 objects I mentioned, the close by object moves in the backward direction very fast. The second object also moves backward, but slower. Third object moves even slower. And if you go very far, if you look at, say, a cloud through the window, or there is a mountain far away, or there is a tree or temple or anything which is at a far distance, those objects almost move in this direction, the direction in which your train is moving. The objects as such are not moving, but you make this observation. And that is because of this angle, that from A to B, you make an angle. This makes an angle of about 160 degree. This makes an angle about 120 degree. This makes an angle of about 80 degree. And further you go, the angle keeps on reducing. And the feeling of movement comes by how much we have to sort of move our eyelids or our face to track and observe. So very far objects, we almost see stationary, but because we are moving, so they also appear as if they are moving with us. So these are very interesting kind of observations. You can do it yourself and learn, interact, ask questions to each other and teach. Thank you so much. Maybe at this point I stop. Sorry that I took about 10 extra minutes. So if you have any questions, I'll be very glad to answer those. Thank you very much. Maybe I unshare my slide.
Thank you very much for such a wonderful talk, and I'm sure the way you explained in very lucid manner the concepts related to space, I'm sure students must have enjoyed. So with that, the forum is open for question and answer session. So participants can either directly ask the question, or they can put it in the chat box.
The chat box questions, maybe one of you can read to me. I will answer those.
Yes, yes, sir. I'll read that.
Okay, thank you. But if there are no questions, I thank you all. And in my PPT is available with Dr. A.C. Mathur. You can get that, and that I have my email addresses. You can write questions.
अरे व्हाट्सएप मैं थोड़ा पूछ सकता हूँ कुछ आपको?
जरूर, बिल्कुल.
हाँ, एक तो मुझे ये पूछना है कि is there any relationship with sunspots and river course on the earth?
River flow, you mean?
River courses. गंगा, जैसे गंगा रिवर का कोर्स है या सरस्वती का कोई कोर्स था या नर्मदा का कोर्स है, तापी का कोर्स है, तो सनस्पॉट नंबर बढ़ने के साथ ही रिवर कोर्स भी चेंज होते हैं क्या?
नहीं, सनस्पॉट का जो साइकिल है, हालांकि उसमें भी पीपल हैव, बिकॉज सनस्पॉट की ऑब्जर्वेशन करीब 400 इयर्स की अवेलेबल है, लिटिल मोर देन दैट, 400-500 से फिजिकली मतलब मेजर किए हुए सनस्पॉट की ऑब्जर्वेशन है. उसमें वेदर के कुछ पैरामीटर्स तो रिलेट होते हैं, बट रिवर के कोर्सेज वगैरह तो आई थिंक doesn't really get related. No one really have done such work, but I have a feeling that may not be getting the amount of water or the amount of, say, floods that come in the river during rainy season, that may have some relation with the sunspot numbers. But there again, I am not aware that people have done such studies.
I think some scientists from PRL only have studied the course of river Tapi and sunspot relationship.
Is it? Is it maybe from the hydrology group recently? Someone, I retired from PRL in 2011 and have not been going there.
He is also retired, but he has done some study with some students from university and BISEG.
I see.
And
maybe on paleo scale there may be relationship, not in terms of the sunspot cycle which I mentioned, which is very short, 11 year or so, but on because sunspot studies are also done by paleo studies like carbon dating and several other techniques, whereby you determine the solar cycles of the past, and those may have sort of a relationship with the river flow. I'm not sure. Yeah.
दूसरा एक क्वेश्चन ये था कि नॉर्थ पोल पर, उत्तर ध्रुव पर कोई पहाड़ी ऐसी है जो बहुत हाइट में हो?
मतलब अर्थ के नॉर्थ पोल पे या सन के हैं?
आर्कटिक रीजियन में
मेरे ख्याल से तो नहीं, मतलब अर्थ मतलब ये स्नो के माउंटेन तो वहां है, शायद होते ही हुए हैं, बट ऐसा बहुत बड़ा माउंटेन तो शायद पोल्स पे नहीं है, ऐसा जहां तक मुझे लाइक पहले लेक्चर में प्रोफेसर हर्ष गुप्ता ने दिखाया था कि जो एंटार्क्टिक है, दक्षिण पोल है, वहां पे एक माउंटेन दिखाया था उन्होंने. तो इस तरह के छोटे माउंटेन तो डेफिनेटली नॉर्थ पोल पे भी होंगे, बट जैसा अपना हिमालय बहुत बड़ा ऊपर दिखता है, ऐसे बड़े हिमालय, बड़े पर्वत शायद नहीं है.
और तीसरा एक ये पूछना था कि तो ये आपने गैलेक्सी की बात की, तो जम्बूद्वीप नाम की कोई गैलेक्सी है कि जहाँ कोई
नहीं, ये जैन धर्म के लिटरेचर में ऐसा एक, मैंने भी ये पालिताना जो जगह है वहाँ पे उन्होंने एक बहुत बड़ा मॉडल बनाया हुआ है जो बेस्ड ऑन द साइंटिफिक लिटरेचर ऑफ जैन रिलीजन, जिसमें वो जम्बूद्वीप करके बीच में एक सेंटर में बड़ा पोल दिखाया, एंड द एंटायर जिसमें 2 सन है, एक निकलता है दूसरा छिपता है, लाइक दैट. तो वो सिस्टम तो बहुत अच्छा है और बहुत अच्छा भी लगता है, बट जो साइंटिफिक इंफॉर्मेशन हम लोग जानते हैं उसके पे आधारित वो नहीं लगता। ऐसा मैं गया था तो मैं वहाँ के जो
जाने का टाइम हो रहा है मेरा, किचन में ही कर दे थोड़े से जल्दी से।
तो जम्बोद्वीप नाम का
तो
कोई
आपको
गैलेक्सी तो नहीं माना जाता है। गैलेक्सी बहुत है, ये तो है, मिलियंस ऑफ गैलेक्सी है।
Are there any other questions from participants? I think, sir, there are no questions. So thank you very much, sir, for joining us today and enlightening students about opportunities in space science. Thank you very much, sir.
You're welcome.
With that, we now move ahead for the next talk on application challenges and opportunities in space sensors by Dr. Samudraya. And I invite Dr. Rajesh Nairi, who is a professor in PC Jabin Science College, to officially introduce the session speaker.
So good afternoon to all participants and delegates over here. So I, Dr. Rajesh Nairi, Assistant Professor of Physics and Assistant Professor of Physics, PC Jabin Science College, Hubballi. So take this proud moment to introduce one of the eminent scientists, Sir Dr. DRM Samudraya. Sir has completed his MSc in Physics from Andhra University in the year 1975 with the specialization in electronics. Later, he joined Space Application Center, Ahmedabad in 1976 as a senior scientific assistant for the development of television cameras for Bhaskara 1, the first Indian remote sensing satellite. Sir has grown through various grades and retired in the year 2013 as outstanding scientist and deputy director. He shouldered various organizational and project responsibilities and made extensive contribution for the design and development of more than 50 state-of-the-art electro-optical space sensors for remote sensing of Earth, Moon, and Mars. As a deputy project director, he guided various teams for OceanSat 1 technology experiment, Cartosat 1, Cartosat 2, 2A, 2B satellites. He had been instrumental in establishment of state-of-the-art laboratories and the development of world-class technical teams. His fields of acquaintance are electronics, electro-optics, optics, physics, remote sensing, team building, and project management. Post-retirement, Sir guided teams at ISRO as Professor Satish Dhawan scientist for 2 years. He registered for PhD in 2016 and completed in 2020 in the field of ocean remote sensing from Indian Institute of Remote Sensing, Dehradun and Doon University. He is presently a member, chairman of review committees at ISRO and DRDO, honorary advisor for PRL, and mentor, technology advisor and mentor for some of the private institutes, industry, startups, universities involved in aerospace activities. Sir contributions have been recognized by ISRO and various professional societies by honoring him with awards. He received team awards for Cartosat 2 awarded by ISRO in the year 2007, Spacecraft Technologies Awards in the year 2009, National Geomatics Awards in 2010, Satish Dhawan Award in 2014, ISRO Individual Performance Excellence Award for Lifetime Contribution in 2012. He was selected as a Fellow of Indian Society of Remote Sensing in 2020. His research contributions, he published more than 60 technical papers, book chapters, and design and development reports. Also, he's a life member of various societies. To name few: Archaeological Society of India, Indian Society of Remote Sensing, etc. He was the chairman of ISRS Ahmedabad chapter from 2009 to 2011, vice president IRS, a national body from 2011 to 2013. During his period, so he has organized many conferences, seminars, and conferences. So with this brief introduction, I present before you, so Dr. Eminent Scientist, Dr. DRM Samudrai. Welcome you, sir.
Good afternoon, everybody. Thank you very much for the nice introduction. And first of all, I thank the organizers, Sri A.C. Madhur and the college for giving me an opportunity to share my experiences regarding sensors. So I think I will start my presentation with sharing the my presentation first. So, Jabin College. Are you able to see the presentation?
Yes, sir. Yes, sir.
Okay. Thank you very much. So I will, because time is less, actually, Hariom sir has given very nice lecture, and he has given the best introduction that can be given for this type of seminar. So over about the overall space and the science and the pending issues, opportunities, etc. So my actually aim is only to expose the youngsters to the space sensors per se related to spacecraft as well as for the remote sensing. There are many other sensors. Because the time is less, I have restricted to very small field, but still it will give a very good exposure and acquaintance. So many of the, I included many view graphs to just make the people feel about the intensity of the research that can be done or the opportunities that are available and the applications. So some I may not be explaining in detail, but anybody who wants to know, they can always contact me because my mail address is given at the end. So first of all, my salutation to all my teachers, because research is continuously learning, and all my ISRO seniors and colleagues, and I may heartiest greetings to all the participants for the best understanding of the awareness. So first, my presentation basically addresses what is space sensor and what are general considerations and approaches for developing sensors, and sensors specifically for control and operations of the spacecraft, and for remote sensing of Earth, Moon, Mars, or any planet, what are the type of design principles and challenges we have. And after this, I try to give the Indian accomplishments in sensors realization and applications. Here also I am restricting to only optical sensor, electro-optical sensor. There are microwave sensors, X-rays, gamma rays, like that many sensors are there, but we are not able to discussing all of them. Flavor only. And finally, I will also discuss who can do it so that it can motivate the youngsters. And at each of the bottom, I try to put some quotations which are very valuable and motivating for all the budding scientists. So I just for information, and many of you may be knowing, but they are all motivating to me. So I thought I shall share that to you. So what is a space sensor? In general, if you see space sensor, basically, I try to. Okay. Yeah, space sensor. Basically, space sensors are sensors which are there on satellites or space stations or rockets basically to make them work properly. That's why they are one class of space sensors. And other class is to study the deep space, planets, stars, galaxies. That's what our Harivam sir discussed. But I'm not going to go into details, but they are different class. And other thing is that as sensors help to study in detail of Earth, Mars, Moon, or any other planet, what we want to do. So these are the general things we can think about space sensor. But the classes, we can have different names like analytical sensors, contact lenses, remote sensors. So analytical means you need to have a sample and then do all that work. A contact means slightly away from the sample, we are keeping our instruments and doing it. Remote sensing means we are looking at the objects very, very long distances. So these are the general classes of sensors we can think. Why we are telling you, for each of them, based on this purpose, the sensor design will be different. So that's why I have put. But in general, if you want to see what are the sensors for the space, so we have imaging instruments like panchromatic color cameras, infrared cameras, stereo cameras, microwave radars. Like that, we have radio instruments or spectroscopic instruments. Each wavelength wise, how is the behavior you can know. It can be in different ranges. And we can also have particle detectors, charge particle detectors, neutral particle detectors, and some more compound plasma spectrometers, electron temperature probe. Like that, there are many types of things. There are gas sensors, mass spectrometers, gas chromatograph, wind sensors, and humidity sensor, temperature, pressure, electric field, magnetic field, seismic. Like that, there are so many sensors. So you know, it's very, very wide. But all of them, which can be used on the ground, they can also be used on the space or other planets. That's why all are required to be understood. Only some we are going to touch. So while designing or developing sensors, what are the general conditions or considerations we need to consider? So just to give a flavor of the complexity of the system and challenges involved in developing the sensors. So before that, we just try to understand the basic sensor which we use daily, that is our eye. Eye, basically light is coming from somewhere. So either it is from sun falling onto objects and reflecting back, coming onto the eye. So input is light. So basically there should be a source to illuminate. Either source itself is illuminating or it is illuminating some other objects. Then that light comes and falls onto the eye. So there is a lens. Okay, there is an iris, aperture can be controlled. Then it is focused. So it is collecting and focusing and falling onto the retina. So in the retina, you have again different cones for different colors. And there is optic nerve, and finally it goes to brain, and whole system works. So it is just to understand. So basically there is a source of a signal. That is, in general, for space we use electromagnetic rays, not sound waves, etc. Because electromagnetic waves, they pass through even vacuum. So electromagnetic waves are required like that. There should be a source like sun or artificially created source. Then you have the whole rate of optical system, or even in you can RF also you can have. All these things can be done. Basically understand the building blocks of a sensor. You can get a feel of it. Now the sensor can be mounted and understood, measured from at different places. You can on the ground or on balloon, helicopter, aeroplane, and satellite. So for each of them, the conditions are going to be different. So accordingly, the sensor design will be different. So, and because basically it has to work on a moving platform and environment is going to be different. All these things have to be taken. But in the sensors generally, platform control sensors, generally they take into account the platform characteristics, how they are transported on the ground, what is the environment in which it has to work. But remote sensing systems, sensors, in addition to the above, they also have to look about the illuminating source and as well as the target. So these are only basics I am touching just to get a feel of scientific feel of the what is involved in the science. So now if you see the sensor design, depending upon the operating conditions in which orbit our sensor is going to work, at what height, and atmosphere, if it is going to be on that place, on the orbit, or on a planet, what is the atmosphere, surface temperature, pressure, and dynamics of that, like wind direction, circulations, etc. Surface conditions, whether it is rocky, soil, etc. Gravity of the planet, radiation, energy sources available, because every sensor requires power. So we require to understand what kind of energy is available, and the energy sources, radiation, it come, cosmic rays, etc. can damage, and vibration, mechanical shock, etc. So in addition to this operating conditions, we also have to take into account what is the scientific aim or functional aim of the sensor. That is what dictates the thing. Then basically, finally, mission and technology base. So what is the size and weight of the sensor? What kind of power generation technology and capabilities available? And what science data, whatever you collected, how to transmit it? And reliability. Reliability means how are we sure that it works for the required time in the required environment? So it is a different flavor. One has to take into account all these things with respect to. Just to understand the vibration effects, see, when the rocket is launched, there is going to be acoustic vibration, and during launch, and then stages are separated, then also there are going to be shocks, and on the ground there are transportation related environmental conditions, and these things will degrade if they are not taken into account. So acoustic energy can cause vibration. So structural components from 10 hertz to 10 kilohertz. Our sensors, our mounting systems have to take care of this thing. And these frequencies, it can cause resonance, natural resonance, and then energy peaking can lead to failure. So generally, we design the things such that their natural resonance frequency is outside these bands. That is general approach. And these are, because there are problems, challenges, and I am also discussing what solutions are generally things. Now, if you see here, if you are trying to design a rover or lander on some planet, environmental conditions make difference. So you can see here in this picture, average surface temperature on the x-axis and average surface pressure on the y-axis. So Earth, if you take as one bar, now you can see 1,000 times more pressure is there in Jupiter. And similarly, temperature wise, if you see, Mercury goes to 400 degrees centigrade. Venus also is like this. So every planet has got a lot of temperature, pressure, different. So if you are designing, you have to take into account all these things. So there are different considerations, spacecraft heating due to incoming and reflected solar radiation, outgoing IR radiation. So materials have to be selected with proper temperature operation, coefficient of expansion, thermal expansion, TTE, and conductivity has to be taken into account. So these are the issues which are taken into account in the spacecraft, lander, rover, and even in sensor. So that's why I just put the complexity is very high, but it is very challenging, and people have found out the solutions also for this. And if, for example, there are high temperature materials like titanium, metal matrix, nickel superalloy, ceramics, etc. They can withstand very high temperature, just for example. So nothing to get frightened. So there are solutions, already research has been done. We shall make use of it. We can also make new materials. There's no problem in that. Similarly, electronic systems, normally we do with silicon, whose maximum temperature is 150 degrees centigrade. We can use gallium arsenide, it will go to 350, or if you use silicon carbide, 700, or gallium nitride will go to more than 750, and if you make a semiconductor with diamond, it will be 1000 degrees. So there are materials available, so we can always do the research and do proper design of the electronics for that. Similarly, if you see, this is the wind speed and average surface temperature. You can see on some of the planets, the wind speed compared is about 100 meters per second, but if you go to Neptune, it's going to 500 meters per second. So, and at different pressures, these numbers are there. So what we have to select is material selection for mechanical strength. Then it also requires self-cleaning property, because a lot of dust will be coming and falling. So the experiment cannot be conducted, or we have to use a shutter, or because wind speed is very high, we need to have fail-safe modes in the systems. These are the considerations generally. And if you see the research, now you see naturally lotus leaf has got a self-cleaning property. You understand, all of you have seen it here. Now it is hydrophobic with nanostructure. So such nanostructures are already developed by the world in the world. So we can try to make use of this. You are all aware of the even paints to avoid dust. Similarly, we have another parameter, what we call the mass of the planet or the gravity of the planet. So if you see compared to Earth, the gravity goes to 4 times, 3 times at Jupiter, and mass ratio is that. So accordingly, we have to select the material for mechanical strength and mass and landing mechanism and fuel, because gravity is different. Rover fuel and mobility, region of exploration may be selected where the numbers may be comfortable. So just to give a flavor how the sensor design is driven, or the spacecraft or lander design is driven. So another parameter is called the radiation. Radiation comes from sun or other stars. So we have the cosmic rays, galactic cosmic rays, and solar protons and heavy ions, etc. These numbers again measured in radiation megarads per mil of aluminum, etc. So they all vary from place to place, this to this. So we also have to take into account, in case of Earth, we have a magnetic field. So because of Earth's magnetic field, the particles will be traveling and getting concentrated in some regions. So we have to worry about those regions like called Van Allen belts, etc. So and they create, actually, accumulated radiation also creates a problem for electronics. A single heavy ion also will damage the electronics, or even optical materials can get damaged, mechanical surface crashes can be changed. So we have to select materials with radiation hardness or tolerance to radiation, shielding effect we have to create, and resistance to degradation also we have to select. Such kind of challenges are there. And if you see, another thing is the power. So if you take from sun, the solar system itself, as we go away from this thing, the sun energy coming is falling down significantly. So when you want to try, what happens is the solar panel has to be designed accordingly. So their efficiency, size, mass will be taking, material also will be taking. So, but orbit parameters also have to be decided, because when you are orbiting, only some part of it only will be seeing sun, remaining is not there. So these are all the considerations we have to take. So as we go away, actually, received power will come down, and accordingly solar panel size has to go up. Or if solar power is not adequate, we have to go for nuclear batteries, etc. So these are the, again, requirements for from the sensor point of view. There are many types of nuclear batteries. Some are being now started in India also, these kind of batteries, but not yet fully developed. Okay. So similarly, as we go away from the Earth, so the angle subtended by Earth from the spacecraft, it will change. You can see here the angle is big and angle is small. So the antenna, etc., because the data has to be transmitted, you require a narrow beam width antenna. High pointing accuracy systems are required. High transmitting power also, because distance is there. Then bigger aperture receivers on ground are required, or like that. Otherwise, we can go for relay operations. So this you can see different types of planets. We can see angle subtend is different. So accordingly, the complexity in the systems have to be taken into account. And another thing parameter is one-way interplanetary communication delay, because signals are electromagnetic, so it takes this time. So if you see here, Pluto, this is the time. It takes 250 minutes, etc. So like that, different planets take different. So because what happens if you want to command, you can't command real time. So you have to have autonomous systems which senses the considerations, what is the conditions, and takes care of that. And also robustness to errors. Some error happens, it should be able to correct. These features have to be incorporated in the sensors and also in the spacecraft. So these are all the complexities and challenges. For example, that we have discussed about the operating conditions, etc. Now, scientific aim. Suppose you wanted to see the origin of life. But we know origin of light, if it had to be there, inorganic building blocks are required, water is required, and energy is required. And from that, actually, what is our understanding of the life on Earth? So there are cells created, and then from that, molecules, then micromolecules, macromolecules, chains of molecules, then the small creatures, then the plants, mammals, okay, human beings, etc. And if the life is not there, once upon a time it was there, you will see fossils. So based on that, based on this kind of structures, you have to design the sensors. For example, if you see here for detecting energy sources, we require photometers. Kindly mute, sir. Thermal sensors like that. For detection of water, kindly mute, sir. Kindly mute. IR spectrometer, mass spectrometer, like that. For detection of elemental building blocks, okay, we require all these types of instruments, UV, visible, X-ray, etc. For detection of fossils, etc., we require imaging color camera, etc. For detecting living organs, imaging color camera. So like that, you can see the sensors design. It is not only operating conditions, but also the science driven. All these things together decide what is to be done, how we can do it. As per sensor, the spacecraft also is spacecraft or lander or rover. They're all built around that. So that is why it comes. So basically, we need to study a lot before we propose. That means continuously we keep on reading what others have done, make use of that so that we can minimize the resources required, experiment can be properly done. So what others have done so far and what measurements are required, out of that, what is the range of the measurements, accuracies of the signals, and what would be the approach for analysis. Once you measure, how we are going to do this also decides. So basically clear scientific goals lead to optimum experiment design. So it is possible. Everybody has done. Lot of literature is there. That's why we keep on reading. Everybody has to read. That's why Harivam sir also told it is a continuous reading. Harsh sir also told it's continuous understanding, learning. So we can do it. So this is the thing. Now, if I come to sensors for control operation of the spacecraft, actually. So very brief on spacecraft. Basically, we need to know we have power system on the spacecraft. We have thermal system controlling the temperatures. We have the attitude in which direction satellite is looking at is required, because we have some parts have to look at sun so that power is maximized. So attitude sensors and command. When you give command, whether command is executed or not has to be understood. There is a sensor for that. Then propulsion system. There are gases. So there are gases, etc. So pressure sensors are required. And so if there is a human being are there on a space station, Earth station, etc. So we need to have environmental control. Sensors are there for life support and control. So these are all the things that has to be, these are generally there. Here I just gave a sketch of the sun sensor. Suppose in this axis, you know, if you put a sun sensor, based on that sun angle, we can move the system, whatever is required. These are required for sun sensor to track the solar systems. Then because it has to be monitoring the bus, there is a bus voltage sensor, the battery sensor, current monitoring sensors, power distribution if it is done to subsystems, again monitoring is done. So like that, similarly thermal system temperature monitoring, like thermistors, etc. are there. And then attitude sensors, they are very critical, because when you take photograph, you can't move it. So you have to be stable. So for that, S sensors are used, sun sensors are used, star sensors are used, stars are used, magnetometers are used, and then inertial measurement units are different types of sensors are used for different purposes. You can also see their accuracies are different. So there are a lot of research being done in all these things. And this Earth sensor is like this. So you can Earth horizon, because Earth is having a radiation. So against the deep space, where the transition can be monitored, from that orientation of our spacecraft with respect to Earth can be understood. And like that, we have similar star sensors. You can monitor the stars And then based on the stars, you can have a catalog of the stars. And from the catalog of the stars, you can know exactly where we are monitoring. Just to give a feel of these things, these are the some type of sensors. And now I'm going to go for the remote sensing systems. So where the sensors are used for looking at the sun, moon, earth, or stars, etc. So what are the design principles? So this that remote sensing. So if you see an example, a sun is there, sun rays are coming, going through atmosphere, which has got some absorption characteristics, falling on the earth, and it reflects. So it can be seen by a sensor on the spacecraft or satellite. Once you sense, convert into electrical signal, transmit it to ground, so you can reconstruct what you have seen, and then that can be analyzed based on the differences in the reflectance at different wavelengths, like that. And once you know this, you can understand this is a bare soil, vegetation, etc. So accordingly, you can do the applications. A lot of applications can be done. So basically, remote sensing requires a source of illumination. In this case, it is sun, but in case of active sensors like microwaves, etc., the satellite itself will have its own source. Keep and please close. Okay. So, and also we need to study the spectrum of this, whether it is in whether it is in the X-rays, ultraviolet, infrared, visible, microwave, like that. So different things can be understood from that. And even the atmosphere will be different for each wavelength. It is not going to be same. Some will be transmitted, some will be absorbed, some will be scattered. So all that we have to understand. So we need to understand about the source, about the atmosphere, about the surface characteristics, then the sensor comes into picture. So see, these things have to be understood to properly interpret what the information we are getting from the sensor. So just to give a feel of how the remote sensing is there, but this source can be replaced. In this case, we may not be looking at the earth, but we may be looking at the star, or we may be looking at the galaxy. Then they will have their own light coming out. It may be X-rays or ultraviolet rays, like that. Or distant things can be understood from radio waves or microwaves also. So depends upon the observation aim, and the sensor has to be designed accordingly. So in addition, I told you the sensors have to be the reflection. Sir also explained, Hariom sir explained. So you have normally we study in the school, the specular reflection like a mirror. But if the smoothness has to be much smaller, the roughness has to be much smaller than the wavelength involved in this. So if it is not, so it is not in one direction, it will be multiple directions. So here, completely diffused. That means it is going in all directions. Because of this diffused reflection only, we are able to see in our room or in outside all objects, because light is falling on all objects. From that object, they are going in all directions. That's why we are able to see. So diffuse reflection. So we may have a fully specular reflection, or a combination of specular as well as diffuse reflection. So these are the characteristics of the surface. So we have to take into account these things also while designing the sensor. So once you see that here, but what is the advantage of remote sensing of Earth per se? Because India has advanced so many sensors, and we are on par with world in many cases, not in all cases. So what is the advantage of that? Because the satellites are moving around the Earth. So we have systematic data collection. So we can repeat and see what happens after some time, and we can have global coverage. Even though you have sent one satellite, the whole globe can be monitored, and whatever is we cannot access also, we can actually see with remote sensing what is not accessible normal way. Then multi-purpose information. Once you collect information, you can use for land, water, or atmosphere, or roads, whatever it is there. So multiple purposes can be combined and obtained. And this actual remote sensing gives a scope for continuous research and innovation. So all the scientists and engineers, they continue to do the work, and there is so much progress. Further, lot of future is possible. And there are large number of ongoing and new applications are also there, because this data remote sensing for Earth particularly, we have the US has got, European countries have got, India has got, China has got, but you can see there are so many applications. Now you see with satellite, using Landsat satellite, the crop land is completely mapped. So we can understand which crop is there at what place, and then what kind of drought is going to come, or if there is some heavy rains, what is going to come. All these things we can estimate the yield of each crop and find out. So this is one application regularly used. In India also it is regularly used. And other thing is the scientific things. So there are systems and process, how the land surfaces, water and atmosphere, how they are getting affected by the whole of sun interaction, and because of that, whether global warming is happening or not, and what is going to happen, so you can study. So these things can be further presented in various places. Disaster monitoring also can be done, like that it can be done. So in addition to this remote sensing data is combined with geospatial, geological information system, a computerized system where each layer has got information. One is the picture and non-imaging data like population, etc., can be money, all these things, can be combined, and then decision can be taken. So this is called geospatial information system. There are many advances, and India is also one of the top countries in using these things. So now the GIS combined, the applications are innumerable actually. We can't even do it. All industries can do, all you can do in natural resources monitoring, you can do tourism, you can do strategic things related to military, you can do like that. There are many things can be done. So applications of remote sensing are innumerable, and then people are going to give lectures. So I'm not going to touch on this, but sensors, when they design based on these applications. Just I want to draw your attention and give you a feel, because every sensor designer feels happy when this data is used in multiple applications for the development of the humanity in the world. So that's why I just put this. But basically, if you see any optical sensor, you can think a lens is put here, which has got a focal length and field of view, and so it can see this much ground on this, and because it can image this much area onto a sensor with pixelated sensor. It's not a single sensor, so you can have information on each of the piece separately. So basically, we have focal length and the height about the thing. So from this, okay, you can think of all these things. So this is called the smallest element what we can resolve in a remote system, we call resolution. And at a time, how much we are able to see, that is called swath. And the same thing, the parameters related to lens, if you take, they are called instantaneous field of view, focal length. Similarly, sensor, if you say there is a detector pixel size, how many microns each detector is there independently, and how many pixels are there, and what is the format in XY, how much is there. These are all the things. So, and one thing we can understand as a general knowledge is as the height increases, you can see as height increases, spatial resolution becomes poor, but it covers more area. So sensor has to be designed. If you want particular resolution and particular orbit, so you have to design accordingly. So these are the just fundamental things. Now, if you see here, you can also see the same thing what we have told. There is a lens. You can see multiple elements are there, single element lens. There is a complex device. Then the data is collected. There are sensors, multiple sensors. Then this converted into electronics, analog processing, digital processing, data conversion, transmission on the ground, reconstruction. And there are structures required for controlling all these things. You can see here mechanical designs are required, and the whole system has to be controlled. Thermal design is required, and whole lot of system control, system equations are there. So design challenges, if you see, sensor parameters are interdependent. Resolution, swath, how many times you are seeing in a day, or after how many days you are seeing, like that, all are interdependent, and there is no universal design to cater to all the requirements. Okay, so custom design for functional performance specifications. So how we do it based on the available technologies understanding of this. So based on that, and spacecraft resources, spacecraft also how much power it can give, how much data it can transmit, how much size it can accommodate. So all these things are taken into account. And other than this, important thing is always space design means we require minimum volume, because you're carrying 1 gram also, it requires a lot of fuel. So minimum volume, minimum weight, minimum power. And spacecraft interfaces, how many are there? They are limited actually. Then the launcher and environment reliability. So these are the things. So if you see the challenges, so you have the challenges in the system design, optics, detector, electronics, mechanical, digital synthesis, data compression, data formatter, transmitters, receivers, antennas, ground processing. All these things are challenges, and there are so many things that can be done in for any scientist or engineer. It can be done. So it is quite challenging. So quite interesting. Just to draw attention, I gave some more details of what is remote sensing system. That is what. And basically, like we have our eye, and if you want to see more, what we do, we move our head. That means more area we are able to cover. This is called scanning, right? The scanning, same thing if you want to do from the spacecraft. If you have a single detector, you can do only imaging of small this thing, then you have to move like this, then the spacecraft moves. So you can have, this is called whisk brooming type of system. And initial further developments have come where instead of single detector, we can have a line of detectors. So the field of view will be slightly bigger for optics, but it can image one line at a time, so many pixels. The spacecraft movement gives this. So XY direction we are giving scanning here, or we can also have whole frame. You can have and further frame can. So these are there are many more imaging modes, but I just to give an idea. So there is a scanning mechanism which is required, and we are trying to intelligently use the spacecraft motion itself as a scanning mechanism. So that's what this thing. So coming to optical system, there can be refractive optics, there can be reflective optics, or mix of reflective and refract, what we call catadaptive optics, based on what kind of field of view, aperture, and spectral range. Refractive is the lens type of thing. So spectral range is very limited, but it's very light and cheap. But whereas reflective, it can be for wide spectral range, because mirrors, there is no specific wavelength related, but it can give large aperture but narrow field of view. And catadaptic mixes all these things and gives this. So selection is based on the requirements of aperture, field angle, etc. And design has to take into account functional performance requirements, fabrication, how do you realize it, either here or somewhere, what are the tolerances in the fabrication, and what are the aberrations we have, and how to minimize it, and how these things are going to be mounted, and because so that they cannot move with respect to vibration, etc. So all these things have to be taken into account. So these are just to give a feel of the complexities or challenges in optics. Now, if you see, because we want to measure in different wavelengths, so we wanted to have 4 bands, 5 bands, or continuously whole spectrum we want to measure. So we need to have a spectral separation system. There are different spectral separation filters. Actually, you can have, or you can have a gratings, you can have prisms, you can have, like that you can have interference filters, you can have. These are different types of spectral separation systems. There are a lot of research in all these things. Actually, now you can see here, in a single detector, you can put the filters on different filter wheel and move the filter wheel. So for the same area, you can collect, if you fast moving, you can collect in different bands, or you can have a strip type of filters on a array detectors. These are multi-band systems. Or if you want to have a continuous spectrum, like we can have the prism for splitting the light into various things. I just shown only visible, but it can be done for any wavelengths. Or you can use gratings, and even in gratings, nowadays they are called convex gratings, where the complexity is going to be very, very high, but very good quality spectrum is available. And we are also having a wedge filter type of thing. As we move, the color changes actually. So in an array detector, you put this one here. So for the same ground, if you are moving, you can get color. So these are some techniques already being done. And coming to mechanical things, when we have different, this is one camera. There are primary, secondary, tertiary mirrors. They're all kept in a structure. So this structure actually supports optics, detector, and electronics. And requirements of the structure is low mass, high stiffness, and alignment is important between optical things. Very small variation also can degrade the signal. So optomechanical sensitivity, thermal stability, whole area has to be, whole volume has to be controlled within 2 degrees. Now you can see how the structure actually is mass relieved, light to make it lightweight actually. So these are all the challenges and solutions already available. So you can see primary mirror, okay, secondary mirror, tertiary mirror. So these are Cartesite 2, and you can see even the mirrors are made of glass where the material is scooped out to make it light. But at the same time, the surface curvature has to be same, and surface finish has to be to maybe lambda by 50, lambda by 100 type of requirements have to be there. So it is a very good technology. And these mirrors, once made, they have to be mounted stress-free. So you can see stress-free mounting of the mirror with a bipod. So kinematic design they call. So these are all the challenges, how to make a mirror, how to make it lightweight, how to hold it, even if some temperature difference is there, it will not move, or if there is a vibration also, it will not stretch the mirror, it will not change the position, it will not degrade surface finish. These are all the challenges in the sensors. And we have to align all of them properly. Otherwise, we will not get it. Suppose you see there are 3 detectors. If the alignment is proper, they are like this. If the detectors are not aligned properly, or mechanical structure is not designed because of temperature, vibration, or in alignment, they will be like this. So similarly, the detector has to be in focus. If you are not keeping, we get a blurred image. And if it is a multi-band, a blurring also will create much better. Registration also is important. So these are all some of the challenges and solutions. And coming to detectors, actually, if you see detectors, what we call transducer, which converts the light energy or X-ray energy or gamma ray energy into electrical signal. So there are different types of things are there. So if you see for different types of wavelengths, different materials are sensitive. So one has to select these kind of things. And similarly, based on the material selected, it can be CCD or CMOS or thermal detector or photon detectors. It can be linear array, like that. You can have different types of things, and there are new detectors coming as novel quantum detectors, etc. So there are so many challenges. So they give different sensitivity, they give different resolution, and they give repeatability, accuracy, dynamic characteristics. So these are some challenges of detectors. Just I want to bring. You can see here a CCD, 12,000 element detector CCD. The charges are collected, going to this, and coming out. So these are all the things that happen. Integrated circuits are made where the photosensitive zone is there and electronic zone is there. So, and finally there is amplifiers, etc. are there. And nowadays in CMOS detectors, even analog to digital converters are also included. That's why those cameras are being used in our mobiles. So just to give a feel of it. Now, if you see the electronics, CCD has to be biased. So some voltages are required, some clocks have to be given. Then that output coming has to be processed through preamplifiers, post amplifiers, ADC, etc. Then they have to be handled, data handling and transmitted, transceiver, etc. These are all the things that happen. So based on the what we call resolution, total number of pixels to be processed, or detector type and radiometric resolution, the complexity of electrons is going to be slightly different. Now, one more thing is we require low power, because we already told power is a premium. So there are many challenges to design low power electronics. So, and integrated circuits. There are so many techniques that can be used. I'm not going into details, just to understand there is a lot of research that's going on and people are using it actually. So it is all being done. So low power design is a continuous challenge. And then there is something called thermal control, because optics performance is sensitive to temperature. So we have to control the whole of optics into 2 degrees only gradient, and particular temperature goes on 20 plus minus 3 like that, or somewhere it will be minus also, minus 10 like that. Then similarly IR detectors, they are optimum only at 150 Kelvin or 30 Kelvin. So bolometers particularly, they require 10 millikelvin stability. Variation has to be 10 millikelvin. So calibration sources has to be, black bodies has to be 100 millikelvin. So for all these things, thermal design is done by there is no convection in the space. So only conduction and radiation. So proper conduction has to be done. There should be modeling and experimentation, validation. So basically we remove the heat to environment by radiation. So for that we do pre-cooling. The pre-cooling can be done by space, exposure to deep space, which is 4 degree Kelvin, or by electronic devices also you can do, like the thermoelectric devices, etc. All things can be done. So these are all the thermal is very critical. So it is again science related to thermal is very important, and mechanical engineers also work on this, and then together they design the very good thermal systems. So, and one more important thing I told you, just to give a flavor, the reliability. What is reliability? Reliability is the probability of a system performing its functions for the defined period in the defined environment. So we need to worry because space is very harsh actually, and it is different from what we experience on Earth. So it is not possible to go for maintenance or repair. So we need to have reliability. It is a quantitative thing, so we can do that. So there are many techniques by design, by testing, by inspection. You can always do all these things. So basically, the design has to take into account, then it can be inspected or tested. So this is how ensured. And if you just want to understand, if you do what happens, you get a feel of this reliability. So like any system, when it is made, its lifetime, on x-axis lifetime is put, and failure rate, if you see, failure rates are very high in the beginning. So this is called infant mortality rate. Now even in humans, we know children have a high death rate, and once it stabilizes, then it is a low but constant failure rate. And again, after aging, the failure rates are high. So these are the things. So quantitatively, they can be done. So to understand whether a product is having a problem or not, through different actually tests are done. Thermovac, vibration, thermal cycling tests are done. So through that, so we can establish, rule out that there are no problems and ensure, give confidence that it works by adequate number of systems, quantity, we can say, yes, it works. So that's why there are different models. They call engineering model, they call flight model, proto model, like that. So through models, we establish that things will work. They are working consistently under different environment. So that gives the confidence. So now if you see, I've come to the last part of my presentation. So here we have the sensor realization, challenges in application with examples, not much this thing here. So you can see here, we already discussed about application. For weather monitoring, we have so many things we have done from the beginning. Meteorological payload, 1971, airborne multispectral scanner, 1976, then VHRR in INSAT series, 1992. Now INSAT 3D, we have got the best system imager. So actually here it uses a wishbone scanning. So pixel by pixel or multiple pixels, multiple lines are scanned. That's what system here. So it is a bidirectional scanning, etc. So a very complex scanning mechanism is used here. So this is the best we have. You can see it gives a 1 kilometer resolution from 36,000 kilometers orbit. That is geostationary orbit is giving 1 kilometer in visible and sphere. And MIR and TAR it gives 4 kilometers. Water vapor it gives 8 kilometers. So these are the bands in the atmospheric absorption transmission. You can see where the bands are located. So it is a very large spectral range, large field of view. And these are useful for cloud picture, surface temperature, wind, vertical temperature profile, vertical humidity profile, total ozone and its vertical profile, aerosol density. All these things can be obtained from these imageries regularly. So this gives a typical figure, and this is the instrument actually 6-channel imager flight model. You can see how it is, just to get a feel of it here. And similarly, we require the vertical profile of the things. So infrared sounding is one of the things. You can see here, if you see here, this is temperature, this is the height. If you see, actually temperature varies and pressure varies and also humidity varies. So we need to understand from place to place, time to time. That's why there is sounding systems. So they are infrared sounding. That means what the Earth is radiating, when it passes through the atmosphere, how it gets modified. So if you measure the the radius, the top of the atmosphere radiance, from that you can estimate at each layer what is the concentration, what is the pressure, what is the temperature, etc. This is one way of infrared sounding. Other is limb measurement. That means not from top, from satellite is going, see ahead or behind. So they are called limb measurements. Or you can also look at sun and star against this, how this atmosphere is behaving. That's called occultation measurements. So there are different systems. So instead of that, people are also using LIDAR. So instead of depending upon star or these things, you can send laser, and how the atmospheric particles are actually behaving, you get by the reflected energy. So these are the techniques that are used here. So inside 3D sounder, if you see here, we have actually inside 3D sounder. Sorry. Yeah, this inside 3D sounder, we have actually 19 channels arranged, filters arranged on a filter wheel, and these are the positions of these things. So these are operational, and we are getting data. And inside 3D is actually are already in the space, and they are giving continuous pictures. They are useful. Now the limb viewing actually. So I just gave you example of limb viewing. So here you see satellite is moving, so it is looking at the and horizontally. So limb viewing. So limb viewing, we have made a payload, and it is called atmospheric spectroscopy. Air glow measurements are done. You can see the pictures of air glow. Very low intensity signals, very high sensitivity system is made, 100 Rayleigh. So this is the type of thing with the 2.6 watts and 2.9 kg system is flown already. And another thing is ocean. Sensors are designed specifically for ocean, because normally water reflects. So very small light goes into the water, it gets attenuated. But in the top layers of the water contains the particular oceans, you got the chlorophyll, or what you call mass, green mass, and sediments, suspended particles. From that, the light comes back as a scattered light. So that gets added along with what we call the atmospheric scattering. So if we can measure this in different 8 bands, so we can find out what is the chlorophyll content and suspended particles, etc. Even the bottom also we can know. So these are the things. So you can, this is a very challenging thing. So we have a 360-meter sensor, best in class, with swath of 1420 kilometers. That means 2 days reflectivity, 8 spectral channels, very narrow. So 12-bit system, 12-bit radiometric system we have made. So this is ocean color sensor 1, 2, like that. 3 is getting ready. You can see these are the pictures from the taken, created from the ocean color, the global ocean color. You have the chlorophyll maps are made, and you can also see how even the sediments are there at coastal areas. So these are the things. So these are like that. We can always make these things. These are the ocean color. And similarly for land, there are resource-set series of satellites, and many satellites are there. So there are 3 resolutions and swaths. So one is the coarse resolution, and medium resolution, and high resolution. So you can have a sampler type of things with these kind of things. So improved urban planning, mapping, national security, crop discrimination, crop yield, forestry, disaster management, all these things are being done. So these are also technologically very big and useful. You can see some of the pictures of advanced wide field sensor, 56 meters, Cape Town. You can see picture here. This is the cameras, 2 cameras are there. Then you can see list 3, you can see Murray River in Australia, and you can also see Kuwait with list 4. List 4 is high, this thing. So this is another thing what is made by India, so for which we are all proud of it. and all being used continuously, not only by India, but even the other countries are using it here. And we also make a stereo camera, because when you want three-dimensional, you require observation in two angles. So these cameras are mounted with two cameras of very big cameras, 41 pan sensors. So they are again used for many purposes, particularly land survey and complete topography is made. You can see this three-dimensional view is created using this camera data. And Cartosat 2 series, where we get better than 1 meter resolution. So this is the better than 1 meter resolution. You can see new technology, step and stair technology is used here. So this is a very big camera with about 1 meter, 0.8 meter primary mirror. And you can imagine 0.8 meter primary mirror and made with light-weighted glass, coated, etc., and all electrons, high-speed electrons, etc. Even the mounting is very sensitive. And this is a picture of Pentagon taken by this camera. So you can imagine the Pentagon, you can see all the small things. Further, Cartosat 2 series gives much better pictures. I don't have here. And I also give a glimpse of actually the Chandrayaan 1 terrain mapping camera. So with a single lens, we have 3 views of the same land actually. Because of this, you can create a 3-dimensional view of the moon. So this is what example. You can just see here how the crater also is imaged. You can see here crater. Using this terrain mapping data, we have created people have put a lot of software developments and created a 3-dimensional view. So you can see based on this, lot of science has come out of this thing. So about the moon, just to get a feel of it. So you can go to the, So this is the hyperspectral camera. Here also it is a very compact camera. We can get multiple channels, multiple complete spectrum, 64 bands are created with this small camera using a wedge filter technology, new wedge filter technology. And these are you can see the images and how they have created titanium oxide map has been created. So different bands, how they behave at a given location has been given here at different locations. How the spectrum is coming. So, and if you want to summarize, actually we have made up to 85 sensors so far for in the electro-optical for observing Earth and Moon and Mars. So in various wavelengths, there are so many instruments and so many these things. So there are much more to be done, and all youngsters can join this thing. And one important thing I just want to give you is the miniaturization, how small we can make. You can see here a camera with 36 meter resolution and 150 kilometers swath, 4 bands, was made in 1988 with 150 kg. And same thing with the new technologies and new understanding with new set of people, we could make in 2007 with 5.8 kg, and further it is miniaturized to 1 kg in 2010. So miniaturization is important. So miniaturization, lot of research is required. All youngsters can join and do it. How miniaturization can be done? Because basically you have to understand microbiology, microelectronics, apply all these microfabrication techniques, and if you apply, you can always do, because nature always gives the miniaturized products. So we should understand from nature, we can do it a lot. And you can see, for example, how I am telling nature, see, cat can recognize images faster than supercomputer. So there is no artificial computer which can recognize like cat. So can we understand what cat is doing in its brain? Can we implement it? Similarly, if you see octopus, squid, etc., they actually change the colors instantly. So instead of going for different filters, can we generate these kind of things? And similarly, photosynthesis, the whole lot of process happens and energy is converted from one form to other form. If you can do it, apply it in space research, it will be good. For example, if you see another thing, ant can lift 100 times its weight. Okay, so we have nothing to do till now. Up to this, we have not come up to that actually, very, very far off. So can we understand what is structural design of this ant, and can we apply for space research so that we can do something on moon or some other planet? Similarly, woodpecker drills hole with simple, it's big, small energy impact, but it can create. So can we understand the design and then apply it. So like that, there are so many things, natural things available, which can be applied and we can all understand. Now, if you see who can do it. So it is a team of engineers or scientists have to be done, because you have understood the flavor now. So what kind of team? Team of passionate and dedicated persons who are interested in learning and apply all knowledge systematically, right? And team which goes into details and roots, that kind of team only can do it. But everybody can do it. We all do it in natural, in our requirements. So basically, you dream, innovate, visualize, simulate, and experiment before conclusion. Just like that, we should not talk why it is not done, why it cannot be done. It can be done. It should be done. It will be done by all of us, but with proper understanding and proper study. So that's what. So I wish all of you, the participants, become future space scientists and make India a leader in the space technology. And for that, what we have to do, we have to liberate ourselves from constraints in dreaming. If somebody asks, what do you want? The God comes and asks, we'll say, because my neighbor has got 1 crore, I require 5 crores. Not like that. So you should liberate yourself in dreaming, so that you will get true ideas. Then parallelly, you should become expert in knowledge and skills. So, and not only that, you have to make a team. Then only it can be done. So we have to promote culture of innovation and a spirit of nature, and all these things have to be coordinated. That is what we call align and integrate all efforts to achieve the goals. Like you see, we read so many scriptures. To achieve moksha, what we have to do is the soul and body has to be aligned. Soul thinking something and body something cannot be done. Soul and body has to be thinking, has to be synchronized. So here also we have to do it, and we all have to do it. Like Professor Harsha Gupta has told, it is that synchronization, it is that alignment and integration of all the people together they did. Similarly, the ISRO, whatever achievements are done is because of this kind of teamwork and synchronization of all the people, thinking of all the people together. That's what it can be done. And so to summarize, actually, the space sensor design is exciting, satisfying work. It's the teamwork. It can be done definitely with planning, dedication, learning, and implementation. And so for that, we have to learn like a scientist, open ourselves. Once we learn, but we should be precise like engineers. That is what we have to do it. And thank you very much. Thank you all. Probably I took more time. Sorry. Organizers.
Thank you very much, sir, for such a fabulous talk, covering the basic aspects of space sensors, their functioning, and their connection with space. I'm sure that you have inspired a lot of researchers among students, and they will contribute in near future, contribution to the space science and space technology. So with that, forum is open for question and answer sessions. If there are questions, and especially if students, they want to ask any questions in their mother tongue, and their professors can translate it to the speaker. Questions in mother tongue are also invited. So students, please don't be shy while asking your questions.
Actually, I have given more information to excite them, to trigger them, and they can get more doubts, and they can ask me afterwards also. Because I just don't want to say that you have understood everything in this lecture, because it's only awareness. So interest only has to be created.
So there is one question from chat box, Mr. Melvin. The temperature tolerance of these sensors.
We are not able to. I'm not able to hear you.
There is one question about what are the temperature tolerance of these sensors.
Yeah, each sensor has got its own temperature tolerance. Okay, so some sensors like IR sensors, they work in the minus 200, etc. So 30 degrees to 50 degree Kelvin, whereas CCDs, etc., they can work around 0 to 40, 50 degrees. But even if they work, every temperature, the behavior of the sensor will be different. So for optimum operation of the sensor, we have to maintain it at a very narrow temperature. For example, CCDs, we operate 20 plus minus 5, because what happens is it will have dot signal. The moment it has got dot signal, our SNR will come down. So that's why temperatures have to be this thing. And whereas IR sensors, they are not sensitive at all at room temperatures. They have to be taken to very low temperatures. So each sensor has got its own operating range. And within operating range, we have to optimize for our performance.
Can I ask one question?
Yes, sir. Professor Tucker.
I think data, P-band data and L-band data are not easily available. Are people not ready to develop this L-band camera or P-band camera, or is there any hinge, political or technical?
Which one you are talking about? Are you talking about microwave? Microwave you are talking?
P-band and L-band.
L-band in where? Microwave?
Microwave.
Yeah. No, the technological limitations may be there. It is not that easy, because when you go to lower wavelengths, no, that means higher wavelengths, actually sizes are going to be big. See, for example, if you take visible sensor to microwave sensors, visible sensors are compact, microwave sensors are bulky. In that also, if you take X band, C band, L band, like that, for each of them, the complexity is going to be different. So that's why L band anyway is being done for the ISRO NASA missions. No, they are going to be done.
Thank you.
It is going to be difficult, not easy, but we have to develop. Once we start, it may take 5 years, 10 years, like that.
Thank you, sir. Any other questions among participants? Sir, I have one question.
Yeah, please go ahead.
There are a lot of now CubeSats, nanosats are coming. So how one can, with the miniaturization of sensors, how do you see the potential of the sensors network using CubeSat or nanosat for space science studies?
Yeah, actually that planet, etc. No, they have so many nanosats, etc. So basically, today the mobile and automobile technology has helped miniaturization of these cameras, etc. on the ground. They are available commercially. Now, such things can be used in space, provided you test them properly, ensure their reliability, that they will work in radiation environment, etc. That's why making use of all these things and making use of advantages or advances in optical technology, like they are going for instead of spherical surfaces, they are going for aspherical surfaces. So all these things, that's why they have come, lot of miniaturization has been done. Even ISRO also has done it. Now that miniaturized sensors, now miniaturized electronics, because one is sensor, then the data transmission and data rates, etc. have to be handled. So that's why today there are so many miniaturized sensors are available, miniaturized things are available, even for what we call drones. Compatible to drones also are available. So that's why it is a very good opportunity for the universities to study these things, because basically I gave you, we have to study a lot, we have to understand a lot before you conclude. So most of the times what happens is that study is not happening. So in this case, I just want to tell, actually, the faculty is the basic core. If faculty is interested, they can do the basic work and make use of every batch to do innovations and thinking, etc. But if you leave it to students only, because they have to worry about exams, they do only for small time as a project, it's exciting. But once exams come, because that is the primary thing, so they will forget. So what I actually understand is that wherever it's your institute, we are also involved in some few institutes, wherever staff is involved, they can do it. And staff, means understanding, designs, all these things can be done analysis. If they require, they can tie up with industry or with ISRO to take help and do it. So miniaturization can be done, and all these small nano satellites, micro satellites, and formation flying satellites, they all can be used to do very big jobs.
Thank you.
Future is very high. That's this is the place where our industry and the academia can get involved and apply all the knowledges. So one of the critical things I did not discuss, I just gave only reliability, how to make COTS system reliable. Commercial off-the-shelf systems, either subsystems reliable. That is what one art, actually art or science. We have to understand that very clearly. But there are so much research is being done. So we can also do it.
Thank you, sir. Are there any other questions among participants? I think, sir, there are no other questions. Again, sir, thank you very much for such a highly informative talk, and I'm sure it must have been interest among students connecting sensor and science applications. Now for lunch.
Thank you very much. Thank you. Thank you. All the best to all of you. Thank you.
That is the basic, you can say, definition of climate and weather. Now, I have given my email address also. So in future, if anybody wants to ask anything regarding this, I will be happy to answer those things. So my presentation details are like this. That first of all, I will tell you something about the measurements which are required for weather and climate studies. Then the uniqueness of satellites, because weather and climate can be studied through normal methods also, normal instruments also. But the uniqueness of satellites is there, which makes them very useful for weather studies. Then global effort for meteorological satellites, right from in 70s, meteorological satellites are being launched, and right now major meteorological centers or the forecast institutions, they are using meteorological satellites observations up to a very large extent. So Indian efforts are also there for weather studies, and satellites are helping in forecasting the weather as well as some long climate studies. Okay, then to know something about the weather and climate, you should have something which is very interesting. So the applications which are interesting for the common man, that I am going to tell. Then what are the challenges in weather forecasting? That means there are still many things which are yet to be solved in weather forecasting. Means many parameters are yet to be measured from space, and up to a certain resolution, what is to be measured, that is also a challenging still. So opportunities lie ahead to find solutions. Naturally, for young students, the opportunities are there to solve these challenges or problems as far as weather forecasting is concerned. Okay, now to start with, I will tell that there are certain weather parameters, or you can say to start with, these are the parameters, the studies of which can tell us what is the weather today at a particular location, at a particular city, or in a state. So temperature, humidity, rainfall or snowfall, winds and clouds. Now, apart from that, I forgot to write, there is one more important parameter, that is pressure. So these parameters are to be observed and monitored closely at a particular place as well as globally, to know what will be the temperature or the humidity or the likelihood of rainfall or wind speeds or cloudiness at a particular place. So these are to be measured either through normal, or you can say conventional methods, or through satellites. So these are the, you can say, the building blocks of weather studies. Now, how satellites are useful in making those studies is its uniqueness because of its coverage. So naturally, the area which is observed by satellites is unprecedented, and it is quite large compared to the conventional measurement of the atmospheric or the climate parameters. So then the inaccessible locations like valleys, mountains, cloud structure. So the places where human beings are afraid to go, you can see or observe those places and observe those parameters through satellites. So that is the unique advantage. Cloud structure over cyclone. Now the cyclones, as you know, it's a very organized structure of clouds over oceans. Normally they are being generated or they are developed over oceans. So if there is no satellite, it is very hard to observe how these clouds are organizing, how they are moving ahead, or they are dissipating or growing. So these things are very hard to observe through conventional means. So the satellites are really very helpful, and I will say that as far as cyclone studies are concerned, satellites are the boon for such observations, and not only observations, forecasting of cyclones, its landfall as well as its intensity. They are a very handy observations by satellites, and many casualties are avoided because of these satellite observations and forecast. Now, vast ocean. Naturally, the conventional means by ship observation or by boat over oceans is really, you can say, a very far-fetched phenomena as far as ocean observations measurements are concerned. So while on through satellite, you can do it in few seconds. Whole ocean can be mapped. Now, harsh desert. Naturally, this is again a challenge for observing temperatures or humidity or winds over very harsh places like deserts. Then dense forest. So these places which are very scary to measure by human beings, satellite observations are very handy for such measurements. Frequency of observations. Yes, again, satellites become a, you can say, a very unique observational instrument as far as its frequency of observations is concerned. So if you want to know a temperature of a particular place 2 times a day or 3 times a day, you just increase the orbital frequency of the satellite. So if you can lower the height of a satellite orbit, you can increase the frequency of observations. While if you want to do it through human being or manually, it will be a tremendous task to do that. So frequency of observations can be very easily, not very cost effectively, but it can be controlled through satellites. 10 types of observations. Yes, naturally, subsurface soil of moisture, temperature of few microns, thick layer of ocean, cloud top temperature. So the places where humans observations are nearly very difficult to take, like subsurface soil moisture. So you have to dig the soil to get that observation, while satellites can do it right from 800 kilometers or even 36,000 kilometers above the earth. So these are the uniqueness of satellite observations, which are making it indispensable. Now, this is a just to tell you that this is the first global cloud coverage by satellites, and that was called Tyros N satellite. And you can see that nearly 2/3 of the globe is covered by satellite during this time. So globally, there may be something around 50 weather satellites which are hovering over Earth to take care of different nations as well as different states to monitor the weather over their countries. India's also INSAT series is there around 83° east. Right now you have INSAT 3D and 3R at 83 and 64° east latitude, longitude. Okay. So these are the Indian meteorological geostationary satellites. Naturally, geostationary satellites are required for weather studies as well as communication satellites. Communication because of its stable position with respect to Earth. So right from 1982, when INSAT 1A was launched, right now you have INSAT 3DR working, which was launched in 2016 with the latest visible infrared sensors onboarded and making a very good observations over the Indian peninsula. So this is again a slide which covers INSAT as well as other satellites also, which are used for meteorological studies. So the left side is showing you what are the INSAT or the geostationary satellites are being used for weather studies. The right side shows you the polar orbiting satellites. So OceanSat 1, which was having microwave scanning radiometer, plus ocean color monitor. OceanSat 2 was also having, along with these two sensors, spectrometer also was there. Megatropics, which was the low Earth orbiting satellites, which was having a Madras, Scarab, Sapphire, and Rosa. 4 types of sensors were there. In 2011, it was launched. And right now, INSAT 3D and 3DR, they are the workhorse as far as satellite observations are concerned over Indian region. It is having imager and sounder. I will tell you its applications and the parameters which are being routinely developed from SAC, Space Application Center, Ahmedabad, and the whole package is being transferred to IMD, India Meteorological Department, and they are being routinely generated to give synoptic or numerical weather prediction modelers for weather forecasting. SCATSAT is a another satellite which measures wind over oceans. So scatometer is an added advantage for India. Since 2016, it is measuring wind speed as well as direction over oceans. OceanSat 3 is likely to be there in 2022. This year, it is likely to be launched. Saral Altica 2013, it is a Ka-band altimeter which was there for ocean studies. Now, this is to further elaborate the polar and LEO satellites for weather studies made by ISRO. These are, as I have already told, OceanSat 2 Megatropics and Saral. OceanSat 2 was basically for ocean studies, and it has means ocean color monitor, which was there for measuring the basically the chlorophyll over oceans for the potential fisheries zone prediction. Okay, then Megatropics, which is having 4 sensors: Saphir, Scarab, Madras. There was one more called Rosa. Saphir was there for humidity profile. Scarab was there for radiation budget. Madras was there for the wind speed, water vapor, and integrated water vapor, cloud liquid water monitoring over oceans. So these again, Saral was there for ocean studies, and basically the sea level height was the major parameter which was measured by Saral. Now, as far as the regular monitoring of the weather parameters over Indian region is concerned, it is done by geostationary satellites. And right now, which I have already told, the INSAT 3D and 3DR, they are the major provider of different meteorological parameters. These parameters are listed here. Its applications are also listed here. So I will tell you one by one how they are being, and the images are also I will show how they are being generated and used for weather monitoring. Now, geostationary satellites are indispensable for weather services. Yes, that is the slide which is showing that geostationary satellites are very important for weather studies compared to the polar orbiting or low Earth orbiting satellites, because the polar orbiting satellites provide high spatial resolution but poor temporal sampling. So that means you can increase the frequency of observations through polar orbiting satellites, but their temporal sampling or the timing is very poor. So, okay. So, I will phrase it like this: polar orbiting satellites, they can cover more area, okay, but the temporal or the time frequency is poor. So that is the constraint in polar orbiting satellites. Geostationary satellites provide poorer spatial resolution but high temporal sampling. So here the idea is that since the sensor or satellite is stationary with respect to Earth, you can switch on or switch off the camera as and when you want. So if you want to take an observation, you just simply switch on the camera and it will take a snapshot of the whole Indian peninsula when it is, I'm talking about the insect. So, but only thing is, since it is 36,000 above the Earth, the sensors which are seeing the Indian region, they have a slightly poorer resolution than the surroundings. So the frequency of observations can be through geostationary satellites, while the spatial resolution can be improved through polar orbiting satellites. So right now, the combination of these two will give you a good weather service. Now, for example, these are the images from INSAT 1D taken in 1996. This is the onset period you are seeing. So you just keep a watch over Kerala region. You just see it's a very huge, thick cloud mass over Kerala region. And this is the time when the Indian monsoon onset is there. You just see the date of the observation, that is 28th May. So, which is almost coinciding with the onset of the monsoon, which is something around 30th June or 1st June or 30th May. So, the cloudiness shows you the onset of monsoon. Break period, here you are seeing that when there is a monsoon break, the cloudiness goes to the foothills of the Himalayas. So you are seeing the very thick clouds over foothills of the Himalaya. The active period of the monsoon is having full of cloudiness over whole peninsula, and so the active monsoon period is around 13th of July, when you are seeing lots of raining clouds over central India and west coast of India. So these are the examples of how the cloudiness can be studied through satellites. These are the satellite sensors specifications, different specifications for visible, water vapor, thermal infrared, in INSAT 3A and Kalpana. They are the earlier satellites when we started making the sensors for meteorological studies. Here, one thing is to be emphasized: CCD camera. Now, this was a unique sensor which got a lot of you can say boost from Indian weather studies as well as the farmer community because of its resolution and the type of bands it was covering. So very unique type of observations and applications were initiated using the CCD camera observations. This is again first images from Kalpana 1, visible, IR and water vapor. You just see visible. So lots of clouds are seen over Indian Peninsula. IR, that means it is giving you the temperature sense or the temperature tendency of the whole earth. So the area which is darker in shades, they are supposed to be more warm, while in the whiter area is the colder regions. In water vapor, you are seeing the water vapor concentrations as far as this white and black gradation goes. So the area which is very black is devoid of water vapor, or you can say very less density of water vapor, while the white coloration or white gradation gives you the idea of high water vapor concentration. This was a CCD image taken by INSAT, and which was very useful for many studies in agriculture as well as weather. Now this is the you can say right now the products which we are regularly generating through inside 3D and 3DR, and right now they are being generated every 15 minutes because we have two satellites over Indian region. One is inside 3D, another is 3DR. So every 15 minutes these observations are made, and the numerical weather prediction models are being given data to assimilate. So insolation.
Dr. Alok, our
Yes.
request, can we wind up within 5 minutes because that we are already late and another speaker is waiting. If you can, within 5 minutes.
Not 5 minutes, but 10 minutes I will finish. 10
Please.
minutes I will finish.
If possible, please go quickly.
Okay. So these are the actually you can say the menu card of inside 3D and 3DR parameters generation. So you can see that all types of observations or the products are made. SST is also there over oceans. You are seeing sea surface temperature. This is QPE, the quantitative precipitate estimation. Aerosols over India, fog, which is for aviation or this thing, aviation industry, HE rain, fire and smoke, and snow. So all types of weather parameters are generated through 3D and 3DR. These are different sensors characteristics. This will I will skip. Now over oceans also, it's a huge satellite input for the ocean state prediction, and you can see this sea surface salinity being mapped through satellite observations. This is significant wave height, and the this is the state forecasting system which gives the ocean state conditions. So that means there you will get sea surface height, sea surface wind, sea surface salinity. For every 3 hours you get these parameters. So many things like sea state conditions can be monitored using these prediction models. Now this is again a fog studies image, and this is right side is the temperature profile by inside 3D3DR. This is weather prediction using satellite data. So even short range weather prediction, monsoon prediction, and now casting. All three scales of monsoon, the weather predictions are being developed, generated, and being broadcasted through Mosdaq site of SAG. So the weather studies are, you can say, very much enhanced due to satellite observations. And what I already said, the tropical cyclone prediction has vastly improved due to the satellite observations, and not only landfall, its intensity, its generation, and the time when it will hit the landfall. It gives a
Hello. Hello. I think he has lost the connection today. Hello, Dr. Alok.
Yes, sir, I think.
Yeah. Chintamani, you can call him.
Sir, I don't have his number. I'll just check.
हाँ.
Hello.
Dr. Alok, are you audible? Hello. Dr. Alok Mathur. His call is also, he's not responding on phone.
The person who has called is speaking to someone else. You can wait or call again later.
I have informed him, Jain sir.
Yeah.
I have
So-
informed him just now. So he's just trying at his end.
Okay.
Otherwise, what we can do, we can start with the next speaker, so that if there is some remaining slides, maybe tomorrow if we can adjust that.
Yeah, or the next speaker can finish fast. So after that, we can take our today if time permits. Is it so? Is it possible? Next speaker is Dr. KG Srijay. Yeah. Dr. KG.
That's right.
Srijay Lakshmi. Yeah. So Chintamani, you can take over and ask.
Okay. So is Srijay Lakshmi ma'am there?
Yeah, I'm very much here. Am I audible?
Yes, ma'am. You're audible. I think
I think our Mathur sir is joining back.
I think there is some issue with his internet. I spoke with him just
Yeah,
now.
but now he's joining in his iPad, I suppose. Sir, please unmute yourself, sir. Please unmute. You're on mute.
Okay. Now I'm able to be heard.
Please finish fast, sir. Dr. Alok.
Okay. I think I'm nearing.
You are showing the cyclone things.
Yes. Hello.
Yes.
Okay. So these are the visible image showing you the different types of applications by visible image. These are actually the different applications which can be attempted by different images of shortwave or visible or IR. So that is being shown here. I think I can skip those things. Detection of daytime fog. This is important as far as aviation industry is concerned. So daytime fog is very much useful for them for knowing the fog conditions over the region where they can avoid by either landing or takeoff time. So okay, these are different the parameters which are being generated. Okay, this is the place where I can tell you that they are the users of Insight 3D products. So the synoptic forecasters, aviation forecasters, the modelers, and agriculture, as well as energy. So the wind mapping gives you the idea from where you can have the wind resource or the wind mapping, so that you can tap the wind energy. These are again for climate studies also. This different parameters can be measured through satellites. Okay, this is for this thing. Now I will come straight to the data assimilation, tropical cyclone. I think it is already covered. I will come to the challenges. Severe weather, cloudburst, madras, scattered wind. These are actually, this is also somewhat important, that the climate studies, how India is contributing to different observations for climate studies. Wind energy. Okay, this is the slide which I wanted to tell, that what are the challenges still lying ahead in weather prediction. So the challenge is the amount of available data. That means the model resolution, data from satellite, ground, interpolation in gaps due to time and space. So the type of gap, that means the satellite observations as well as the conventional observations, they don't have the global coverage fully covered. So there are some gaps in between, and that is to be filled. Now that is still a challenge. So where you don't have any observation, how to interpolate, extrapolate that observation. So that is still a challenge. Time available to analyze it. Naturally, the computers are although very fast nowadays, but the prediction also has to be very fast. So if you want to forecast a weather system, you have to be very fast in analyzing. So that is also a challenge. Then complexity of weather events, rain in mid-latitude and tropics, some interactions or cloud. Now the complexity of weather events. So as you know that in mid-latitudes, rain occur because of thermal gradations, while in tropics it is the convection which is predominant in the rain fall, or you can say the rain production. So the mechanism itself changes in different locations as far as weather is concerned. So digitizing weather. Now the digitization of weather, that means how you put all the observations into a model. That is also a challenge. That means how you can mimic the nature. So which is still, so there are so many other processes which are still unknown to the human being, and we are not able to model it in order to perfectly forecast. So these are the challenges which are yet to be met fully through satellites or even through some science. So now I will tell you there are some, okay, yes, these are the parameters which are yet to be measured through satellites, like surface winds over land, surface pressure, now direct measurement of sulfur dioxide, other polluting gases. So these are some of the major challenges which are, so that means the sensors are yet to be developed for measuring such parameters, cloud evolution, development, decay or growth. So these things are yet to be known in a perfect way. Can machine learning, artificial intelligence, and advanced data analysis techniques solve these problems? You to explore. So that means these are the challenges, and yes, the new techniques of machine learning and artificial intelligence, if the younger generation try to put these problems into such kind of learning or tools and find out whether they can solve these problems. So this was my, you can say, thought for you to explore. Acknowledgement in the last that yes, AC Mathur for conceiving the idea and providing the opportunity to share my thoughts. Colleagues of our MOG group in Space Application Center, who were architects of such state-of-art geophysical products from Indian satellites. Thank you.
Thank you very much, sir, for such an enlightening talk, talking about the real application of the satellites to weather and the geophysical sciences. If there are any questions, we can just quickly take one or two questions. Any questions from students? Okay, so I think, sir, if there are questions later, we can take them from students and we will forward it to you.
Correct, correct. Okay, yes, yes. Mm-hmm.
Thank you very much, sir.
Thank you, thank you, thank you. Mm-hmm. Thank you.
Thank you, sir. So we now move to the next session of this event, and it's my so the next talk will be on space biology application challenges and opportunities by Dr. Srijalakshmi, who is associate professor at IIS Tiruvananthapuram. So, ma'am, it's great pleasure to have you, and I request the professor from JB Science College to officially introduce the current session speaker.
Good afternoon, everybody. Respected dignitaries, esteemed resource persons, beloved principal, learned colleagues, invitees, delegates from different parts of the country, and dear students. It gives me immense pleasure to introduce the speaker for the session, Dr. K.G. Srijalakshmi, Associated Professor, Department of Chemistry, IIST, Tiruvananthapuram. Madam obtained a PhD degree in the year 2006 from University of Kerala in chemistry. Immediately after PhD, Madam joined her career as a postdoctoral researcher at BMT's SCTI MST from December 2006 and served till 2007 September. The interested area of research are combinational organic synthesis, smart materials, drug discovery and development, dendrimer and supramolecular chemistry, functional materials are for Theranostics and space applications, gravitational biology and space life sciences. Madam has served at different positions in the Department of Chemistry, Indian Institute of Space Science and Technology, Thiruvananthapuram. She served as a reader from September 2007 to 2010 as an associate assistant professor from May 2010 to August 2016, and at present she is working as associate professor in the department. Madam published over 60 papers in various journals and conferences of national and international reputes. It's proud to announce that Madam is the owner of 4 patents. She gave lecture over 70 seminars, conferences, and webinars. She guided many research students, among those who have been awarded as KLE. She guided more than 25 PG and UG students for projects. She awarded as the best paper presenter for 7 times. Some of the achievements I would like to mention it here. Received doctoral and postdoctoral fellowships from CSIR Government of India. She is the member of Faculty Funding Committee of IIST, Thiruvananthapuram, and was involved in all infrastructure development of institutions. Under her leadership, space biology proposal got recommended for the first human space flight program of India, Gaganayana, and also involved in space flight hardware development for other institutions. She is the member of Committee for Vision Plan for Microgravity Science, ISRO, Government of India. She is also member of HRDG Microgravity Subgroup, ISRO, Government of India. She is the member of several national, international professional bodies such as ACS, ICNM, MRSI, IEEE, etc. She is the reviewer of several international journals. She worked as the organizer of workshops, conferences, webinars on material sciences, computational chemistry, astrobiology. It's my great privilege to welcome Madam once again on my behalf and behalf of our institution and our society to this August gathering. At the same time, I use this opportunity to express my thanks to the organizer for giving me opportunity to introduce and present before you such a wonderful personality. Thank you very much.
Thank you, Dr. Angadi. May I now request Srijalakshmi ma'am to take over. I think we have some network problem. So speaker will be soon joining as there was some network issue. Just give us some moment. Since there is some network issue and so we might start with another talk as speaker has just suggested. So just give us some time. We are just figuring it out.
Chintamani, I think you should take next speaker if possible. Already we are delayed more than 1.5 hours.
I am ready.
Professor Himanshu, he will be talking. So meanwhile, in the background, Professor Veena was trying to coordinate with him. So, so he has agreed so that once he does, then we can go with Sivaraman sir.
Yes. We make Mr. Sivaraman timing was 15:15, 3:15.
So we'll have to, sir. We will adjust, sir, time slot.
Okay.
Now, if possible, I would like to take up because I have to go somewhere. I'm very expired and that will be better. Just a request.
Okay, sir. Just give me a moment.
Yeah.
Sivaraman sir, I think we will start with your talk since you have to go out, you
Yes.
said.
Yes.
So,
Thank you. Thank you. Yes.
Yes, sir.
And Veena madam will be loading it. Center. I request Veena Madam to load my presentation.
Okay. So due to some internet connectivity issue with the current speaker, we are now moving on to the next topic by Dr. Sivaraman. It's my great pleasure to have Dr. Sivaraman sir as a part of this event, and he will be talking about applications, challenges in orbital mechanics and opportunities. And so we are very fortunate to have you and your expertise. I'm sure all the students will be benefited. And with that, I invite Mr. Satosh Gorfade, who is Assistant Professor at PC Jabin Science College, to officially introduce our speaker.
Thank you, sir. Thank you, sir, Chintamani, sir. Respected sirs and students and faculty member from the different colleges and universities of India, Karnataka. Yes. Now it's an honor to introduce the speaker of this session, Dr. M.R. Shivaraman. Dr. M.R. Shivaraman did his MSc in the Applied Physics from Government Victoria College, Palakkad, Kerala in 1966, and thereafter, sir completed his PhD in physics from the Physical Research Laboratory, Ahmedabad, in the year 1974. And later on, he took his PhD on the topic of the topside sounding of the ionosphere from the same institute in the year 1974. And later, sir has joined to the this ISRO Ahmedabad in the year 1975, and later in the year 1988 he joined to the another field, that is System Application and Engineering Group in the satellite communication area in the SAC, that is Space Applications Center. And in the SAC, sir has means adopted so many different positions and developed many of the applications, and especially sir has worked as a deputy project director of Gagana project, and sir has many publications in the scientific in national and international paper during the last 50 years. And sir retired from ISRO in the year 2007, and presently sir is actively participating and working with the space tech consultants in the Ahmedabad. And with this brief introduction, I present before you the esteemed speaker of this session, Dr. M.R. Shivaraman. Over to Shivaraman, sir.
Thank you.
Yes, sir.
I request Veena Madam to load my presentation.
Hello.
I request Veena Madam to load my presentation. She said she will load my presentation.
Okay, sir. Okay.
Is she there?
Yes, sir, she's there. She is loading the present.
Okay.
Sir, we didn't get PPT, sir. Hello, sir. Is it
Hello?
audible, sir?
Yes.
Sir, I didn't get your PPT, sir. I have messaged you.
You are loading?
No, sir, it is not possible, sir.
Any problem?
No, sir,
Sir, can you?
I didn't get your PPT, sir.
You have not received?
No, sir.
No, I sent to your email address, Veena.
Maybe you can check in your spam if it has gone in spam
Just
folder.
a moment, sir. Just a moment, sir.
You said that you have received and
No,
loaded.
sir. Sir, no, sir, I have not received yet, sir. I called you, sir, but you didn't pick the call.
Okay, I will resend it. This is Veena madam, no? Hello?
Veena madam, sir. Veena.
Okay, okay.
VeenaPHY.E, sir.
Okay, okay. Just a minute.
Yes, sir. Just a few, just you share it, sir. A few minutes we will do it.
Did you receive?
No, sir.
No, sir, not yet received.
Sir, if you can attach it in WhatsApp, it will reach faster.
Yeah, I will send it WhatsApp.
Sir, we received, sir. We received, sir.
Hello?
We received, sir. Your
Okay, okay, okay. Is it there?
It is there, sir.
Okay, just load it.
1 second, sir. Send note.
Because I am not familiar with loading.
Shivraman, sir.
Yes.
You have not attached the file, sir. Simply the message came, sir. You attach with the mail, sir. You attach with the mail.
What is your email address? Veena at?
Sir, or else you send it to Santosh P. Santosh 12 PG.
Yeah.
SANTOSH.
Shivaraman sir, actually,
Hello.
Dr. Srijal Lakshmi is back. So meanwhile,
Okay.
meanwhile you are sending it to Professor Veena, we can
Okay.
start.
Okay.
Srijal Lakshmi's talk.
Okay.
I'm sorry for the inconvenience.
No, no problem.
Dr. Srijal Lakshmi.
Yeah, I'm here. Thank you so much, Shivaraman sir, for that kind
no
gesture. Because yeah, because we are having a heavy thunder shower here, so all the networks actually failed. We had gone for a restart. That's right. So can I start sharing my screen now?
Yes, ma'am.
Yeah, one second. I hope you are seeing my screen now. The slide one, is it?
It is okay. Make it full screen.
Yes.
Yeah, I hope now it's visible. Yeah, okay. So without losing much time, I will start with apologies for having that mishap there. Okay, so nonetheless, we are here now, and I am extremely glad to have this invitation from the Indian Space Industries Exhibitor, Ahmedabad, and especially Mathur sir for this kind invitation, and PC Jabin Science College, Hubballi, for arranging this wonderful seminar session. And it is more important because it is entitled Awareness Webinar, which is excellent one, because it's very important to make the students of the coming year aware of the opportunities coming up. So in this particular seminar session, I will be talking very briefly on space biology, an emerging domain in the context of Indian space program, as well as the applications, the challenges and opportunities. And before I start the session, I wish the greetings, I extend my greetings to all my fellow Indians on the Azadi Ka Amrit Mahotsav, our Indian independence 75th anniversary celebrations. So here we go. So as to give a very brief outline of my institute, you may be familiar with Indian Institute of Space Science and Technology. It's a very young institute set up in 2007 under Department of Space, and it functions as an autonomous body under Department of Space, and it is covered under UGC Act 1956. And this is the place from where I am now talking to you. This is the front view of our institute, and it is located near to the southern tip of India. So our institute is unique in its vision to be a world-class educational as well as research institution, and we would like to contribute significantly to the space endeavor. So that makes IIST different from other universities across India. So for you people, what is in my gift box? So my gift box today I have packed and wrapped with these many topics. Although they are going to be in very brief, I'm sure that it is going to encourage few of you to explore into the unexplored domains in space laboratories, especially in the area of space biosciences. So how do we and why do we need to support life in space? And in that, I will talk about space biology, the rationale of that particular subject, and the challenges that the upcoming generation is expected to overcome. And of course, we are looking into the prospects and opportunities for learning as well as research in this emerging domain. And in this line, what are the initiatives that at IIST, my group is actually looking into currently, and of course, the future directions, whatever is possible. So when I framed this particular talk, my target audience, as usual, are the passionate space enthusiasts and the budding researchers that are attending this particular talk today. Let's move faster now, and you are all familiar with these space stations, or what we call as space laboratories. Starting from the world's first space station launched in 1982, that is the Salyut, the USSR's Salyut, the currently getting assembled Tiangong. We do have nearly a dozen or more of space stations, But currently, the functioning ones which are available are only the ISS, the International Space Station, and the Tiangong. And very recently, the life of this International Space Station has been extended till 2030. That's a good news to people who are actually looking into the space exploration and space experiments, because these space laboratories are in fact a very unique feature of the space exploration, and it actually helps us to equip ourselves with the know-how and the knowledge, as well as the futuristic requirements for the deep space explorations as well. So in that context, we can actually consider the space stations or space laboratories to play a very critical role in transforming our views about the long-term survival outside Earth. So there are questions, why should we travel out and settle and all those stuff? I'll not be addressing those things here. But whichever is available here and whatever we are going to set up, these laboratories are unique, and unique in the sense that they will actually help us to broaden our understanding of biology, physics, the fundamental sciences, as well as astronomy and engineering. So if you ask me whether these are only objects of scientific interest, of course, no. These are also objects of great power competition, as well as building social relations and international collaborations and cooperations as well. So it's a huge an independent. You cannot independently exist when you are doing actually space research. Okay. So when talking about space biosciences or space life sciences, what does it typically mean? To give a very generic, or to give a very fundamental explanation to that, we can actually talk about space bioscience as the study of biological specimens as well as biomedical processes happening in these live specimens. By taking these live specimens as experimental subjects, you take them to space and study what are the changes happening. So now coming to the definition for live specimen. In fact, the definition of life is what we know as living beings on Earth. We have our own definitions for life, but we are not pretty sure whether this is the definition for life which is existing elsewhere. Okay, that is just a cosmic perspective of the subject called astrobiology, but we are here talking about space biology, where this live specimens from Earth is being carried to space to find out the changes which are happening. So if you want to define something to be a live specimen, of course, these 6 attributes will help you, including the movement, organization, homeostasis, energy production, as well as consumption, reproduction, as well as growth. Okay, so what is that which makes the space biosciences unique? Of course, the space biosciences is made unique as well as challenging due to the following attributes of the space as the laboratory. And as you all know, when life emerged in the planet, in this blue marble, we do have something called a very, focused and oriented directional stimulus, what we call as the gravitational force. And when we move away from Earth, due to this distance, because it is having an inverse proportional to the square of the distance, that we are actually depriving ourselves from this directional stimulus, out of which most of the body functions of the living organisms are have been evolved. And apart from that, there are other unique features of this space laboratory. For example, you will not be finding the sedimentation process. So the loss of sedimentation, the density-driven convection, you cannot have a normal convection over there. You have to force convections in the space laboratories. Other than that, diffusions, especially those due to mechanical forces, are actually prevented. And above all, there is something that is unique, what you call as Marangoni convections, that are unconventional sort of convections that are uniquely found in Earth space laboratories. So all these people, they collectively attack you when you are trying to do some experiments on board space stations. Okay, so let us not worry too much about those things. But at present, what is being explored in the space biology domain elsewhere, and in the International Space Station, which has been inhabited for more than 2 decades by now, a lot of experiments have been conducted with reference to the human body, the plants, the animals, the food, the habitat development, so on and so forth. And when we look into the early years of space biology research, in fact, we were trying to find whether the living organisms are able to survive space flight. And during so many research years, as years went on, we now understand that not only animals, humans, plants, they all can withstand the exposure to the so-called microgravity or near weightlessness, as well as the cosmic radiations, the cocktail of several radiations that are attacking you from different sides of the universe, and also the rigors of launch and re-entry. So we now know how to make the specimens safe inside the habitat and experimental enclosures that we are sending. So with a lot of experiments and information from that on a macro level, currently the focus on in the space biology research is on the understanding the biological changes at the cellular as well as the molecular level. So I emphasize this point. We need to understand the biological changes that are occurring both at the cellular level as well as the molecular level during and after spaceflight. So this is the aim with which we have to enter into the realm of space biology, because there are so many groups which are already having a lot experiments being done in these space stations. So when we consider space as the laboratory, or in fact, to be more precise, space as the bioscience laboratory, now the question pops up, where does really the space begin? So we do have different definitions for space. Something crossing the Van Allen belt or von Karman line. So many things are there. But here, with respect to this particular lecture, I would like to emphasize that here the topic that we are discussing is with respect to biology. So I have to emphasize more on so-called the physiological space. And if we look for a definition, we can actually think about it as just with this starting just beyond the biosphere. So biosphere is that part of the universe which includes the atmosphere, lithosphere, and hydrosphere, where the life can survive without any artificial support. But once you climb up, with the increase in altitude, there happens to be having many changes, especially with respect to the pressure, amount of gases present. So by crossing some 18.28 kilometers, we understand that without an artificial life support system, what we call as a spacesuit, we are unable to survive ourselves. So this altitude of 18.28 kilometers in a way qualifies to be called the physiological space, but even at that altitude, there is a finite pressure of 54 millimeter of mercury existing, and that actually vanishes when you cross some altitude beyond some 82 or 84 kilometers above the Earth's surface. So whenever we talk about space life science research, the general objectives, the first and foremost, as I have already mentioned, is to study the effects of the exposure of microgravity on biological systems. And why do we need to understand the effects of exposure? Just because human beings are being inquisitive, they want to explore the unexplored. So we always look into something called explorations, human space flights and deep space exploration. So we need to understand what are the challenges, what are the risks that we are going to face, and accordingly, we can plan for, or we can strategize some mitigation plans. So the second aim is to have the use of this microgravity environment to broaden the scientific knowledge about the influence of gravity on living systems. This is something, a wonderful science I would like to tell you, because this is what you call as the gravitational biology. So this is something because we evolved in the force of this particular gravity, and what happens if it is lifted or if it is actually altered with respect to the biological systems which have been refined over this 4.2 billion years of existence. So there is something called emerging, which is called biospace forming. This term, I would urge our student community out there to please make a note of that, because whenever our life is actually subjected to a different environment, it has its own adaptation mechanisms to get adapted to the existing environment. So when life gets itself adapted to the space environment, this is what we call as biospace forming. So this is an emerging area you can explore more. Okay, and if you consider the history of space as a bioscience laboratory, you see not only the space flights, they started simply from balloon flights. You can see 1946 to 47 from New Mexico, the launches of balloon flights happened, then followed by a series of V2 rockets, this and that. I have not put everything here. If somebody is interested, of course, this particular journal link will actually help you to understand what all experiments have gone in the history of this space as a laboratory, and several biological species. Here you see fungal spores, fruit flies, several systems have been studied, mice, monkeys, this and that. In fact, no, we should be thankful to the thousands of animals actually who sacrificed their life so that people could get some sort of so-called confidence in conducting this space explorations, human space explorations. Okay, this is something that I am 100% sure you all will be knowing. This is a huge orbiting laboratory in space, what we call as International Space Station, and this is the only laboratory currently actually 100% functional, and it is visible to our naked eye. If you go and visit the site that is Spot the Station, it is actually hosted by NASA. If you type that Spot the Station, the one web page will come up. You can enter the city in which you are currently staying, and the website will give you the details of the sightings of this International Space Station. It is like a lantern which is flying over your homes. Okay, so you see how huge is this laboratory, almost like the size of a football ground, and the dimensions, and you see the mass. Over 419 or 420 tons, and with different habitable volumes, and you see millions of computer codes, this and that, power generation, all stuff. Okay, so this is one of the marvels, engineering marvels that humans were able to build in space. Okay, so once we build this marvels, what else is done in this laboratories also we need to understand. So as on today, the program, the Expedition 66 is just started 5 days back. That is something which is in progress, and it is a joint venture by NASA and Roscosmos. Roscosmos is the space agency of Russia. And here, it will go on, and these are the crew members are happy reaching in the orbit. Okay, this is in the LEO orbit, 408 kilometers, and approximately 19 orbits. It completes 19 sunrises, sunsets. People are able to visualize from this International Space Station. And with respect to this particular lecture, what I want to emphasize is more than this fascination, the research in our orbit has been there continuously for the past 21 years, exclusively in ISS. And you can see nearly more than, or not nearly, actually it is more than 3,000 scientific experiments have been completed on the International Space Station, especially by these 7 agencies. They are going hand in hand. And if you look at these experiment numbers in hundreds, you see that the biology and biotechnology experiment is something which is dominating research in the International Space Station. So the different members and this DOI for this article is provided. I would urge again the student community to explore and understand more about that. I'll be available for discussions if any you are having in this regard. And let's continue with the research in orbit, just to put a few glimpses. And on the extreme left, you are seeing the Christina Koch. She has been having this record for having the single longest space mission by a woman to date. And then we are having something called International Space Life Sciences Working Group already there, with the 7 agencies going hand in hand, and several experiments. I have picked a few of them which are relevant to this particular talk, and biofabrication facility is one among a very important facility where they test a lot of biological experiments, and the 3D printing of organs are happening there. Then you are having botany research hardware, and the veggies, greens are being grown there. And to continue further, the growing of the greens is not at all easy, but they are going to be the game changer for the deep space mission. So the partnering organization, space organization, takes a lot of effort to produce these growing greens to support the deep space missions. So you see, all are smiling when you are seeing something in the space laboratory. You really brings smile. So in order to help the psychological, conditioning of these astronauts or the space travelers, also this growing greens is actually very important. So people in the agricultural domain has a lot to do, lot to contribute in this particular research. And definitely when you are talking about the research in orbit, one thing that we cannot just ignore is to have international collaborations. Okay, so apart from having our own indigenous technologies being developed in our own countries, definitely the research has to have a component of international collaboration. Again, you can see this. Fortunately, I have met this already in person. So we have this NASA and this cosmonaut, Russian cosmonaut. They are installing an hardware for conducting this. It's a glove box to conduct some of the biological experiments. And here you are having this hardware being fabricated or is taken out for implementation for biology experiments. Here also what you call as the multi-use variable gravity platform, MVP. This is being installed inside the Kibo module of JAXA. And you see the NASA astronaut is actually doing that particular job. And here also there is something called Life Sciences Glove Box, that is exclusive facility to conduct life science experiment, because you have a sort of a containment zone or a contained environment where you can actually conduct the biological experiments without much of contamination of the other side of the modules. So these are all things which are really going on in the space laboratory, and all of which are actually part of the space biology research. So why should we think about this particular aspect with great enthusiasm? Now, the great enthusiasm is definitely backed up by a very, very big, in fact, it's a huge announcement from Government of India announcing the program of the India's first human space mission, what we call as Gaganyaan, and the fully autonomous 3.7-ton spacecraft will be carrying a 3-member crew to the LEO, approximately 404 to 406 kilometers. And we aim to bring these crew members safely back to Earth after a mission duration of up to 7 days. So the strategy and all what are discussed are actually mentioned over here. I'm not going to the details. What I want to emphasize, because this is an awareness program, so I wanted to emphasize to the community sitting over here that from ISRO's well-established capabilities of having or modern space transportation systems, satellite systems, and space applications. This is an area where they have contributed enormously. Now, from the existing capabilities, ISRO has to grow further, and then we have to explore something new, which is called the human-centric domains. So in this area, the support from the whole of the country is actually very, very much required. For example, to build human-rated platforms, building up of facilities for astronaut training and other biomedical support systems, then life support technologies, everything we have to build in our own country. Definitely we can get the knowledge and the support from other countries, no doubt about it, but we have to have indigenous technologies. And I'm 100% sure the country is blessed with people who are actually having high potential to achieve each and every job which we want to pursue in the coming future. So this is one area where definitely all can wet their hands and learn something new, exciting, and less challenging. So one more announcement is that preceding the human space flight, where the real crew members will be traveling, there will be 2 developmental flights, which are actually supposed to be the experimental flights to to assess the performance of the space flight. So what is that beauty of such developmental flights? The beauty is about the opportunities that such flights are giving us, especially for space science and technology development experience. So this is another area where you people can really work and find something very, very interesting research. And definitely when we take life into space, there are several hazards that are awaiting us, and we classify them into the space risk. And the NASA has actually classified the 5 of them here itself, with respect to distance, confinement, the closed and hostile environment, deprival of gravitational forces, as well as the radiation hazards. Again, all the risks and consequences that is mentioned over there. For paucity of time, I will not go into the details, but to give an overall view, that is the extreme environments, when we are actually traveling away from Maki Godse, when we are traveling away from our mom, our life is challenged by extreme environments. So the lower gravity levels, as well as the cosmic radiation levels, as well as the distance away from Earth, we don't have anything other than what we carry from Mother Earth. So you don't have any air, you don't have any food, you don't have any water. So we need every of these commodities for our survival. So you just imagine that you are deprived of a bottle of water, or you are given a ration water for 1 or 2 days. What will you feel? So that is going to be what we are going to face. So currently the research in biospace has also addressed how to support or how to provide these consumables for long-term missions. So this is a continuation of the previous slide. So that the research article mentioning all the details. It's a very wonderful article. In fact, the risk level has been classified the low, medium, as well as high. And the planned human missions by different countries are also being listed over there. So in what all ways we can actually perform experiments and what all ways we can analyze the result, everything is compiled into a single slide. Maybe sometime later, if I exclusively focus on that aspect, I will discuss sometime. But before that, what I wanted to emphasize here is that currently our country is having a space biology vision, and I happen to be a proud member of that vision committee for ISRO. So we have two emerging domains that I wanted to highlight here today with respect to this human space missions. We call them one as the space biology, and the second is called bioastronautics. So from the smaller biological systems to human explorations, we have laid out a roadmap. So starting from cellular molecular biology to development biology to building subsystems, we have a long way to go. So in order to accomplish the goals, we have put the timelines as well. And here, the whole country has to aim and support the research and development of technologies that allow humans to travel safely and productively in space. The underpinning point is safely and productively in space. So what is that critical component when we come to the conducting of laboratory experiments? The critical component is actually the customized hardware for the experiments. So you believe me, if you want to perform science in space laboratories, you need to have 100% support from an engineer. So I would just emphasize here that space biology and bioastronautics is one domain of science, in fact, which has at least, it cannot have any boundaries at all. Even if it is having a boundary, it's having blurred boundaries with engineering sciences as well, engineering sciences and technology. Okay, so accordingly, there are several categories of experiments possible, like human in loop experiments, humanoid in loop experiments, as well as completely automated set of experiments. These are all which can be planned by you, each one of you. When we come to bioastronautics, you can see it is a multidisciplinary. Every subject under the sun can be brought under this bioastronautics because it incorporates biology, engineering, medical sciences, as well as space sciences. Earlier days in our country, medical professionals, they will never talk about space explorations or space biology. But now India is in a position where our medical professionals, engineering professionals, biological and the hardcore science people, along with the space science people, can go hand in hand to build marvels. Okay, we have also announced the building of another engineering marvel in space, what we call as Indian Space Station. So when we talk about the medical risks in space flight, there are several risks posed by microgravity, isolation, all the factors, whatever I have previously mentioned in the slide. And in that, in the first mission, in fact, our group is attempting to find maybe a more sort of detailed understanding of the kidney stone formation in space travelers. So here, the healthy and productive habitation of space is something that we are looking forward. So we need the technology as well as the engineering aspects to support that mission. And we do have a huge challenge is to protect our space travelers. It can be a Vyomnaut or Gaganaut. We have not named them yet. So during the space flight as well as following long flights, how can their life or how can their health be protected to the maximum level possible, in addition to providing the daily consumables like air, water, food, medicine. And along with that, dealing with the issues arising from the gravitational biology. So this is something that we need to aim for, that is research and development of technologies that allow humans to travel safely and productively in space. And the next point is more important to the community sitting over here, because from space, we have to bring the benefits back to Earth. And this has been one among the significant or the salient features of Indian space program. the space science for society. So we aim to bring back the benefits of every ₹1 spent on space research back to the community on Earth, our fellow people on Earth. So these are the biological features of space flight. You might be knowing much of them, but here I just wanted to just emphasize this area, human engineering. It's an evolving domain. Okay, so now now from the previous slide, I was talking about many research still going on in space stations. Then why come we need to reproduce, or we need to replicate those research? And to just make you aware, we cannot actually reproduce such experiments. The point is we need to have our own database for all such phenomena which are with respect to our space travelers. The reason being the individual sensitivity to space flight stressors can modulate biological responses, and this is very important depending on the genetic, demographic, and lifestyle variability. So when an ESA astronaut or a NASA astronaut is traveling, the biological data that has been accumulated from their studies may not match or may not 100% suit for an Indian human space traveler. So definitely country has to have its own capabilities to explore this particular domain, bioastronautics as well as human engineering. So host of opportunities coming up. As mentioned, there are several areas which are already being explored, and ISRO has established itself as a doyen in this particular field. And apart from that, we need to have other platforms also to be explored. For that, balloon facilities are available with TIFR Mumbai, sounding rockets are available with ISRO. Then we are having certain ground-based facilities also being built up. Small example I will give in the coming slide. So everybody can start with identifying ground-based analogs. They can conduct microgravity science experiments. Microgravity science is not a science. Microgravity is one platform where science can be performed to some exciting levels. So flight opportunities we can explore, and of course the space biology proposals will be solicited by our ISRO in and out. So that those things you need to explore further. And definitely for colleges, Hubballi College and all, I would urge that you can start with academic programs by instituting some mentors from ISRO and start our training the next space biologists, next generation space biologists. You can actually conduct some microgravity life science experiments. All this stuff can be actually done. Okay, so when you go into the global picture, of course, it is a huge area, bioastronautics. Lots of research and internship opportunities are available outside India, especially with MIT and University of Colorado Boulder. IAC is having links with most of these institutes. And then we do have our own programs where these areas, whatever I have listed on the right, is being pursued to a considerable extent. And we are growing in these domains. And this is another area if biotechnologists are sitting over there. And of course, you can have some of your friends from aerospace engineering to go hand in hand and build something, a huge area, which is called space synthetic biology, which has its own challenges as well as opportunities. So this particular research article that I have listed over here, it actually tells you about 6 grand challenges, what they call in space synthetic biology. So we are looking forward for engineering the biological systems for space exploration, not only space exploration, for industrial uses as well as for understanding the science in detail. So the bacteria, archaea, eukaryotes, all these things have been harnessed for space use, and they can be brought back and customized for applications on Earth. So there is a question now coming up in most of your minds, where to start. Of course, we can start by exploring the platforms which are available for conducting microgravity experiments. You can watch, keep a watch on ISRO's announcement of opportunity call in the ISRO website. And these are the platforms currently available or maybe available in the near future. Satellites will be available in the near future. Scientific balloons, as I mentioned, it's already available in the country. The stage 4 of the Polar Satellite Launch Vehicle, what we call as PS4 platform, is ready, as well as sounding rockets are available. So you just use the space flight opportunities to perform your scientific and technology demonstration experiments You empower yourself, you prove it to the peers that, okay, I have the capability to do that. You can also use the platform not only to characterize, refine, test, also to calibrate your experiments. And even these platforms can be used as a test bed for a new concept. And you can actually continue the existing microgravity research if you are doing something in that domain. And of course, again, I would like to remind you that the hardware to conduct the experiments are going to be the bottlenecks, or are going to be the real challenges that we are going to face when you are exploring this thing. So to elaborate slightly further on PS4 orbital platform, you can see that after satellite ejection, this guy will be just roaming around till the fuel is consumed 100%. So till that platform is available, you can use them for microgravity experiments. We have several payloads successfully flown, after which ARIS has been from IIST. So the capabilities are with respect to the multi-payload platform. You can have multiple payloads, lifetime up to 6 months, power can be drawn, attitude, 3-axis attitude control, facilities for data storage, as well as communication is also available. So designing, why should we conduct such experiment? Because designing, conducting, and optimizing this ground and pre-flight experiments can be a very good starting point for space biology experiments. So this is something that all can explore. And you see, we may have our own space laboratory by 2030. Definitely learning from experts also become critical. International linkages become critical. So this is a simple example where we started the space biology at IIST. This was a submission against an announcement of opportunity call. So this is our research team, and we are just trying to understand the changes in kidney stone formation happening during space flight. And the model organism selected for this particular purpose is Drosophila melanogaster, the simple fruit fly. So if you talk about the fruit flies, they are the marvelous, golden bugs, because they are called, with bagging some 6 Nobel Prize in physiology and medicine, and with 77% of disease gene similarity with human. They are one among the highly explored species for space research. And these statements from NASA, Ames, and ESA are self-demonstrating. Tiny flies make big biology happen in space. Many things that happen to flies in space also happen to humans in the long term. So one important model to study the disease in humans are going to be the fruit flies, and we are currently exploring that. And these are the functional, the hardware build-up that we have completed in IIST. For me, it has been a transition from the Earth laboratories to space laboratory. I have been targeting this space biology emerging in India, and I wanted to grow along with this particular domain. And fortunate enough to be in this generation where our country has started the program, and we are now trying to contribute as much as to the country in terms of our own research and our own motivation, which is being transferred to the students across the country. Okay, so another example for research which can support this particular space biology experiment is the microgravity simulating platform. This is a simple example of a random positioning machine. It's a 2-axis machine, and we are able to generate G forces of 10 to the power minus 3. And this was tested for both Drosophila experiments as well as plant growth experiments. And we are happy to tell you that we could get a very wonderful results out of that. Not going into the details, essentially because this particular design is under protection. And I would also emphasize one point that this particular project was completed by one of my MTech students, a girl, Shrujana. She completed this particular project in 1 year time. So where there is a will, there is a way. And I actually encourage my students as much as possible to give their best. This is what the country actually needs today. Okay, so this is the real fabricated thing. And this girl, she is Shrujana, along with our director, Dr. Vinay Kumar Tedwal, who supported a lot in these programs. So I'm not just, it is moving. You can see that. We will skip the video faster. Yeah. Different angles. It's having a lot of components, in fact. So maybe we will switch it. And just to sum up, we at IIST are pursuing space biology, and in the longer run, we want to integrate the artificial intelligence into the space biology experiments, as well as in our exploration for personalized medicine, as well as bringing in the Internet of Things in microgravity simulating platforms different. I mean, my dream is actually a far-fetched dream, and I'm 100% sure that with the support from my students and support from the whole student community in the country, we will be able to make a mark. Actually, we want to become a very critical link in the space biology continuum in the globe. Space biology is it's a continuum now. We want to become a critical link in that venture. That is what my dream is. So, of course, we understand perseverance is the key, because the life cycle of a typical bioscience life experiment, it takes somewhere around minimum 5 to 6 years to mature and then go to the launch pad. So not so easy at all. Different peaks we will be facing, but albeit all these things with strong motivation and encouragement from our gurus, as well as the support from our students, we will be able to scale sufficient heights for a country's space program. That is my wishful thinking. So why should we struggle like this? This is my inspiration, because the accomplishments in space have a huge impact on Earth. If you see, more than 2,000 products are spin-offs from space technologies, and several in medicine. You cannot tell that the space research is actually spending crores of rupees unnecessarily. No, not at all. Whatever precision medicine or whatever precision techniques that we have brought to Earth is mostly from space research, even the food for the kids. Okay, so many things, all are listed over here. And with respect to ISRO's technology transfer also, you can look into the various number of sensors, the prosthetic food, polyurethane food, and all. What all things have developed, they have a footing on the space research which is taking place in the country. So I believe in growing by networking. And for the students who are sitting over there, you may please set your goal, and it may look something unachievable. You don't bother about it. I earnestly urge you to pursue your dreams. And in the process, definitely you should be looking at the international picture with lots of national spirit and steadfastness, goodwill, and unabashed optimism. Be optimistic. Okay, we can achieve those goals. Okay, and our aim should be in this particular domain. Our aim should be to develop indigenous technologies to sustain Indian human in space programs. So I believe we have a long way to go, as well as a lot more to learn. With that, this is some of the glimpses where I was fortunate enough to have lengthy discussions with Wing Commander Rakesh Sharma. This is Dr. Sharmila Bhattacharya, the Fruit Flight Lab Director from NASA Ames. My collaborator, Dr. Ravi Kumar Husamani, he's still with this particular, he only originated the Drosophila experiment in our laboratories. Our chairman, this is my startup team. I have a startup company whom I'm mentoring within IIST. This happens to be the PSLV C52 launch, where in IIST had one satellite. So many experiments, myself with Vyomitra. This is Srujana and my PhD student Chitra. We have a lot of foreigners. I mean, this is my collaboration with the TU Delft, Netherlands, where the ambassador from Netherlands actually visited. Okay, so many things. I'm just telling you that our life becomes very busy when we are into this particular domain. And with that, I would like to wind up this particular lecture by expressing my sincere gratitude to the organizers. Definitely my institute, who has been supporting me from the beginning. The advantage is that I and my institute are growing together. I happen to be joining the institute on the first day of its inception, and my parent organization, ISRO, as well as all my students and collaborators. And finally, thanking all of you for your kind patience. And if you have any doubt, you can please have a email communication with me. My email ID is presented over here, and my personal webpage, where you can get some more details about this stuff, is also listed over there. Thank you once again, one and all. So with that, I come to the conclusion of my lecture here. Thank you so much. Jai Hind.
Thank you very much, ma'am, for such a wonderful talk. I think this was one of the unique talks we had as a part of this webinar series, combining space and biology. And I'm sure a lot of students who are interested in biology, they can think how to connect it with space. With that, platform is open for questions. If there are any questions, participants can ask directly.
They can also mail me directly if they are interested. Okay. In fact, I made it into the smallest capsule possible to keep it in within the time. But at the same time, I just wanted to tell our young fellow men that lot of things need to be explored. Okay. And we have every potential within us. Just explore. And we are there to support in whatever way is possible. Indian Institute of Space Science and Technology and my group working in space biology, and we are actually taking baby steps in this endeavor. So having a group is always good. Okay, and if Hubballi College also requires any support from my end, definitely I can be. Okay, that we can, if you are interested. It's a promise from my end. Okay. It was great seeing all of you. And Shivaraman sir, again, thank you so much. You only facilitated this particular. Thank you so much.
Thank you, ma'am.
Thank you so much. I think Jain sir is also there. Thank you, sir. Thank you so much. Thank you so much. I'm really blessed to be, to present something in front of these veterans. This is something I always cherish because those are the unique opportunities we get. We get blessings from them. That is something our student community also should learn. Whoever is there, please make sure that you utilize the resources. We have enormous resource within the country. Please make them, utilize them, and never ever think that we are working away from Earth. We are not useful to Earth. We are the people who are going to be very useful because the meticulous nature of space research is like that, only for that thing. Okay. Again, thank you so much. I think we will not prolong and will not stand in between the Shivaraman sir's talk and our audience. Okay. Yeah, thank you so much. Thank you so much.
With that, we move on to the next session by Dr. Shivaraman sir. So I request Dr. Shivaraman sir to proceed with his talk.
Yes. Make the screen big. Can you make the screen big?
Hello.
Hello.
Is it visible,
Can you
sir?
make the screen bigger?
No, sir. It is maximum, sir.
Okay. Good evening to all. Myself, Dr. Shivaraman. I will be speaking today about orbital mechanics, and it will be in two parts. The first part I will cover in a very most simple way what is orbital mechanics and what is meant by orbits of the satellites, rockets, and many things, and what are some of the challenging problems in the orbital mechanics. Next slide, please. Next. Veena madam is there? Hello? Can you go to my left side?
1 second, sir. 1 second.
Yes. Good. Next one, please. Hello. Next one. Yes. So what is basically meant by orbital mechanics? It is actually a study of motions of rockets, artificial satellites, and space vehicles, which are all moving under the influence of forces like gravity, atmospheric drag, thrust, and many other forces. It is actually a modern offshoot of the celestial mechanics, that is, dealing with the motion of the planets. Like natural celestial bodies such as moon around the earth around the sun. Next one, please. So it is offshoot of the celestial mechanics, which is called orbital mechanics. Next. Now, there are basically two laws that govern the motion of satellites, which is the basic of the orbital mechanics. One is Newton's law of universal gravitation, another is Kepler's three laws of motion. I will just briefly introduce them. Next one. The universal law of gravitation states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of the masses of their two particles and inversely proportional to the square of the distance between them. That is the basic Newton's law of universal gravitation. It is shown in the next slide. Next one. If there are two bodies with masses m1 and m2, which are separated by a distance r, the force between the two due to gravity is g into m1 m2 by r square between the two masses m1 and m2, where r is the distance between the two objects and m1 and m2 are the masses. Next one. Now, there are basically three laws that governs the motion of the satellites or the planets. The first law states that the orbits of the planets are ellipses, with the sun as one of the focus of the ellipse. So this is the sun, which is at one focus of an ellipse, and this is the other focus, and the planet goes around the sun in an ellipse. This is what is stated by Kepler as the first law. The same applies for the satellites also. Satellites go around the Earth in an elliptical orbit. Next one. Next one, please. The second law states that the line joining the planet to the sun sweeps out equal areas in equal times as the planet travels around in the ellipse. That is, when the planet is at aphelion, that is apogee, which is furthest from the sun, it travels very slow, and when it is nearest to the sun, that is perihelion, that is perigee, it travels faster, so that the areas covered are equal when it is nearest to the sun or away from the sun. So this is the second law of Kepler. Next. The third law states that the ratio of the squares of the revolutionary periods of the two planets is equal to the ratio of the cube of their semi-major axis. That is P1 squared by P2 squared is equal to R1 cubed by R2. Where P1 and P2 are the periods and R1 and R2 are the distance. These are the three laws of Kepler which govern the basic portion of the satellite. Next one. Now, in satellite orbital mechanics, basically what we try to determine is position of the satellite or the rockets or the space vehicles or very things which goes around the Earth. So in order to know where the satellite is, we should know their position. And in order to uniquely define the position and velocity of a planet, of a satellite at each time, 6 parameters are basically needed. There can be 3 position components or 3 velocity components. But this is not so well used There are other forms of orbital representation, and one such representation is a Keplerian ellipse. Next one, please. So basically, in orbital mechanics, we use six basic Keplerian parameters, which I will be describing now. Next one. Next one, please. So two of them are semi-major axis and eccentricity. You know, if you know elliptical orbit of a satellite, there is a term called semi-major axis and eccentricity. These two are the two parameters which are used to define a satellite. They are shown in the next slide. Next slide, please. This one shows basically the ellipse. These are the two focuses where at one point the sun is there and the earth goes round. These are semi-major axis A. Next one, please. And the second parameter is the eccentricity. That is, next one. E is equal to square root of 1 minus b squared by a squared, where b is the semi-minor axis and a is the semi-major axis. So these two are the basic parameters of the sixth one which are used. Now other four parameters are basically angles, and I will be describing them now. Next one. This diagram shows this is a plane of reference, that is the equatorial plane, and this is a gamma is the first point of area where the sun crosses the equatorial plane. The satellite celestial body or the satellite is shown in an elliptical orbit around that. Then the angle between the inclination, angle between the ecliptic plane and the farthest position of the satellite, nearest position of satellite in the orbit, perigee, is called argument of perigee. And if the celestial body is at an angle away from that angle mu is called true anomaly. And this angle in the anti-clockwise direction, that is called longitude of ascending node. And the angle of the orbit with respect to the ecliptic plane is called inclination. These are explained in the next two slides. Next. So inclination is the angle between the orbital plane, that is equatorial plane, and orbit of the satellite, and the equatorial Earth equatorial plane. That is a plane of reference. That is one angle. Then there is a longitude of ascending node or right ascension of ascending node. That is angle measured in the equatorial plane between the reference direction in the space pointed to vernal equinox. That is where the sun crosses the equator, and the position of the perigee. Next. Next one. Then the argument of perigee defines the location of the perigee in the orbital plane with respect to the equatorial plane. That angle is called argument of perigee omega. And mean anomaly M defines the position of the orbital body along the ellipse at the reference state. Next. Next one, please. Go ahead. Yes. So these are the 7 parameters, 3 scalar parameters and 4 angular parameters. So once you know these parameters, you can define the position of a planet or a rocket or a satellite around the Earth. And this is basically what is done in orbital mechanics. Determine this angle and determine their positions. Now, why do satellites go around the Earth? When an object is thrown parallel to the ground with an initial speed, it travels for a while and falls to Earth at a point, say A, as shown in the figure. If it is thrown with a little higher speed, it travels for a longer distance and falls at a point B. If the speed is still higher, it may fall at a further distance. All this happens because And other is the gravitational pull of the Earth, G(m)m by r square. Small m is the mass of the satellite, m is the mass of the Earth, r the distance between the satellite and the Earth, and G is that called gravitational constant. So these two forces, when they are balanced, the satellite go around the Earth. That is the velocity, if V is such a way that the two forces balance each other, the satellite will go around the Earth in an elliptical orbit. So that is why the satellites go around the Earth. Next one. So when the horizontal speed is equal to the value given by the equation, when the gravitational pull is equal to the centrifugal force, the object goes into a circular orbit around the Earth. That is mv square by r is equal to gmm by r square. So the velocity of satellite is equal to square root of gm by r. If the speed is slightly higher or lower than this, it will go into an elliptical orbit. Assuming that atmospheric drag is zero, there is no drag of the satellite, the object will continue to go in the orbit forever. As an example, 1000 kilometer, the orbital speed is 7.35 kilometer per second, and at 20,000 kilometers, it is around 3.9 kilometer per second. This phenomenon happens in natural satellites or planets as well, like the moon, as like the satellite around the Earth. Next one. So this is the basic principle of satellite motion. Now, when the satellite go around the Earth, there are so many other forces acting on it other than the gravity, and even the gravity is not constant. There is a change in the gravity of the Earth with time. So these are all called perturbation parameters. There are basically 5 perturbations of the satellite orbit. One is the atmospheric drag, that is called air drag, because there is a neutral atmosphere of the atmospheric density, the satellite gets decelerated and slowly the velocity decreases, accelerated, and the velocity decreases. This is called atmospheric drag. Then the Earth, because the Earth's oblateness, the gravity is not constant at everywhere, that non-spherical gravitational attraction of the Earth. The second perturbation. Gravitational attraction of the sun, moon, and other planets is a third body effects. Solar radiation pressure, both the direct and albedo component, that is the direct sunlight and the reflected sunlight. And variable part of the Earth's gravitational field arranged with the solid Earth and ocean. These are all the orbital perturbations. It is very important to model these orbital perturbations and correct the 6 orbital elements regularly so as to get better orbital position. Next one. So I will deal with all these forces one by one. So this shows the solar gravity, the albedo reflected sunlight acting on the satellite, lunar gravity, as the satellite moves, the air drag of the atmosphere, Earth's gravity pulling it here, tides in the ocean and Earth, and solar radiation pushing it this way. So these are the perturbing forces acting on Earth, near Earth satellite, shown in this figure. Next one. Among all the perturbations, the most important ones for a low Earth orbit are the atmospheric drag, that is due to the neutral atmosphere, and Earth's ablatant effect, that is the gravity effect. Previous one. Previous one. So, no, next one. So atmospheric drag, as the name suggests, is caused by the retarding experience while moving through the atmosphere. The atmospheric drag is proportional to the projected area perpendicular direction of the flight, and the direction is along the negative velocity vector, and this is given by this term, where CD is the drag coefficient, atmospheric density rho, the surface area, and unit velocity. This atmospheric drag is usually modeled knowing the atmospheric density model. So if the atmospheric density model is good, the atmospheric drag is very good. You can calculate easily and then apply the correction for the satellite perturbations. Next. This is the drag acceleration given by Ft is the force by mass, and this is the term drag parameter CdS by M. This is called drag parameter set. And this is actually the acceleration given by this. Next, which is a retarding force, and the satellite loses its velocity slowly, and slowly it re-enters the Earth's atmosphere and goes. Second force, the shape of the Earth resembles an ellipsoid with an equator radius about 20 kilometers larger than the polar radius. And it is all given by a potential V as a function of R, distance, theta angle, and phi longitudinal angle by Gm by R, and this is a spherical harmonic. These constants CNM and SNM can be calculated by tracking the satellites and knowing that regular orbital parameters. You can calculate this gravity effect, these terms, and then calculate the gravity effect on the satellite and apply correction for the non-spherical gravitational attraction. Next one. Next one. So this is maybe the potential given by this. These are all the different terms. Next. Next. Now, there are other forces like solar radiation pressure, which is both direct and albedo component, that is the reflected components. And the photons striking a satellite exert a minute pressure on it. The acceleration due to such a force depends mainly upon the mass of the satellite and the surface area exposed to the sun. Then solar radiation pressure is zero when the satellite is in Earth's shape. So finally, the equation of motion of a satellite is given by d squared r by dt squared plus gm by r squared r vector plus f, which is the perturbative force, is equal to 0. These are all the perturbative forces and acceleration term, and this is a main gravity term, which is the major component of the force. So if you solve this equation, putting a model for this force F for different forces, atmospheric drag, non-spherical harmonic components, and other things, one can solve the position of the satellite can be obtained, and thus you know where the satellite or a rocket or even a space debris is there. So this is basically the orbital mechanics. Basic equation is usually in orbital mechanics to solve, to know the position of the satellites or even planets. So this is basically what is called orbital mechanics. Next. Now the table here shows the force on a GPS satellite, which is at an altitude of 20,000 kilometers, and there is a resultant acceleration due to those forces. The central gravitational force, that is major force, causes an acceleration 0.56 meter per second square. Equatorial bulge, that is the non-spherical component of the Earth's equator, that is 5 into 10 to the power minus 5. Lunar and solar gravity, 5 into 10 to the power minus. Solar radiation, 10 to the power minus 7. You see, the main force is the Earth's gravity, but these minor terms also contribute, like the equatorial bulge, lunar solar gravity, and solar radiation. So all these have to be considered if we want to know the position of a GPS satellite very accurately. And that is one of the challenges which I will be explaining later. So in addition to 6 Keplerian elements, the orbital perturbation terms, the mean anomaly, argument of perigee, inclination, and right ascending and ascending are also required to calculate the satellite position. So there are 6 plus 4, 10 terms required to know the position, like a GPS satellite which is at 20,000 kilometers. Next. Next one. So this is again the basic equation of motion. This equation is motion of the satellite solved to get Keplerian elements and also orbital perturbation parameter. This is basically the what the mathematicians do in the orbital mechanics. In addition to 6 Capillary elements, the orbital perturbation terms are also determined. Next. Now the position of the satellite, which is at ship P above the Earth, which is represented by an ellipse. Actually, there is an equatorial bulb and polar are tightly flattened like an orange. So we can either define the position of the satellite above the Earth in terms of lambda, phi, and x above what is called ellipse or in Cartesian coordinates x, y, and z. Next one. Next. So these are called Earth's fixed coordinate system. The origin is at the center of the what is called a ellipsoid in WGS 84 World Geodesic System, and that is called center of the mass. The z-axis is between the north and south poles with positive values increasing northward. The x-axis is in the plane of the equator passing through the origin and extending from 180 degree longitude, and y-axis is in the plane of the equator passing through extending from 90 degree west. So this you can read further later. Next. So basically the coordinates are obtained what is called Earth's fixed coordinate system. Next. Now there are different orbits satellites are launched for different scientific purposes. I will be going through what are the different orbits and how they are used in where they are used. The most common one is the low orbiting satellites. They are relatively close to the Earth, several hundred kilometers above the Earth. They are short orbital period, 90 minutes. Once in 90 minutes, they go around the Earth. There is no specific minimum altitude, like ISS is at 200 kilometers. We can have many revolutions per day in a low orbit satellite, but a swath area, that is coverage area, is limited. All manned space missions, except lunar missions, where LEO, basically they are using remote sensing satellites and Earth observations, weather satellites, space science, communication satellites that provide internet service, that are called low Earth orbiting communication satellites nowadays. So low orbiting satellites are basically used for remote sensing, weather, space science, and communication. Next. Next one. So this is showing the Earth, north and south. It is at 1,000 kilometers low Earth orbiting satellite at inclination to an equator, low inclination. This is a low Earth orbiting satellite. Next. Next one. This is the International Space Station at a height of 200 kilometers going around there. That is also another kind of low Earth orbit satellite. Next one. Next one. Now, the second kind of orbit is a medium Earth orbit. Medium Earth orbit comprises a wide range of orbits. It can be anywhere between a low Earth orbiting satellite and a geostationary orbit, which will be coming later. They are typically around 20,000 kilometers, like GPS. GPS is medium Earth orbit. Previous. It is similar to low Earth orbiting satellite, and it is used by a variety of satellites with many different applications. It is very commonly used in navigation, like the European Galileo system or GPS. Galileo powers navigation communication across Europe and used for many types of navigation, from tracking large jumbo jets for getting direction to your smartphone. Galileo uses a constellation of multiple satellites to provide coverage across large parts of world all over. So basically, the GPS and Galileo are medium Earth orbit navigation satellites that provides navigation. The medium Earth orbits are preferred by providing navigation services. Next one. Next. So this is a medium Earth orbit satellite. This is a GPS satellite going around there at 20,000 kilometers. Yes, there are about 24 satellites going around there, and minimum 4 satellites. Another type of orbit is a geostationary orbit. That's commonly what we use in our TV. They remain over one location over Earth's orbit. As the Earth rotates, the satellite also moves along with that. So relatively, there is no relative motion between the satellite and Earth. It is achieved by placing the satellite in a special orbit, where orbital period exactly equals 1 day. Altitude is roughly around 36 kilometers, and inclination is near zero. That is, it is over the equator. Geostationary satellite can see up to 70 degrees north and up to 70 degrees south, plus or minus 70 degrees. They can see north and south of the equator up to 70 degrees. Geostationary satellites mainly used for satellite communication or permanent rare station in space. They are also used in data relay. Therefore, coming Jabin satellites, we will use geostationary satellite for relaying the data. Rarely they are used in satellite acquisition. You see, geostationary satellites are not preferred in satellite navigation, but the geometry is very poor. Next one. So this is geostationary orbit. The satellite is at a height of 35,706 kilometers. The satellites move around the Earth. As the Earth rotates, the same angular velocity, the satellite also moves around. So that is always fixed and looking at the satellite. So you can send the data and receive it back without any disturbance. Next one. Using geostationary orbit for communication pose severe problems in Russia, since so much of their land mass is above 70 degrees. As I told you, geostationary satellites can cover up to plus or minus 70 degrees. So the Russia cannot be covered by geostationary satellite. So this was overcome by creating what is called a Molniya orbit. And I will cover that in next, what is called Molniya orbit. So Russia uses Molniya orbit for communication. Next. So it is a highly eccentric orbit. So when the satellite is here, it travels fast according to Kepler's second law of motion. And when it goes high and it is further away from the Earth, it moves slowly. So suppose Russia is here. When it passes over Russia, the satellite will be moving very slowly. So 1/3 of the time, the satellite will be visible over Russia. And if you have got 3 satellites in the same orbit, which are at 120 degrees separated, you can provide communication above 70 degrees in latitude. So these are called Molniya orbits. And Russia uses that. Next one. Next. They are highly inclined and highly elliptical orbit. They cover northern Russia, large apogee altitude, and very slow velocity at apogee. If apogee is over Russia, then satellite hangs over Russia according to Kepler's second. Next. Now, Molniya orbits are also used for providing navigation. That is called, there is a system called wide area augmented system, like our Gaggan, which India is providing. That is an augmentation to GPS to provide a better service than a GPS. And Japan is using highly eccentric orbit, Molniya orbits. They are also called tundra orbit for them. It is called quasi-zenith satellite system. And they use Molniya orbit to provide. That is, the satellite they are using 3 GPS satellites and 1 highly high eccentric orbit, and with these 4 satellites they will be determining the position. So this is also used for navigation. Next, Japan is using that. This is the thing. You see here, the satellite will be moving slowly. So one will be always there. And next one. Next. So here, the satellite will be moving fastest. Around 70% is the same. One satellite will be hanging over Japan, and they will be providing the service. They will be covering, having a transmitter like a GPS transponder and transmitting the signal. Next. So there are 3 orbits. With the 3 Molniya orbits, that is highly eccentric orbits, we can cover, provide GPS service. Next. Now another is a polar orbit. In polar orbit, satellite usually travel past Earth from north to south rather than from west to east, passing roughly over equator's poles. They are a type of low orbit, Earth orbit. They are about 200 to 1000 kilometers, but passes over poles. Their inclination to equator is 90 degrees. Because inclination is around 90 degrees, a satellite polar orbit will eventually pass over every part of the world. That is the advantage. This makes polar orbit well suited for satellite gathering information about Earth, such as satellite weather, Earth's weather, and remote sensing. Satellites in polar orbit do not have to pass the north-south pole precisely. Even a deviation of 20 to 30 degrees is good enough. So this is called another type of polar orbit, using communication and weather. Next, this shows the polar orbit. It travels pole to pole. Next one. This is a sun synchronous orbit. It is a particular kind of polar orbit traveling over the pole. It are synchronous with the sun. Suppose a satellite is going pole to pole and the period is 24 hours. It is synchronous with the sun's motion moving from east to west for 24 hours. This means they are synchronized always in the same fixed position relative to the sun. This is called sun synchronous orbit. This means that the satellite will always observe a point of the Earth as if constantly at the same time of day, which serves as a number of applications. For example, it means that scientists and those who use satellite images can compare how somewhere changes over time. So satellite remote sensing people can use sun synchronous orbit to revisit the same place at the same time on different days, and use it to study the variation. So this is called sun synchronous orbit. Next. So this is shown in the next diagram, sun synchronous orbit. So this is the sun synchronous orbit. They are at a height of 600 to 800 kilometers, but period of about 24 hours. Next. So if you want to monitor an area by taking a series of images of a certain place, sun synchronous orbits are very good. Therefore, scientists use image series like this to investigate how weather pattern changes, to help weather prediction. They also use to monitor the Earth's forest and everything, how it changes. Just now, another is a transfer orbits or geostationary transfer orbit. This is where a satellite is, a rocket is on the lower orbit first, it goes around the Earth, and at a particular, at the apogee, the rocket fires and the satellite goes into a geostationary orbit, that is at 36,000 kilometers. This orbit, intermediate between the geosynchronous and the launch, is called geostationary transfer orbit. That is how we launch to our GSLV, our geosynchronous satellites. Next. Next one. So this is how you already covered. Next one. Next. Now the interesting point called Lagrangian points. For many spacecraft being put in orbit, being too close to Earth can be disruptive to their mission, even at more distant orbits such as geostationary orbit. For example, for space-based observatories and telescopes whose mission is to photograph deep dark space being next to Earth is hugely detrimental because Earth naturally emits visible light and infrared radiation that will prevent the telescope from detecting any faint light like distant galaxies. So photographing dark space with a telescope need to be next to a glowing Earth will be hopeless. Next one. So Lagrangian points or L points allow for orbits that are much further away and do not orbit Earth directly. These are specific points in the space where gravitational field of Earth and Sun combine in such a way that the spacecraft that orbit them remain stable and can thus be anchored related to it. In fact, the fuel required to maintain in that orbit is minimal. There are 5 points between the Sun and Earth, L1, L2, L3, L4, and L5, where the gravitational field Earth and Sun combine in such a way that a spacecraft can orbit. These are both 4 times further away from Earth than the Moon, compared to Geos, which is 36,000. Next. So these are Lagrangian points. They are shown here L1, L2, L3, L4, L5. The JWST, that is James Webb Space Telescope, is launched in L2. That is a Lagrangian point L2, so that we can have an uninterrupted view of the space, and our India will be launching a satellite called Aditya L1 at L1, so that the satellite will have uninterrupted view of the Sun and study the Sun. If a spacecraft are launched to other points in space, very distant from Earth, they would naturally fall into the orbit around the Sun. And those spacecraft would soon end up far from the Earth, making communication difficult. So we cannot launch spacecraft further than that. Instead, spacecraft launched to the special Lagrangian points stay fixed and remain close to Earth with minimal effect without going into different orbits. At these points, the pull due to gravity of Earth and Sun are equal. So these are Lagrangian points. Next. These are observational and space missions. They use L points. The solar telescope SOHO and LISA use the L1 point. Herschel, Planck, Gara, these are all the satellites. They are at L2 point. Aditya L1, India's first satellite to explore Sun, will orbit around L1. It is going to be launched this year. Webb telescope is at L2, which is 1.5 million kilometers away from Earth. It will actually orbit L2 as L2 orbits around the Sun. This special halo orbit helps spacecraft to stay in place without burning much fuel also. Next. So this is basically Lagrangian points, specific points in the space. Next. Now we'll tell in another 5 minutes and close some research problems in orbital mechanics. The one of the things is a better orbital prediction. As I told you, the perturbation parameters are very difficult to model and predict. For example, in GPS, the orbital position is transmitted to users for satellite navigation, and it should be very well known. So these are GPS is tracked by a network of tracking stations all over the Earth, and for 12 hours they are predicted, and these parameters are transmitted to the GPS satellite, stored and retransferred to the user and used. The position error of the GPS satellite is of the order of 5 meters using this predictor parameter. And these 5 meters is not tolerable. They get a position accuracy of 5 meters in landing of an aircraft. It should be at least 0.5 meters. So GPS transmits orbital parameters and perturbation parameters, 12 hours, but they are not very accurate. The accuracy in positioning is only 5 meters. If position accuracy is 0.5 meters. So using an augmented system where you use real-time tracking, the position accuracy achieved is 0.65 meters. And more research is required to improve the air drag and gravitation that can improve GPS positioning accuracy without any. And this is a challenging problem. Next one. Next. Now you see better accurate prediction of re-entry of situation. Last Saturday, in the Saturday night, over Gujarat, there was a re-entry of one of the satellites, and the people mistook that it is a meteorite, and they could see it breaking into pieces and falling. And everybody thought it is a meteorite, but it was actually a Chinese rocket which re-entered the Earth, and people could not predict that it is a satellite re-entry and it is not a meteorite, and warned the people in advance that don't be panicked. And after 1 or 2 days only, it was predicted that it was actually a big Chinese rocket that broke into pieces and fell over Gujarat. Another incident was the SpaceX. Recently, a SpaceX lost of Starlink satellites immediately after launch due to solar storm. Nowadays, solar storms are very prominent, and this due to solar storm, suddenly there is an increase in atmospheric density. And what happens is satellite drag, the satellite starts falling to the earth. In fact, there were 40 satellites for launch by SpaceX a few months back, and around 20 of them started falling one by one to the earth. People were wondering what happened. It could not be predicted. And you see here, and this Starlink satellite lost 20 of them. So you can see in this, what is this? And it is accurate prediction of satellites during solar storm is very important. Next one. So there is a scope in that. Better accurate position of asteroids passing over here. It is a rocky fragment left over from the birth of solar system around 4.6 billion years. One of them, they are entering the Earth, and scientists estimate there are millions of space rocks in this part of space. Sometimes these asteroids change their orbit if they come under the influence of planet's gravity like Earth. They can also collide one another or even collide with the Earth. Once a stray rock measuring 20 meters in diameter hit the Earth in 2030, with up to 33 times the power of an atomic bomb. So even now, many asteroids are predicted to fall. They are close by for passing through the Earth. The accurate position of the asteroids is very important, and more research work is needed. Now next. So these two are the interesting things. Finally, I thank Mr. Mathur and Indian Space Industries Exhibitors from Ahmedabad, as well as KLE Societies and PC Jabin Science College, Hubballi, for inviting me to talk in front of you. I am more happy and thankful to you students for attending my lecture. Most part of my presentations are from details provided in the internet, and you can search in internet and get more. I will be very happy if someone could take up orbital mechanics as a subject for a PhD in future. And if any help is needed, you can contact and my email ID and mobile number or in my first name. Thank you very much. Have a nice day. Bye.
Thank you very much, sir, for such a wonderful talk on orbital mechanics. I'm sure students who are from physics background will be able to connect with the orbital mechanics, and they are really inspired to take up orbital mechanics for their future studies. With that, forum is open for question and answers. If there are any questions from participants, they can ask question to sir. Any questions from participants?
No problem. You can ask me later also through email. I'll be happy to answer.
Okay.
Thank you. Have a nice
Thank
day.
you very much, sir, again. And we are really privileged to have you as the expert for this wellness webinar series. Thank you very much.
Okay. Good.
We now move on to the next talk of the session. Himanshu Shukla sir. Shukla sir, are you there? Himanshu Shukla sir, are you there?
Yes, am I audible?
Yes, sir, you are audible. It's great pleasure to have Himanshu Shukla sir will be taking us to the journey of rockets and his role in creating the motors for the rockets. It's my pleasure to introduce Himanshu Shukla sir. Sorry, I am traveling, so you might hear some background noise.
That's fine.
Sri Himanshu Shukla sir completed his Bachelor's of Engineering in Chemical Engineering with honors from Government Engineering College, Ujjain in 2012. He later joined ISRO in 2013 at Satish Dhawan Space Center, SDSC Shar, Sriharikota, which is Spaceport of India. Since 2013, working in solid propellant plant for production of rockets includes S200, S139, PSOM XL rocket motors for more than 20 PSLV, GSLV Mach 2, GSLV Mach 3 launch vehicle missions. He was also involved in the development of solid stage rocket motor for launching prestigious Chandrayaan 2 and Gaganyaan. Presently, since March 2020, he is working at surface treatment, thermal painting divisions of at the divisions of Space Application Center. He is responsible for surface treatment operations like gold plating, silver plating, anodizing, etc. on the satellite components. He has also developed and established more than 50 numbers of new processes for space application. It's a great privilege to have you, sir. And I'm sure with your expertise as a youngster working in the field of space, students will really get inspired to take up this domain as their research career, and they will contribute in the field of science and technology. Over to you, sir.
Thank you so much for the nice introduction. Firstly, I would just like to ask, am I audible clearly?
Yes, sir, you are clearly audible.
Okay. First of all, I would like to thank ISI committee, organizing committee, and college members for organizing this awareness webinar series for students, which I think is really good initiative taken. Not taking much time because I think already we are going late. So I would just jump to my presentation. Whether my presentation is visible?
No, I don't think so. Now I think. Yeah, now I can see your screen.
Hello. Start. Am I audible?
Yes, sir, you are audible, sir.
Okay. With the presentation mode. Not able to share my screen here, right?
You have the permission, right, to share the screen?
Yeah, I think so. Just a second. Just try one second. Yeah, whether my screen is visible to all, the presentation.
You may share the screen right now, sir.
Okay.
आप लॉगिन कर रहे हैं एग्जिट करके वापस करो शेयर कर स्कैन करो उसको
Hello.
We can see it now, sir. We can see it. We
Am I
can see your presentations.
Sorry for the delay. So I would like to directly go for the presentation, and I'm going to give a very small presentation because we are already late and some delay because of the internet problem today. We faced the whole day, and I think Shivraman sir has given a very good introduction about the satellites, how they rotate around the Earth. So I would like to begin with challenges and opportunities in the field of chemistry and chemical sciences in space industries. So basically my topic will cover like how the chemical engineers and chemistry people are involved in developing rockets or satellites and other space-based applications in industries. Here, my first thing, I would just like to tell you the outline of my presentation. Firstly, as you can see, the main aim of ISRO is launching satellites and launching satellites to like around the Earth in low Earth orbits, geostationary orbits. Based on applications, we launch satellites. And for launching satellites, we need a vehicle, a launch vehicle, we can say. So I would just like to give a brief introduction about the launch vehicles, spacecrafts of ISRO, like what kind of propulsion mechanism is used for different rockets, the polymers, adhesives, and chemical paints used in space industries for spacecraft manufacturing and rocket manufacturing. As well as for satellite manufacturing, we use different kind of surface treatment operations. And all these points involve like application of chemical sciences, or you can say chemical engineering is definitely involved in a very big way. We can say in launch vehicle development and spacecraft development, which I don't think much people are aware of, if I can say about the students. But I'll just give a brief overview of everything. Here we can see like space industries like ISRO are multidisciplinary organization, which involves all the science fields, involves physics, chemical engineering, mechanical engineering, electronics, etc. All are working together for the development of launch vehicles, spacecraft, and space-based applications. Here, since I was talking about the chemical engineering and chemistry background, I would like to cover, as I said, rocket propulsion, polymers, surface treatment operations, ablative materials, etc., which are used in space application industries. Firstly, I would just like to give a brief introduction, like what are the launch vehicles of ISRO, or we can say rockets of ISRO available. We started with SLV-3, which is like a satellite launching vehicle. In 1980, the first SLV-3 was launched successfully. Here we begin with a payload mass of very less, around 40 kg. We tried to launch to a low Earth orbit, and the lift-off weight of the rocket was around 17 tons. Next, from 1980 to 1992, for 12 years of hard work, we were developing ASLV. It is called as an augmented SLV, which is having a cluster of strap-on rockets, which was used to again launch a payload of around 150 kg. We have increased the mass by almost 3 times to low Earth orbits. Then came the workhorse of ISRO, which everybody knows, PSLV. It's the XL version because it surrounds, as you can see, these small rockets, which are called as PSOM XL solid propellant rockets, which are around 6 numbers. So it's like an extended version of PSLV, because PSLV doesn't have this strap-on rockets. It only has the main core. The main core consists of a solid propellant rocket, which is the center stage. Then comes a liquid stage, which is the second stage. The third stage is again a solid stage. And the fourth stage, which burns in the space, is again a liquid stage over which the satellite is attached at the top in the heat shield, as you can see. After development of PSLV, we were trying hard to increase the payload capacity, initially which we were having to achieve around 1860 kg, as you can see here with PSLV. And with GSLV Mark II, we were able to go up to 2.2 tons. And with Mark III, we have gone up to 4 tons. Now, all these launch vehicles are having solid propellant rockets as the main core stage. If you can see the Mark III here, it is having 2 strap-ons, which are S200 solid propellant rockets. And the center stage is L110, which is a liquid stage, which consists of liquid propellants. And at the top, you can see whatever black color, if you can see in the GSLV Mark II and Mark III, these are the cryo stage, which is like one of its kind developed by India, because the technology was very difficult to achieve, but somehow, and I can say with very deep hard work of our eminent scientists, we were able to achieve the cryo stage, and it's a big achievement for us. And now the payload mass which we can carry to the geosynchronous transfer orbit is around 4 tons with the GSLV Mark III. And I can tell you this GSLV Mark III launch vehicle is only going to be used for the Gaganyaan mission as well, for launching humans to space. Now, as I already explained, what are the application of rockets? We can see here, we have to carry the payloads, which is our satellites or spacecrafts, to the orbits like low Earth orbit, geostationary orbits. All the orbits have been very nicely explained by Shivraman sir. So I'm not going to touch that topic. And also we use rockets for launching interplanetary missions like Chandrayaan mission, Mangalyaan mission, and now we are planning for Aditya mission as well. So the rockets will be used for launching those satellites as well. And in future, we are going to carry out some space work, like we are going to launch our own telescopes to observe the space bodies. Also, we are planning to have our space station, which is like Indian made, so that our humans from India can go in space and do all the experiments as explained by earlier in the biological presentation as well. Now, as I covered the launch vehicles, I just want to give a very small introduction about the spacecrafts of ISRO. We have like communication satellites. The satellites can be broadly categorized in this manner. Like communication satellites are used for communications, as we all know that we are having B2H, we are having mobile phones, and all these communications are happening because of these communication satellites which will be launched to, like we can say, geostationary orbits, which is 36,000 kilometers from the Earth. Then we have Earth observation satellites, which we used for Earth observation, mostly for remote sensing, like ocean observation. Then we go for like mapping of the terrain areas. Then we go for many observations like civilian. Then we have defense applications. We can have a very good observation from the satellite of all the Earth areas, maybe rivers, mountains, and everything. through this Earth observation satellites. These will be launched in the low Earth orbits. Then we have some scientific spacecrafts in which we are planning to study, like as Sir said earlier as well, for Aditya mission and Lagrange's points and all the other interplanetary missions, we use scientific spacecrafts. Then we have navigation satellites. We all have GPS in our mobile phone. That GPS is working because of the satellites of Global Positioning System, which is US made. We have our own Indian made navigation satellites as well, which is called as IRNSS, or we can say Indian Regional Navigational Satellite System, also called as NAVIC. Then these are the other small satellites, student satellites, experimental satellites, which we launch with the launch vehicles. Next, I would just like to give a small introduction about the rocket propulsion. For chemical engineers, I think this will be the best suited thing for space industry. The propulsion of all rockets, jet engines, deflating balloons, or you can say aeroplanes and jet engines, which use propulsion mechanism, is explained by the same physical principle, which is Newton's third law of motion, which states that every action there is equal and opposite reaction. Here you can see in a rocket on the right side, I'm just depicting a small rocket. Whenever a fuel is burned in the presence of oxygen, so whenever oxygen combines with the fuel, a combustion reaction is happening, because of which gases are generated. And these gases are exited from the nozzle area, or we can say the bottom area of the rocket. And when these gases are having that high energy gases, when as a product of combustion, they are passing through a nozzle where their velocity is increased. And because of this velocity is increased, the kinetic energy is increased. And when the kinetic energy is increasing, there is an equal and opposite action, because the gases are coming out at very high kinetic energy by Newton's third law of motion. An equal and opposite reaction is happening to the rockets. The rocket moves upwards in the opposite direction of the flue gases. So because of this basic law, the rockets are flying. And we can see one more law which governs the rocket movement is law of conservation of momentum. It also describes the same phenomena. Whenever the momentum is given to the flue gases because of the combustion energy, the same amount of momentum will be transferred to the rocket. So only the direction will be different. The flue gases momentum will be at the towards the nozzle side going outwards, but the rocket will be flying in the opposite direction, we can say in the upward direction. And this is the simple rocket phenomena where the mass of fuel is burning and coming out. So the mass of rocket is reducing by m minus delta m, and the flue gases are coming out. So delta m is the amount of propellant which is burned and coming out of the rocket. And in the right side, you can see that reaction energy I have explained, where the force is acting in the opposite direction of the flue gases. Now, the type of rocket propulsion system, like broadly, we can categorize into three categories, which are like chemical rockets, electrical rockets, and nuclear rockets. Chemical rockets are very simple. As you can see, a combustion is happening between a fuel and oxygen. And these combustion energy is getting converted into gases, is forming very high energy gases, or we can say flue gases. And these combustion products, when coming out with high kinetic energy through the nozzle, it imparts the opposite force, we can say the reactant force to the rockets, which makes the rockets flowing or flying outside the atmosphere. Here, a combustion is happening directly between the chemicals. Then we have electric rockets. Here, electric energy is again converted, is again generated by either solar energy or nuclear energy. Here also we are generating the electric energy, and then that electric energy is responsible for that whatever working fluid will be there inside, like ionic form or ions, we can say. These ions, or we can say when electric energy is imparted to these ions, they generate electricity, and they generate, we can say, high kinetic energy ions, which are coming out through the nozzle and imparts the momentum to the rocket. Next comes the nuclear fuels. That again, nuclear, everybody knows, the fission reaction or fusion reaction. Whenever fission reaction is happening, everybody knows a large amount of energy is generated, and this energy can be used for generating the reaction force for flowing the rocket outward. Since I am mainly covering about the chemical engineers or chemical sciences background, I'll just describe the chemical rockets. Chemical rockets can be classified as solid rocket motor, which uses solid type of chemicals for generating combustion energy. Liquid rocket engines, which uses the fuel or chemicals in the liquid form to generate that energy. And third will be the hybrid rocket engine, in which we can say it's a combination of solid and liquid. Let me define a little bit about solid rocket motors. It is like the simplest form of the three propulsion system, as I described, solid, liquid, and hybrid. Because in this solid rocket motor, the chemicals are mixed in a fixed proportion, which consists of a fuel and an oxidizer. The oxidizer becomes a part of the propellant and get imbibed in the rocket in the form of solid. So that whenever it leaves the Earth's atmosphere also, there is no need of oxygen because already oxygen will be supplied in the rockets. So this oxygen is either in the form of solid, in the form of oxidizer, or in the liquid. In case of solid rocket motor, it will be in the form of solid. This is just a schematic of a solid propellant. Here you can see at the top there is an igniter which initially ignites the propellant chemicals, and it is responsible for like starting the rocket propellant. It consists of a grain. Grain is nothing but a mixture of chemicals which are solidified and cooled in a casing. As you can see, the center part of the rocket is hollow. Why it is hollow? Because we need to provide maximum surface area of the grain so that when igniter burns, all of the surface area throughout the casing will burn together and the flue gases will be coming out through the nozzle. Nozzle is always a convergent part because we all know whenever by continuity equation, if we are reducing the area, the velocity increases. And once the velocity increases, the kinetic energy increases. The higher the kinetic energy, the higher the momentum will be transferred to the rocket to fly. So that's why nozzle, you can see always a nozzle plays a very great role in defining the momentum of rocket. Again, you can see the casing will be protected by the propellant because casing will be around, I can tell you, the thickness of the casing will be in the range of 10 to 15 mm only. But still, it will not, the burning of propellant will generate a temperature of 2500 or 3000 degrees centigrade, but it will be protected by an insulator material, which again is generally nitrile butadiene rubbers or other insulating materials, polybutadiene rubbers, which are protecting the casing from the high temperature of the flue gases. And again, you can see at the end face of the propellant is an inhibitor. This again is a polymer, which is like IPDI or TDI based. It protects the end faces of the grain from burning so that only the center part of the propellant grain is burning and not the end part. So it gives a uniformity in burning throughout the burning stage. Now, since you can see the solid rocket motor is compact and it is very much, you can say, standard, it is a fixed kind of thing. Once you start the ignition, there is no way to stop the solid rocket motor. And also it gives you a repeatability, a uniform kind of ignition. But as I explained further, there are many complexities in liquid or cryo, or we can say hybrid rocket motors, which is not there in solid rocket motor. That's why I call this the simplest form of rocket. Now, as I told you, the grain consists of chemicals. These chemicals are oxidizers, which provides oxygen to the fuel, which are like, which is going to burn and create that energy for combustion. The oxidizers used are different kinds of nitroglycerine, ammonium nitrate, ammonium perchlorate, nitrocellulase, whereas fuels can be used as aluminum, ferric oxide, metal hydrides, etc. Then to bind this oxidizer and fuel, we need a very good binder so that it can hold it together throughout the burning stage. It should not break during burning because high amount of pressure energy will be generated during burning of rocket. So we need very good amount of very good quality of binder which can bind. And let me tell you one thing, these binders are not compatible with every kind of fuel or oxidizer. Different oxidizer will have different kind of compatibility with different binders. So always the complexity lies in defining the chemicals which are used to make the propellant rather than after making the rocket and firing the rocket. So the complexity lies here. Chemical engineers plays a big role in defining all the chemical reactions between the oxidizer and fuel in the presence of binder and how it binds the solid propellant. Also, it contains plasticizers because the viscosity will be very high and it needs to be casted in a very long grains of around 10-meter height. So we need some plasticizers to improve the flowability. Then all this liquid, or we can say slurry, has to be casted in a grain, or we can say in a casing, and it needs to be cured. Cured means it needs to be hardened, like concrete is hardened. So we need curing agents. Different kind of curing agents are used, like IPDI, TDI, etc. And again, we can play with the burn rate if we want to increase the burn rate fast. So more flue gases will be generated for a very small time. And thus, because when it flies through the nozzle, a high amount of kinetic energy can be generated for a very short span. Thus, we can also modify the burn rate by adding burn rate modifiers. So I can tell you one thing, like the very huge amount of chemistry is involved in selecting a propellant, in making the solid propellant. And once everything is finalized on paper, and we can say like everything has been conducted a pilot trials, or we can say small trials, we can always go with the big rockets. And once we have established a solid propellant, it becomes a backbone of the launch vehicle, we can say like that. I just wanted to show you how does a solid rocket booster look like. I've taken picture from NASA. You can see the rocket is very big, and we cannot make a very big solid propellant grain because when we are casting it, we need to achieve uniformity. So it's always made in form of small segments. As you can see in the center, there are almost 5 segments which are casted separately and then joined together. And all these segments, when they are joined together, you can see there will be gap in between the propellant grains. And as I explained earlier, the propellant should always burn from the center and not from the ends. So again, here comes a very big role for chemistry, or we can say chemical engineers. Like we have to develop a material which inhibits, or we can say which doesn't allow the end faces of the propellant grain to burn. And when we are joining it, again, when the firing is happening, you can see a cylindrical burning is happening from the center to the end. We can say from the hollow cylinder, the cylinder is getting expanded, and the inhibition material, the polymeric material which we are applying on the end faces, also should be eroded accordingly. Firstly, it should not burn because it should protect the end faces. Secondly, it should get eroded as well, so that the burning should happen uniform, the same thing. And you can see at the end there are nozzle, and at the top there is nose cap. And this is just a schematic. I just wanted to show you how does a solid motor looks like. It's a very simple mechanism, a hollow cylinder we can say, which is consisting of a grain which burns during the after ignition. Now let me come to a liquid rocket engine. Liquid rocket engine, as it's clear from the name, it consists of fuel and oxidizer which will be in the liquid stage. Apart, as we have seen in solid propellant, it is in solid state, so it comes in the liquid stage. The liquid rocket engine can be of 2 types, either pressure fed or turbojet fed. In solid propellant, we have a very simple mechanism. It will be casted and it will be solid, and when the burning starts, it starts burning from the center to towards outside of the case. But when we come to the liquid stage, here, since the oxidizer and fuels are in the liquid form, it has to be, like you can see in the cylinders at the top, it has to be stored separately, and it has to be fed to an engine, and in a very good proportion, or we can say a very defined proportion only. The liquid and the oxidizer in liquid form and the fuel in the liquid form should reach the engine, and it should ignite at the same time and start combustion, which generates flue gases. In the same principle, it makes the rocket fly. But here, to feed the liquid continuously to the engine, we have 2 kind of system, either pressure fed or turbojet fed. Turbojet fed means it's a motor, or we can say a pump will be there, which will be continuously pumping the liquids. Or we can have, as you can see in the number 1 in the right side of the diagram, highly pressurized gas will be there, which will be pressurizing the top of both the tanks containing liquids. And this pressure will be controlled with the help of valves at the bottom 5 number you can see. And these valves will be allowing only the sufficient amount of fuel or oxidizer to go towards the engine and burn, so that continuously uniform burning can be achieved. and no need to have any pump or anything to feed the liquids to the engine. Here, the pressure feed system is generally used because we can have a pressurized tank which can continuously pressurize the liquids towards the engine. Now, in liquid stage, we can see since a firing is happening at the engine, it requires cooling mechanism. Why cooling mechanism is required? Because there are two things. Firstly, we should know about the rocket. The rocket should be of very less or minimum weight, because if we increase the weight of the rockets, then we cannot increase the weight of the payload. So it has to be designed in such a way that with minimum weight, minimum insulation, minimum cooling mechanism, we can achieve the maximum thrust. So the maximum advantage of liquid engine is we can anytime stop the liquid engine and anytime restart the liquid engine, even in space, by controlling it from the Earth. This happened in the Mars mission as well, when the engine was stopped after launching from the Earth, and it took almost, we can say, 6 to 7 months to reach around Mars. And then the major task, when we gave the command to start the engine, everybody was crossing their fingers whether it will start or not. But luckily it has started, and I don't say only luckily, but with great efforts of our eminent scientists of ISRO, we were able to achieve that ignition, and we were able to achieve that orbit around Mars, as sir explained already, the orbits. And we were able to achieve everything of which we have achieved in Mangalyaan mission because of this liquid engine ignition and initiation. And like there was a cooling period of around 7 months, there was no burning at all. Now, let me just tell you a very small thing about liquid engines. There are two kinds of liquids. Now, liquids can be used separately. So they need to be ignited together when mixed together. So they are two kinds, either hypergolic or non-hypergolic. The hypergolic is whenever the liquid oxidizer and liquid fuels comes in contact, immediately a spontaneous reaction occurs and combustion flue gases are generated, or combustion is happening, and there is no need of ignition. These are called as hypergolic. Whereas some example of some hydrogens like MMH, UDMH, hydrogens with N2O4 MON can be used. And other is non-hypergolic. It requires ignition device to initiate combustion. As in case of cryogenic, we can say when the liquid hydrogen, which is stored at very low temperature, and a liquid oxygen again at very low temperature of less than minus 250 degrees centigrade, when they are coming together in the engine, they need an ignition to start combustion. That ignition device can be any kind of pyro thing, or a different kind of ignition mechanisms are available. So for non-hypergolic like cryogenics, we need ignition mechanism, whereas for hypergolic, we don't need ignition mechanism. Directly they can be mixed together in the engine and generate thrust. This is just, I just wanted to show you the difference between the solid and liquid engine. Here you can see the liquid engine is a very complex engine. It is having very small lines of liquids and cooling mechanism, and there is turbojet mechanism, there is a pressure fed system. This is only the engine. The liquid which is stored is at the top of it, which is not shown in this diagram. The liquid fuel and liquid oxidizers will be stored separately and will be fed by either one of the mechanism like pressure fed or turbojet fed. And this is just the engine where the ignition, or we can say where the combustion is happening. And around this, you can see so many lines, the complex lines, which is responsible for many things like cooling, regenerative mechanism. And it was all developed by India as well. This is just a picture of a liquid engine from NASA, which is called as RL10A4. Just this diagram, I just wanted to show you the difference between the solid propellant or solid motor and a liquid engine. Next, as I said, there is one more kind of rocket mechanism, or we can say an engine, which is a hybrid engine. It combines the advantage of both solid motor and liquid engines. How? Because as you can see in the diagram, there is a pressurized neutral gas at top, which is going to use for the feeding mechanism for liquid oxidizers. Here, the oxidizer will be in the form of liquid, which will be there at the top of the solid fuel. At the bottom, you can see solid propellant grain. Now here, the difference between the earlier solid propellant motor and this motor is it doesn't have oxidizer. The oxidizers will be supplied by the liquid oxidizer, and there will be a spray nozzle mechanism, which will be spraying continuously the oxidizer on the surface of the solid grain, and the fuel will start burning because of the supply of oxygen from the liquid oxidizer and fuel from the solid fuel. It is having like you can say it is better than solid but less better than liquid. It is kind of in between. The better than solid I can say is it can be controlled. If we stop the liquid oxidizer supply to the solid grain, there will be no ignition. It can be stopped or restarted, whereas a solid propellant once burns cannot be restarted. And here we can use the liquid oxidizers like liquid oxygen, lithium fluoride, liquid fluorides, and the solid fuels can be polybutadiene types like STPB or PTPB. Okay, so next. Now, since I've explained you a different propulsion mechanism consisting of solid, liquid, and hybrid, the future propellants which I can tell you is conventionally we are using many chemicals, and everything in the propulsion requires chemicals are very hazardous, like monomethyl hydrazine, unsymmetrical dimethyl hydrogens, the ammonium perchlorates. These are all generating fumes, or we can say flue gases, which are very toxic and which are very harmful to human being as well as to the environment. So future, we are expecting many more innovations, or we can say generation of new kind of propellants, which are called as green propellants, which are less toxic compared to the conventional propellants. Some examples are ammonium dinitramide based, hydrogen peroxide based, or we can from water electrolysis, we can generate a gaseous oxygen and gaseous hydrogen, which can be combined together to generate thrust. Also, we can use some ionic liquids which can replace MON and MMH. These are hydrazines which are very dangerous, not only to humans, but to environment as well. Now, since I have covered a lot about the rockets and propulsion mechanism and the chemical engineering application in it, I just want to highlight a small topic, or we can say it's a very big topic in space industries, but I just wanted to touch it. There are many polymers, adhesives, and paints which are used in space industries in the development of space crafts or launch vehicles, which are having various applications like protecting the case of solid motor, as I explained. Then protecting the end faces of segments, also we use polyurethanes. Then we have nozzle assemblies. Nozzle assemblies will be covered with some polymers, which are different kind of polymers which are protecting. Some are like ablative, some are like self-sacrificing as well. Then we have different kind of satellite assemblies which use polymers or adhesives. Then we have thermal insulations for insulating the two bodies, which is generating high heat, and the heat should not be transferred to the other bodies because it will cause many harm to the circuits of the spacecrafts. Then we have electrical insulations, and we have conformal coatings for all the circuits which we are using in spacecrafts. Typically, the polymers we are using are silicon-based, polyamides-based, epoxy-based, acrylics. These are just the examples which we are using in space industries. And there is a very big scope of development of new kind of polymers, which is having a very good, as you can say, like space is having a very harsh environment. In Earth, we can say the temperature only goes one side. Either it will be very cold or it will be very hot in some countries. But in space, you can see the temperature varies a lot. It can go up to minus 250 degrees centigrade and go up to plus 250 degrees centigrade. Depends on where you are choosing the space, near the sun, away from the sun, near the planets. So there is a very harsh environment for the spacecrafts in the space, which demands development of different kind of polymeric materials, which can sustain that temperature shock, thermal shock, we can say like that. Also, when we are planning the interplanetary missions, we are planning to develop some polymer concretes so that when we go to the moon or Mars, these concretes can be developed and used for making inhabitants or habitants for living, we can say like living or storage. There are different kinds of epoxy resins used for solid rocket motors. And these epoxy resins also plays a very big role because they are very hard. At the same time, they are very much, you can say, thermal resistant. And some epoxy resins are very good conductor as well. And some are very bad conductor. Then I just want to touch a topic which is thermal insulation. For regulating the temperature of most of the spacecrafts, we have a polymeric film of carbon, or we can say a black pigment. Whenever we are using black color pigment for making a polymeric film on the top of the spacecraft, it absorbs sunlight, or we can say it absorbs radiations. And whenever we want to reflect the sunlight, we can coat it with a layer of aluminium. At the same time, when we are not using any polymers, we can just protect it by developing a different kind of materials which can sustain at high temperature, which is having good reflectivity, less absorptance. There are different kinds of process also is involved which provide that kind of properties. Now I can tell you one thing is we are protecting the outside of the spacecraft sometimes with the white paint, so that all the radiation coming from the solar should be reflected back and should not be absorbed and should not heat the spacecraft components. Whereas the inner side of the spacecraft can be used, can be black painted, a different kind of polymeric paints we used here, which can, like you can say, emissivity is very high. So it can emit all the radiations which are getting generated inside the spacecrafts. Other than thermal protection, we also have different kind of surface treatment operations for protecting. So whenever we are manufacturing satellites will have different kind of instruments, and different kinds of instruments will have different roles. Sometimes it is generating electricity, sometimes it is generating heat, sometimes it is supposed to transfer the heat from one point to the other point, sometimes it is supposed to absorb the heat from the outside. So for imbibing that kind of properties to any material, we do different surface treatment operations for increasing the corrosion resistant as well, for increasing or changing the optical properties like emissivity, absorptivity, improving solderability of different material. Like we want to solder two materials, but those two materials are incompatible for soldering. So we provide a coating of a gold coating, we can say, on both the materials. And when both the materials will come together with the solder, there is a very good bonding between these two materials by providing a top coating. And also we are improving the RF performance of materials. Generally, we use aluminium in spacecraft components, and aluminium is not having the best electrical conductivity, but it is having very less, you can say, specific weight, because it reduces the weight of the spacecraft which is required, so that less space of we can say less space of spacecraft is there, so we can use less energy to transport it into orbit. So for improving the RF performance, we increase the electrical conductivity by providing a coating of silver plating or copper plating based on the end application. And these surface treatment operations, as I explained in plating, here you can see a schematic, whereas an electrolytes will be used, and there will be one cathode and one anode. Cathode generally will be our spacecraft component, which requires the properties of the surface to be changed. And based on end application, if you want to increase the RF, we can go for silver plating. If you want to increase the solderability properties, we can go for gold plating. If you want to increase the electrical conductivity, we can go for copper plating. So in the same way, these different electrolytes are used for plating different kinds, and different anodes and will be used for plating different kinds. And you can see the metal ions which are dissolved in the electrolytes will get deposited on the cathode, which is our spacecraft component. One more application we have in surface treatment is anodizing. Anodizing, in which here the spacecraft components in electroplating is cathode, but in anodizing it becomes anode. And here generally we do for aluminium, we form a very thin layer of aluminium oxide on the top surface of spacecraft components, which imparts very good corrosion resistant properties to the spacecraft component. So based on the end application of the spacecraft, or we can say the component, we use different surface treatment operations, and which helps in making the complete spacecraft as per the plan, or we can say as per usage. Just I would like to conclude, this chemical sciences, as I described, plays a very important role in the development of space-based industries, and has great upcoming challenges in the development of, there is a very huge development market of rocket motors or engine, for launching satellites. As you can see, there is a very big space race going on around the world. You might have heard about SpaceX. You might have heard about 10 to 12 startups which are already started in India, which are making different kind of launch vehicles and are trying to provide least cost supply, or we can say transportation of satellites to the orbit. Then we need green propellants. A very big demand is there for development of green propellants. I think students can concentrate here and develop some green propellants which can reduce the harm to the environment and to the human race. Then we need different kind of polymers which are suitable for space environments. As for the Earth, there are many polymers available, but for the harsh space environments, when we are planning for interplanetary missions or we are planning for Aditya mission, we need some kind of polymers which can sustain a very high degree of temperature shock, or we can say high temperature or low temperature as well. Also, we need adhesives. As you can see, sometimes many part of electrical circuits needs to be bonded together, and due to temperature shock, or we can say high heat, these gets debonded, which causes great failures in launch vehicles and spacecraft. So advanced adhesives needs to be developed. Also, surface treatment operation, there is a vast opportunity for development of different surface treatment operations like electroplating of gold plating, silver plating, copper plating, nickel plating. There is a huge market available and huge scope for opportunity, I can say, for the students for developing new technologies which can provide very good properties to the spacecraft components and to the launch vehicles as well. Also, I can just want to say the very big nozzle which is made sometimes is anodized to protect it from the corrosion. With this, I just would like to thank the Director SAG, Deputy Director ESA, Group Head EFMG, Head STPD, the ISIE Organizing Committee for granting me this opportunity to deliver a lecture. And I think I was able to create some kind of little bit awareness in the students regarding chemical sciences, or we can say chemical engineering applications. And I would like to thank AC Mathur sir as well for inviting me to deliver this lecture. Thank you very much. And if any questions, I am open for the questions as well. Thank you very much.
Thank you very much, sir, for such a wonderful talk. And I think you have brought the complex subject of rocketry to, in a very lucid manner to students. And I'm sure with such a talk, I think they are really inspired to take up this subject for their future career. I have two questions. What is the role of nanofluids or nanoparticles in case of the chemical rocketry? And also the second question is, do you see the microfluidics coming into future for rocketry?
Yeah, very good question that is. In fact, I was trying to cover that topic, but because of the very less time, I've not gotten into that. This nanotechnology has become a very big, I can say a very big development in this field of spacecraft. If you see for surface treatment operations, if we go for nanoplating applications, it imparts very good properties of the plated material on the base surface. If I go for the if you go for the major kind of plating mechanism like gold plating or silver plating, and if I go with the conventional techniques, it deposit the metal ions which are the size of I can say in the form of nano is much better than it if it's in the size of size which are greater than nano or 10⁻⁻⁷ micron, or I can say, sorry to say that, but if I go for the fuel in the solid propellant or fuel mechanism, generally we use aluminum powder, which is in the range of the size of that the fuel size will be in the range of around 6 to 8 microns, and it goes up to 25 microns. But we are planning to develop an aluminum fuel which can be made in the form of nano size. Nano size aluminum fuel will generate I can say 2-fold times thrust on comparing with the conventional aluminum available. But the only problem comes in handling of the aluminum. The different kind of fuels, if we go with the nano, it increases the thrust energy, it increases the amount of combustion energy, because whenever we go for nano, the surface area of that particle increases, and thus it helps in increasing the combustion energy, and thus helps in increasing the thrust as well for the rockets. So nano always plays a very good role in increasing the properties, say surface treatment, or we can say in rocket fuel as well.
Okay, thank you very much, sir. I think there is a question from Dr. Ravi Gangadhar. Sir, if you could ask directly to the speaker. Dr. Ravi Gangadhar.
Like, can lithium be used?
Sorry, sir, I
As a
was not able
propellant?
to hear the question.
Can lithium be used as a propellant? And do we have any electric or nuclear rocket technology? And or as these are green propellant technology, as I feel.
Yes, sir. I think we have developed an electrical energy rocket engine in 2001 in NASA. They have demonstrated as well. And in fact, ISRO is also working in the field of electrical rocket propulsion. Just I would like to tell you one thing, like even if we are going for electrical energy, it has to be generated by either solar mechanism or by nuclear fission or combustion mechanism. So generally we use either solar or nuclear. So whenever this energy, or we can say that fission energy, is used for generating electrical energy, and rightly you said, this electrical energy will be used to flow these ions outside the rocket nozzle, which generates thrust. So it reduces the impact on the environment, like it reduces it. It can be told as green propellant, but only the mechanism of generating that electricity has to be specified. If it is renewable like solar, it's the best possible mechanism. But again, if we are going for fission mechanism, again it becomes a little bit complex, because again the controlling part is very difficult for generating electrical propulsion, because whenever fission reaction happens, you know, sir, it is an uncontrollable reaction. That's why many trials has been conducted for nuclear fission rocket engines, or we can say electrical engines, but still we are, I can say, a little bit behind in completely developing it and demonstrating it because of the complexity of the mechanism. But still, if it is being developed, it is the best possible mechanism which can generate high thrust with the minimum amount of combustion gases, or we can say minimum harm to the environment.
And how about if we make lithium ion as a propellant and it can be recharged, can it be made use in this?
Sir, yeah, sir. As you said rightly, lithium ion generally we are using in batteries in the spacecraft components. And you said lithium we want to use as a fuel.
Yeah, with rechargeable system, recharging system, so that it can last long with a green rate.
Exactly, sir. But the main requirement, as you said, I think you are talking about the interplanetary mission, because once we reach the outside the atmosphere, it becomes space. And once we are in space, we need some kind of mechanism when we are going for interplanetary, which we can restart and stop in between, so that always we can change the orbit of the satellite or spacecraft when we reach to different planets. And in that case, I think, as you said rightly, the battery mechanism can be used, but still now, or I can say as much I know, that it has not been that much developed, or that battery mechanism has not been used that much, because I think the major problem comes with the thrust, because a lot and lots of amount of combustion is required to generate that amount of thrust to throw the rocket out of the atmosphere. But once it's in space, there is no drag or no stopping. So even if I push a little bit, it will continue to travel in that motion until and unless some external force acts on it, which is like Newton's first law, you can say like that. So I think for interplanetary missions or mechanism where we are using, like I can tell you, like in International Space Station, wherever astronauts are moving outside the space, they are using electrical propulsion only, which is having just a small kind of, there are two kinds of mechanism they are using for traveling. Either they are having pressurized gas in their suits, so whenever the gas is flowing in one direction, they move to other direction, or they can use electric propulsion with a little spark they can generate that thrust so that they can move in one direction in space. But for ground-based application, the battery becomes a little bit tricky.
Yeah. I mean, we need to club both, inculcate three things, then we can have a maximum efficiency.
Right, sir. Rightly said.
Okay, thank you. Thank you.
Are there any other questions from participants? They can directly ask to Himanshu Shukla. Sir.
Do we have any? Yeah. Do we need to fill up any feedback form?
We'll be providing it tomorrow, the feedback form,
Okay, fine.
in the tomorrow session. So I again thank Himanshu Shukla sir for joining us all the way from Space Applications Center ISRO, and he has provided a very good overview of the rocketry to students, and I'm sure all students, all participants are benefited from his talk. And thank you very much, sir. And as this is the last session of today's last session, so I also thank all the session speakers today along with the chief guest. And we are really fortunate to have all of them, and I'm sure that students are benefited from their talks. With that, I request Professor Veena to make a few announcements. Over to you.
Yes, sir. I am Santosh. Instead of Veena madam is
Okay.
I thank all the speakers of today's sessions, starting from Padma Shri sir to last one Himanshu Shukla. All the sessions are very interesting, inspired, and benefited by the students. And tomorrow again we are meeting from 10 to 5 o'clock with the same Zoom link and same YouTube link. And thank you all the organizers and our society and our college principal and our head of the department. And I thank all the participants and students. Thank you, sir. We are meeting again tomorrow at morning 10 o'clock. Thank you, sir.
Thank you so much.
Thank you all. Thank you, sir. Thank you.